95 to 100% of the water, depending on how well they're installed.
We are live
Okay.
with the APEC conference. I just turned it on to go live, and welcome everyone in the live chat. We're about to get started here.
Okay. Yeah, and it is noon, so I'm going to mute everybody out, and I will read the intro, and then we will go to Remi after that. Okay, and I'll start in 3, 2, 1. Welcome to APEC. It's July 10th, and I'm your moderator, Tim Ventura. First, I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. In today's session, Remi Cornwall will discuss electromagnetic propulsion, including static E-cross-B devices in the Feynman disk. Sandy Kidd will discuss his extensive work in forced precessed gyroscopic inertial propulsion, and Mike Gamble will present a brief history of Boeing CMGs. After that, we're going to catch up with the latest research from the Falcon Space team and associates, and we'll be wrapping up the event with open discussion and ad hoc presentations. Okay, a couple of quick reminders. Wrapping up the conference replays, details, and speaker info on our website at www.altpropulsion.com. Please save your questions for the Q&A session after each presentation. Go ahead and type those into chat as we go, and we will go through chat as well as take live questions after each presenter finishes. So I am very pleased to introduce you to our first guest. Remi Cornwall is an alumni of UMIST Manchester and London University, having degrees and higher degrees in electronic, electrical, and information software engineering and physics. He spent the early part of his career in industry at blue chip companies, but devoted his spare time to problems in engineering physics, where he's acted as a troubleshooter to several companies, solving diverse problems in the annealing of metals, design of HV generators and medical equipment, as well as ignition devices, consulting in anomalous physics research and engineering. His research company is working on 3 projects at the moment: thermoelectric conversion with ferrofluids, secure communication by quantum entanglement, and novel forms of electromagnetic propulsion. So let's welcome Remi to today's call, and I will now hand it over to you, sir.
Hello, everybody, and thank you for turning up. As you've heard, I'm Remi Cornwall, and I've got a presentation for you. It's theoretical at the moment, linked up with well-known experimental results, and I'm just throwing this into the pot of ideas to say that I will do the homework first in terms of the theory base, or if you find something that's an exception to the theory base, explore it further, present your results to make sure you're not wasting your efforts, not tinkering and so forth. So let's go full screen now on 1 second. So if I share the screen, this one, not that one. Here we go, this one. Share. And let's get the presentation running. Oh no, PowerPoint has detected that your graphics card may not be configured properly. Damn it, I'm gonna have, one second. I'm gonna have to switch to the other screen.
Well, yeah, well, no worries at all, Remi.
Because you're not seeing the screen here. So, are you seeing, what are you, I can see what you're seeing, I think.
Yeah, and actually it was showing, yep, it's showing PowerPoint there.
It is?
Yeah,
brilliant.
Yeah, it is on your screen.
Good. Okay, so that's just my website. Probably if you did a Google search, you could probably find me. So,
and you might want to make it bigger. Actually, there's a lot of windows showing. You might want to maximize, or go into slideshow.
Yeah, I think it's the aspect ratio. I've got 2 screens. That's why you keep seeing me looking up. There's an HD screen and a little laptop screen, and it's not letting me do the presentation on the big screen. I'm sorry about this. I'll make the slides available. that's the front page of my website. So you've got 3 projects, maybe 4 with other projects, but that hasn't really panned out yet. So what I want to say, I think I've covered it. I'm just looking at my notes here. Yeah, I'm going to focus on EM propulsion theory, and if there's a little bit time, I might discuss the other projects. Now, the kind of things I like, obviously experiment is key in physics. You've got to have repeatable experiments and your theory based before you can sort of get into the applied science and the engineering aspects. So that's the kind of area I work in. Give me a phenomenon and I'll look at it, theorize in it, and do something with it. But if it's very apocryphal, you don't tend to stand much chance. But that's just my opinion, and that's not to dissuade anyone doing things which are right off the beaten path. You carry on doing what you're doing. Don't take my word for it. Okay. So let's go on to the second page now. So I've got a non-exhaustive list of candidates for EM propulsion. So ion propulsion, ferrofluid drive. Let's go from them one by one. So we know about ion propulsion. NASA are currently, and the Chinese are currently doing work in that. There's also ferrofluid. It's like the alternatives, like the electrical dual. So ion propulsion, you're dealing with things which are electrically charged. With ferrofluid drive, you're dealing with things which are magnetically charged. So things like superparamagnetic particles. It's very much like an inkjet printer, same kind of technology, and it can shove out at the exhaust, so you gain some impact.
Remi, I'm sorry to interrupt. Is it possible to maximize that window?
Can you see
in the PowerPoint window?
The PowerPoint window. What are you seeing? Are you seeing a window with slides down the side, or are you seeing the main window?
I am seeing the PowerPoint, but it's very small. It's only part of your. Oh, there you go. That's that. Yeah, right. That's giant. And actually, if you click resume slideshow, you have a resume slideshow button. That might.
No, you see what it's done.
Okay.
I've hit F5 and it's put the proper slideshow. It's put that on the small screen, and it's put the kind of preparation, the PowerPoint stuff, on the big screen.
Oh, I see. But still, that's much better. That's much better.
Right. Let's even make it even better. Okay.
I'm sorry for interrupting you.
That's all right. Don't worry about it. We've got photon rockets, which we know are just like a light source as your exhaust. Pair production. I don't think I made a slide on that, but I'll come back to that. The Lorentz force, or what you might call ampere forces. Einstein-de Haas effect. We'll come on to that. E cross B devices in general, and then the Feynman disk, which is another type of E cross B device. Now, I'm not really too concerned with the propellant-like devices, so things like ion propulsion, ferrofluid drives don't really turn me on. So what I want to see in the future is that we maybe can just put a power source, maybe it might be nuclear, and we've got all the energy in the world to get anywhere we want to, at least in this solar system, yeah, or to the nearest star systems. Yeah, you're going to run out of propellant. So let's consider things which can work solely from your power source. So I'll move on to the next slide now. And this is just a quick talk about ion propulsion and how they sort of put a figure of merit on rocketry. They talk about specific impulse, which is just the thrust divided by the rate of mass out the back. Yes, and you can quote it this way: newtons per kilograms, or meters per second. You can say it works for meters per second. You just put mv divided by m, the rate of change of m, or you can divide it some define it with the weight of the propellant expelled, and the units come out as seconds. Now, obviously, rockets fare badly. Turbofans are much better because you're hauling a whole load of air, which is free. It's just around you. Now, ion engines, the selling point is to have a very high exhaust velocity, so they currently have the best specific impulse of current technology. So if we look at these graphs, if we look on the one on the left there, if you have a quick look at those, you can see ion engines at the top at the moment. So you've got electric propulsion there, magnetic. Are you seeing my cursor move around as well? Are you? Yeah. Not ahead. That's great. That's great. Okay, so have a quick scan of that. I'm not going to spend too much time. Let's move on to the other graph. That's propulsion performance. So a specific impulse again versus Mach number. So you're seeing that obviously turbofans, great big huge hunking things on current airliners. Down at the left-hand side, slow speed devices, moving on to ramjets, and then you're moving on to scramjets. So that's all very conventional. Good people working on that, but we want to break the boundaries, don't we? We don't. We just copy what everyone else is doing. Let's move on to the next slide. Okay, photon rockets. You've got radiation pressure. You can see that things in things like the Crookes radiometer. You put that in sunlight and it will spin round. And we all know about comet tails as they go around the sun. The tail points away from the sun. So it's the radiation pressure. The relativistic equations describing this, just down here, describing how the energy of a body varies with the speed, the momentum, and you can just get a simple relation between these. And that's useful. Moving on to the photon rocket, you just take the ultra relativistic case. So you just set V equal to C there, and you get the usual ultra relativistic ratio. And that's the limit of it. If you're expelling things out the back, yes. But although it has the high specific impulse of C, it's very feeble. You're looking at 1 Newton per 300 megawatts, which is an extraordinarily huge amount of energy just to get a 1 Newton shove. So let's move on to the next slide and see if there's a way of doing things better than this. So I'm not going to upset the boat, rock the boat by believing that you can break things like conservation of moment energy, which is a portmanteau of conservation of momentum and conservation of energy. Yes, because they're very, very deep principles in physics, which we know are obeyed at least locally. Maybe not globally. You might have heard me a few weeks ago saying that there was this dirty secret in physics regarding conservation of energy in general relativity, but that's legerdemain stuff. Let's not talk about that. But there are very good reasons why you have conservation of momentum and conservation of energy. Now, it's all very technical stuff, but one can explain it intuitively. They talk about Lagrangians and Hamiltonians and making infinitesimal changes, translations, rotations, and so forth. And it so turns out that conservation of energy, effectively, it means that energy is a constant of motion of a system. So when you describe a system by its equations, you get this constant of motion, which doesn't vary with time. And what it's saying, intuitively, what it's saying is saying that the constants of physics don't change. Yes. So your gravitational constants, your electrical constant, and so forth. What it turns out that momentum is saying, and angular momentum, that what they're effectively on an intuitive level are saying that space is the same everywhere. It's homogeneous, and it's the same in any direction. It's isotropic, right? Respectively. So linear and angular momentum are saying that. Now, moving on to the next one. The problem that people will have there, where it will beg a belief, if someone says they've made a drive which violates conservation of momentum, because of the synergy of those in relativity, they're 2 bites of the same cherry. They're joined together in relativity with this 4 vector they call momenergy. It's not easy to pronounce, but momenergy. If you violate momentum in one frame, you definitely will violate energy conservation in another frame. And many people, it's just beggars belief. These are sacrosanct laws of physics. they're not prepared to believe. So maybe I'm a little bit conservative. Maybe I'm a little bit in awe of big science and the existing science base. But if you want to present your ideas, if you start talking wacky stuff like that, they'll show you the door. So in my humble way of doing things, I try to make the presentation as conservative as possible. Now let's talk about that list. Let's move on to ampere longitudinal forces, or the Lorentz force, which is, unless someone tells me differently, is the same thing really. What Ampere called his longitudinal forces seem to be what we call Lorentz forces. There has been some suggestion that the Lorentz force might be a candidate for making a reaction-less drive or a propellant-less drive. It seems to be, if you look at this image of a railgun and you work out the forces, the red bit here, which is the sliding device propelled by the forces, doesn't seem to react against anything. But it's not true. It's a deception. You can work out the forces from the Lorentz law and so forth. What's really happening is there's a reaction in this area, counter reaction. This length of wire around here is the counter reaction. But there's a graceful way of explaining this, and that's if you consider the flux through this area. And because the flux starts out as 0, goes to something, then returns to 0, you know that you're not violating conservation. I'll give you some time to think about that. After, you can look at the slides and so forth, but that's not a candidate. The Lorentz force is not a candidate. Now, something else which seems kind of weird, the Einstein-de Haas effect, where if you have a magnet, and we know that the magnet has internal spins, yes, and it's very strong in the ferromagnetic case. And to make a magnet, you magnetize the sample, the spins line up, and kind of get pinned in place. You can talk about the exchange force or vice force and so forth. The spins get lined up and you have an overall magnet. Now, the spin is angular momentum, exactly the same units. So if you go from, say, something which is paramagnetic or super paramagnetic, and the spins are random, and the angular momentum of the whole system is 0, if you magnetize it, the whole body will start to rotate very slightly. But this looks amazing. Maybe you've got something which seems to violate angular momentum. Not the case. Angular momentum is conserved. When you take the magnet off, it's going to revert back to how it was before. This is not a good candidate. You can't use this one. Okay. So we'll move on to the Poynting vector, which is an expression of the flow of electromagnetic energy. Now, I can direct you, not in these slides, but I can make slides available later to someone called Kirk T. MacDonald at Princeton. And he's got a very good account there about how this Poynting vector came to be. It's something which is seen as a little bit contentious, but if you accept the simplest definition works without adding on quirks, without adding on things which aren't Lorentz and invariant and so forth. So let's work with the simplest definition. You start from the continuity equation, and all this is saying you've got a region of some internal energy. Oh, excuse me. Trouble being in this editing arrangement here. You've got some region which has internal energy on the left-hand side. You've got a term which describes that flow of energy. And then you've got an area where you've got work, force times velocity. You're doing work, you're either absorbing work or generating work. When you just plug in the usual formulas for electromagnetism, you come up with this term here, which is called the Poynting vector. So that describes the flow of electromagnetic energy. Great. Let's have a look at the left image. Makes sense. There's a transverse electromagnetic wave. Just plug your values into this formula here, and it makes sense. The pointing vector is going in the direction of the wave. You know, hooray, that works. If you move your vectors around to the next segment of the wave, still points in the same direction. That seems sane. Let's discuss a simple circuit with a battery and a resistor. It's a little bit weird. You've got, you can see your vectors there. You've got the electric field. There's the battery, there's the electric field. There's a magnetic field going around the wire. And the pointing vector points out into space. It's a little bit weird, isn't it? Because you'd think that the power generated would be going along the wires. Seems to be, it's given an alternative picture, because if you look up here, this expression for the work done, you've got your Lorentz force dot the drift velocity. So obviously the cross term would go out. You take a cross product of a with the same vector, it's going to go out. So not surprisingly, you're just getting the usual Ohm's law thing here. Yes. So that works out. You've got two ways of describing it. So either you can say the energy is flowing through space between the wires, or it's flowing along the wires. And when you come down to the resistor, the energy is flowing into the resistor from space, or it's coming down the wires. So even though it's a little bit strange, it still looks like it's working. So let's take it over to the last diagram on the right, where people were seriously questioning the concepts here. And I think Heaviside is the first one, excuse me. Excuse me. Heaviside is the first one to bring this up, but most people know it from the Feynman lectures, where he talks about a charged particle next to a magnet. And if you work out the pointing flow, it's a static situation, nothing's changing, but apparently is a flow of energy. And he described this as just nuts. I think it was one of the expressions he used. You might know of this from his Feynman lectures, where he puts up a thought experiment to describe how, if it's true that there's electromagnetic momentum, this disk would rotate. And I'll just give a brief overview of what's going on. You've got this disk, obviously it's on dual bearings or somehow suspended in space. Around the edges are electrical charges. So you've got a radial electric field, and it's radiating out from the charges. And in the middle, you've got a coil, which you switch on. So his question was, what would happen when you switch the coil on? And what happens is the disk starts to rotate, starts to translate, angularly translate. When you switch it off, it will stop translating, it will stop moving. How is it doing this? Because it's not reacting against anything, right? He thought it was all nonsense, but the team, Graham and Lahoz, did the experiment in 1980, and they found it to be true. So before we go on to talk about that particular device, just a little bit of background about the electromagnetic field, which will come in useful. You can find this stuff from my propulsion papers. It's in the appendix. So let's talk about quantizing the electromagnetic field. But the reason why it's relevant. Yeah, you won't really find the reason for this in classical physics. So the usual is that you've got the classical solution to the wave equation with the vector potential, Fourier modes. You get the Fourier modes of the field. You can use that potential to find the magnetic and the electrical fields. Put that into the classical Hamiltonian, and then you, by analogy, compare the classical Hamiltonian to the quantized Hamiltonian of simple harmonic motion. And there's extraordinary resonance there, I say, between the two you can pull these concepts over and see that the Hamiltonian of the classical field looks like a simple harmonic oscillator. And then you just pull out the momentum operators and you relate them to the creation and the annihilation operations, which are just saying that when you create a photon, or they're also called ladder operations. When you create a photon, you do one operation, you create one photon, do it twice, you've got 2 photons, or if you annihilate, you've got 1 photon, then you've got 0 photons. That's all it is to it. So that's all the mathematical gobbledygook, all the steps I described on the previous page. But what's interesting, by the time you come down to a description of the momentum, you've got this half term, which is related to the uncertainty principle. So you cannot have 0 electromagnetic field. It will have a constant fluctuation. It may be 0, but it will have a variance. Sorry, I got it wrong there. It will have a variance, but it can be 0. So it means it's oscillating about the 0 point with this 0 point energy. It's also in the momentum operator. Right. So 0 point energy, it's a joke, right? It's just a mathematical artifact, can't be real. Yeah. When you do a calculation to work out just how big it is, it's enormous. I think, I can't remember, and it's some quote, I think it was from Pudov, saying that in 1 cubic centimeter, there's enough 0 point energy there to body world's oceans. It's got to be a nonsense, right? Why doesn't it gravitate? That amount of energy, why wouldn't it gravitate? Well, you might say that it's isotropic, so there's no net pull in any direction. Maybe it's related to the cosmological constant, but that's tiny. Right? Now, regarding the Feynman disk experiment, in their paper, they said it's remarkable when they're describing this flow of energy in that scenario. I'll just go back a few slides. When they were describing this ethereal flow of energy, because you have to have this angular conservation of angular momentum, so the mechanical aspects will start to rotate, and it's something ethereal rotating that you can't see. Graham and Hos, they wrote, it's remarkable that no known particle can be identified as the agent of the observed electromagnetic angular momentum in the exchange with the mechanical detector. However, this does not imply that a new entity has to be introduced. It's already contained in the Maxwell classical equations. So they're saying the non-plus, you can't invent some new particle, to describe this. But there's something there. Now, I had a chat with Graham. He's very, very old. He's in his 90s now. And unfortunately, Hos died over a decade ago. He was intrigued because I put it to him that this thing he was looking for might be this 0 point motion. It's there in the mathematical description of it. So if you have this E cross B device, why not just make a linear device? You just have some arrangement of fields set up. So with your right-hand rule, you've got your electromagnetic momentum being expelled out the back, and somehow mechanical aspects go off in the other way. Should be easy to do, right? I believe the reason why you can't do that is that if you see this expression for the momentum, it's a two-sided transform. You have to sum over positive and negative frequencies. What this is saying is that when you set your fields up, you have to have a flow of electromagnetic energy come in to set these fields up. And you're summing over positive and negative wave numbers. So you're going to find that the 0 point term cancels. So you're going to find that a simple linear device won't work. Now, there's another explanation, and I've taken this diagram from one of Hal Pudov's papers. It's called hidden momentum. You can go to Kirk T. McDonald's website on Princeton, and you'll find he does a very scholarly description of it. Also in my papers, in the references, you'll find lots of descriptions of this. But the easiest one that I can think of is Hal Pudov's description. You've got a current loop. So this is an E cross B device. You've got a current loop, and you've got an E field going down, electrical field going down, and you've got the magnetic field coming out of the paper, and you've got the pointing vector pointing to the right here. So that should just go to the left, right? Well, it turns out there's an effect called hidden momentum, and it does sound like a fix. It does sound like one of these sort of just so stories, but there's very scholarly descriptions of it. But the simplest description Hal Pudov says is that because you have this potential, the potential energy of the fluid carriers, of the electrical fluid carriers, is increasing. So they're gaining mass. You know, E equals mc squared. They're gaining mass, and because of that, the momentum just happens to cancel the momentum from the pointing vector. So I believe, because of this, primarily because of the idea that you're cancelling, because you're adding wave vectors from both ends of the number line, that just static E cross B devices, which are just linear, are not going to work. But that's just me saying that the hidden momentum argument is the standard answer to this. Just loading up the next slide. So if we can't just generate linear momentum, maybe we can use something that we know works from the Grain and Lahoz experiment. Maybe we can use something which generates angular momentum and work out a way of turning that into linear momentum. Let's just take a look at why the angular momentum device, the Feynman disk, works. It's a static electrical and magnetic field. It literally will turn just from static fields. Now, the hidden momentum argument doesn't work here, because if you look at the E field from the electrical field, I keep calling it E field, if you look at the electrical field from all these spheres, it's uniform. It's uniform across the coil. So there's no hidden momentum argument because they're all at the same potential, right? Now, if you use my argument about the momentum, when you look at it in the quantized sense, what I'm saying is that because it wraps round, because your path of integration would be a loop. There's no beginning or end. It's not like the linear device where you have, when you do the Fourier transform, you know, effectively you have a source at plus infinity and a source at minus infinity, and you're describing waves coming from both directions to build up your waveform. With this case, because it's a circular path, it's a one-sided transform. And it so turns out that when you do a one-sided transform, the half sticks around. It's telling you something. It's telling you that you can utilize this zero-point energy. So how could we build a net propulsor from this? Something which gives you a net effect. This is what will happen if you turn on the magnet. What happens, you'll get a transient electrical field circulating around the solenoid, the magnet, which acts upon the radial balls. And when you turn it off, you get a transient circular electrical field acting in the opposite direction. So the thing can only translate, really. Yes? Turn the field on, it will spin around a bit, turn it off, and it will come to a short again. Come and stop turning again. It's a small effect as well. You'd really want to have it in a cyclical manner, where you can have lots of this happening per second, and it all builds up into one great big shove or torque. Now, also what I believe here, now Pudov did a proof for the linear case, which I didn't include. I took a slide out at the last minute, thinking it would just confuse the issue. He had a basic argument where, for the linear case, where he's saying you're integrating this E cross B term over a cycle, and because the start of the cycle is the same, the integration limits are the same as just before the start of the cycle, the end of the cycle, going on to the start of the cycle, you have two terms cancelling. And he was quite unequivocal, where he thought there's no means at all of cycling the fields. This is an alternative proof he gave to me of generating net thrust. That was the linear case. It might be different here. I left the slide out. I took it out at the last minute. But the difference here is this radial term. That P there, that's a momentum, the linear momentum of the Poynting vector. That would contain your E cross B term. The R term here is the savior to this arrangement, because you can say that you're taking the radius of your effect, you're taking it to 0 at the end of the cycle, so you can get net effect. Now, this is what I propose. This is the electrical dual of the Feynman disks. So you're just reversing everything round. So when you have electrets and magnets, you turn it round so you have magnets and electrets. Now, the reason why I would prefer this arrangement, because usually when you work with magnetic fields, it's usually a lot more force. Yep. Now, what I propose here is a system of these L-shaped devices, which are ferromagnetic material. Yes. Now, they're shaped in this way. So why shape them in this way? Well, so it turns out that if you're going to have an electrical field going down through the page, and you've got your magnetic field going radially, you're going to find that your Poynting vector is circulating radially, not radially, actually, around the axis. And we know that the effects occurs with these pole pieces here, that the fields generated from the change in, when you switch the, in this case, the capacitors, it will be the capacitor, I'll come on to that, it's going to push, excuse me, it's going to push against these outer pole pieces. So that's a plan view. I've got a cutaway diagram here showing that on top and on bottom, you've got the capacitor disk. And in between these pieces, you've got high permeability material to help you with your electrical field. Now, the pole pieces themselves are magnetized and can be cycled. And your cycling is going to be the reverse. What you do here, electrical then magnetic field, you switch on the electrical field and you switch on the magnetic field. With the electrical dual, the magnetic field on first and the electrical field off. Now, I believe that what's going to happen if you cycle in this manner, that disk is going to spin up and keep spinning up. Yes? So the question then is, if you can make something which generates net angular momentum without pushing against anything apart from the field itself, how can you turn that into linear momentum? Well, I believe it might be something like this. It's a bit like a conveyor belt, a belt conveyor belt. You've got rotating rollers, and they're able to send the belt forward. So what I suggest we do is that we put these angular momentum generating devices onto a plate. That's just a label. It doesn't mean any kind of device. It's a rectangular box with plate on it. It's just a label. But you put the devices onto a plate. Obviously, they're going to put the plate in some kind of tension, but the forces resolve. When you work the forces out, it resolves that you get a linear thrust. So I believe that might be possible. And when you put the numbers in, you're going to get forces of the order of this equation. So you could make a microwave cavity out of these devices rather than sort of discrete components, as you saw on this slide or even this slide. So let's just say that somehow we find this. So instead of having bulk inductors and bulk capacitors, it's some kind of microwave cavity. Let's just argue that the field is about 1 Tesla. The electric field is about 30,000 volts per meter, and you're cycling at, say, 10 gigahertz. It would turn out that you could get something like 2.6 tons from a volume of a meter cube. If this is correct, if it's correct, and let's say go up to optical frequencies, and you can see the numbers there. Well, fantastical numbers. You know, you're talking more than the thrust of a Saturn V rocket. But if it's true, that's a lot of engineering there. That's the kind of promise that this technique might have. So to dot the I's and cross the T's when one's talking to one's colleagues, you know, academic colleagues, they say, oh, we can see all that, it looks nice, but where's your momentum going? Yeah, you're somehow dumping momentum. I just don't believe it. So I have to set up a model to somehow explain how this might be possible. And this is what I'm working on at the moment. It would be better to work on some of the experimental aspects. I'll get onto that. I'll get onto that in due course, but I want to look at the theory first to make sure I'm not wasting my time. So what I'm trying to do is look at the field and describe it as an ensemble of oscillators. Yes, and they've got this 0 point term. So there's mass energy in the field, right? So by analogy, if you take a hydrogen atom, the electron around the nucleus is in simple harmonic motion, a version of simple harmonic motion. It has a 0 point energy too, and you can move a hydrogen atom about, you can translate it in space. So I'm saying by the same token, these modes that make up the electromagnetic field, they have a 0 point term, why can't you set that in motion? So when you press against the field, you're effectively, even though it has a very huge mass, you can move those electromagnetic modes that describe the field. Now, by analogy again, so you've got a collection of hydrogen atoms. They're going to experience what they call London forces, van der Waals forces between them from momentary fluctuations in the electron crowd around them. So they're linked together. Yes, they interact. So I'm saying by the same token, maybe it's possible that all the modes of the electromagnetic field can interact by this 0 point fluctuation. So if you take a single mode, as it's fluctuating, and remember it has a variance, as it fluctuates on the individual mode, as the electrical field fluctuates, it's going to temporarily look like a dipole. It's going to go plus and minus, and it will switch around and do that randomly. All the other modes are doing just the same thing, and you'll have an effective field around your mode. So what I'm trying to say is that the field, the electromagnetic field, even though it's ethereal, it's beginning to look a bit like a supersolid, a superfluid or a supersolid. It's like a lattice, yes? And the reason why I put the appendage super on the front, because it just simply flows through us with no friction, yes? Although some will say it's a source of inertia, but it's not like a normal fluid, yeah, where you suffer viscosity effects and so forth. So I'm working on the paper at the moment. This is all very highfalutin stuff and probably won't even be regarded. But I believe that you can describe it almost with mechanical effects. So you can predict a heat capacity for it. You can predict the speed of sound for it, which would be the speed of light. Even longitudinal waves. You can describe second sound in it. And most importantly, dissipation. So someone wants to know, okay, I can see your device, purportedly you say you're pressing against the 0 point of the field. Show me how that's a dissipative effect. So I'm able to show how momentum can go to the field and become thermalized, randomized, yes? And then that would complete the proof that you're pressing against something with substance. How are we doing for time? I'm just going to take a quick time check. 45 minutes. Okay. I'm going to move on to other projects of mine and other people which might be pertinent to UFOs or UAPs as they're calling today. Can't spend too much time on them because they're really other presentations in themselves. Now I'm working on an entanglement communication system using quantum entanglements. And the reason why that's interesting, apart from sending information, nothing which is massive. Information has no mass energy, but you can send information faster than light for that reason. It breaks the space-time construct. You know, we're looking at new propulsion devices. Maybe we need to be looking at ways around relativity theory. And got another project to do with thermoconversion, which is greater than Carnot efficiency. And there are counts from people who have been contactees saying that these UFOs, they run cold. They've got a much more sophisticated way of energy conversion than we do have. So it's kind of relevant to today's talk. Let's have a quick look at the entanglement communications project. In the middle here, or near enough the middle, you have a source that generates two photons, and they're what we call entangled. They're correlated. Yes, they share a joint wave function. So if you measure one, it's going to affect the wave function of the other. They have statistical correlation. Send one off in one direction to the left, send off the other to the right, and you have an interferometer setup. Now, what you can do when you measure on the left-hand side, you collapse the wave function from being coherent, from being a pure state into a mixed state. And the right-hand side, excuse me, will pick up this change. If you have a pure state, you'll get interference. If you have a mixed state, you won't get interference, and the detector can pick this up. Now, I've been around the block with many academics with this, and I'm not feathering my own cap, but the best ones have said things like, of course it's possible, of course it's correct, but they don't stand by you. I've got to do the experiments at some point. I think I told you what happened to me a few weeks ago with some university which is meant to do the experiment for us. They just ran off with the money. That was very nice of them. What it comes down to, though, is this idea of the evolution of a joint wave function. Now, on both sides, free space and the interferometer, they're what they call unitary operations. They don't affect the wave function at all, apart from add on a phase. Yes? And the phase is just the essence to say that time has flowed, time has ticked on. You've got a phase on, just like a wave. When you send a wave, when you measure it later, it will have a different phase. So that's all unitary operations do. Yes, they don't affect the wave function. They just add on a phase. Now, what I'm trying to say to these people who cite to me and say the no communications theorem, and saying, well, if by solely regarding, even just thinking about one system of a joint system, I have to take the partial trace, and so take it from being a pure system into a mixed system, well, entanglement wouldn't even exist. This part here, where it's traveling in free space, am I meant to take the partial trace here? You wouldn't have entanglement. if you have a unitary operation, which is this interferometer, up to the point where the detector measures, this is not doing anything to the wave function. I do not have to take the partial trace through the interferometer. Some of them are getting this. Now, as regards the entanglement signaling, what's the speed of it? Well, as far as we know, Alan Aspect did an experiment in 1980. No, sorry, Zebenden did a recent experiment in 2008 where he measured the speed of wave function collapse as at least 10,000 times the speed of light. So this is not to say that he sent any information. What he did was showed after the fact correlations. So you've got the system I discussed earlier with the two photons in what they call HV polarization, horizontal and vertical polarization. When the system's not measured, it has an indeterminate angular momentum. Polarization equates to angular momentum. When you measure it, it goes into a very definite state, such that the sum is always the same as the original angular momentum of the system. So if you measure horizontal on the left-hand side, you'll measure vertical polarization on the other side, and vice versa, vertical on one, horizontal on the other. Now, if you imagine a ticker tape running as you're measuring the outcomes of your measurement, it always lines up. Horizontal, vertical, vertical, horizontal. And this experiment was done to over 10 standard deviations, yes, to show that it's always true. And it just comes down to conservation of probability. Right? So we know that at least after you've done the experiment, when you look at the ticker tape of the outcome of the experiment, over space-like separations, everything matches up. And to do that, some effect is passing between the stations at the end of the experiment, but it's going at least 10,000 times the speed of light. So to me, this is just a smoking gun. This is just saying relativity is flawed, and your way of getting around it, trying to save relativity, the no communications theorem, is wrong. You take the partial trace after joint evolution, not before. Okay, I'm not quite sure how well I'm getting that across, because it is really, it's a whole presentation in its own right. Now, this is what I came up with to explain how the space-time narrative breaks down. You know the usual space-time diagram, and it's a hyperbolic, what they call hyperbolic motion. Yes, the Lorentz transform. Your axis of the moving system deviate from the right angle. So you get a new, when you look at events of a moving system, the prime system, the axes aren't at 90 degrees. And when you project onto these axes, one of the things you find is that there's no simultaneity. Yes, simultaneity. Right, that's one of the features of relativity. You can't say events are the same in all systems. You can't say there's any synchrony between events. But if you look at the faster than light system, it appears that you can do this. And the way to do that is to change the transform. You drop out all of these retarded time terms. So here's a relativistic transformation between frames. And these terms are purely the time it takes for a light speed signal to go from one point to the other. If you're sending information faster than the speed of light, you knock them out. And they're your new axes. So you preserve simultaneity. Okay, let's move on to the other project, and that's to do with thermoconversion. It's another controversial one, but I have to say, Professor Daniel Sheehan, he's a really good chap. Stands by people working in this field, yes, and he publishes in the top journals, yes. So he's given the whole area credibility. You don't tend to get laughed out of the room anymore. Now, he uses the term Maxwell zombies. We know about Maxwell demons, the idea that once you have a system which is at constant temperature, heat energy is just a random distribution of the energies, of the kinetic energies, of the potential energies, and so forth. So because it's uniform everywhere, you can't run a heat engine in it, because normally heat engines would run via gradient. If you had a Maxwell demon, this hypothetical little being, which is able to sort this random distribution, so you could sort your hot molecules onto the left, say, and your cold molecules onto the right, you could run a heat engine. And then people will laugh at that and say, well, it's perpetual motion. Yes, they're very simple thinkers. They haven't really thought about it. There's no perpetual motion apart from microscopic perpetual motion. If you could build a Maxwell demon, it would fall to pieces someday. It would run down. It's not perpetual motion. It's heat reuse. It's heat reuse. That's what it is. So the idea that this demon has to be intelligent, the Maxwell demon, is not true. Sheehan calls them Maxwell zombies because they're just autonomous processes. There's no fault involved. It's just simply processing information. Here's a hot molecule, put it that way. There's a cold molecule, put it that way. So what I've looked for in my research is on this, and where these ideas come together, is that I'm working with phase changes. So first order and second order phase changes. First order phase changes are things like evaporation or melting. Yes. So you have your Maxwell-Boltzmann distribution, and you can draw a line at the top end of the distribution saying that any moieties with energy greater than that will phase change, will convert from water to liquid. It's a sorting process. It's a Maxwell demon or Maxwell zombie process. It's also the same with second order. Second order phase transitions are gradual phase transitions. Things like magnetizing a magnet. The lining spins up gradually. Yeah, they're called second order phase transitions. You can find all this stuff on the website. But I came up with two scenarios. I did research in this, ran out of money. I was working on the ferrofluid system. It so turned out. Lovely chap, great chap, Professor Grady. He wanted $500,000 for research, so I kind of I was only left to doing simulations. Let's take a look at the first order system. Yeah, I'll tell you what this is. This is a column with a reverse osmosis membrane at the bottom, and you've got a hygroscopic liquid, and around it you've got an atmosphere of water vapor, just water vapor. Keep it simple. The water vapor will condense at the top, and it will build up a head of pressure, so at the bottom pure water flows through the reverse osmosis membrane. And of course, when it flows, it's got potential energy. It can run a device. Excuse me. So it's not practical, but it's a kind of what would you call it? A paradox. A paradox. Well, I worked on the second order system because it is more amenable to engineering, and I worked on the system where you were dealing with ferrofluid and you had a magnetization demagnetization cycle, which is a little bit too technical to go into here. It'd take too much time, but you could convert heat energy directly into electricity. Yes, and not just do it at high efficiency. You could have a closed isolated system where it would just go round and round. So you convert your heat energy into useful energy, let that useful energy degrade back to heat again. It would just go round and round and round until the device failed. And it's not perpetual motion because the device does fail in the end. It does wear out in the end. But people who don't want to push the boundaries of research forward, who can't follow a logical argument, or maybe they're just scared or have cognitive dissonance, they don't look at these things. But we don't care about them. But there's an awful lot of them in the university system at the moment. A lot of them are scared to do original research, so it's left to people like us with our resources and with our spare time to look into these things. So, Tim, that brings to the end my presentation. I hope it was coherent enough. Okay.
Absolutely. Remi, thank you. But let me do this. The first thing I want to do is I'm going to stop your screen share, and I want to put this on gallery view. And everyone, please give Remi Cornwall an enormous hand for a remarkable presentation. Sir, thank you so much. You ran through an enormous number of ideas and projects there. So it's tough to know even where to begin, but I should mention that your website, you mentioned that a couple of times, it's evosci.org. And let me see, we did have a number of questions. Who wants to put their hand up to go first? Let me see. And I had the one that jumped out was Michael Boyd was asking if a black hole would be a Maxwell's demon. Michael, do you have questions? Oh, and I guess it would help if I allowed people to unmute themselves. There we go.
There you go.
Sorry about that, sir. Go for it.
Michael. Hello, Michael.
Hey.
How you doing?
So let me, I made some chat stuff here. Let me see, I had a couple questions here.
Oh, that's cool.
Yeah, but again, that was a remarkable presentation, Remi. Thank you.
Oh, thank you very much, Tim. I was honored to give it. And I hope something comes out of this little team we have here.
Okay, here's the question. Okay, you were showing this entanglement experiment using two entangled photons. And my question is, wouldn't the entanglement take place at the electrons that produce the two entangled photons?
Yes. I mean, what entanglement is, I mean, many people, they come to me and ask me what entanglement is and say, oh, you've got an electron spin here, and when you measure it, the spin on the other one, it has some kind of force that goes across and spins it down. Not that. What entanglement is, it's correlation. When you have a joint system, yeah, you can't split it apart with the tensor. You can't split the tensor product of the systems apart. It's not factorizable. So what generates entanglement is a conservation law. So if you have two particles and they're subject to the same process generating them, and say it's energy, they will be correlated. I'll give an example of this. Spontaneous down conversion, where you direct a laser at a crystal and you get two beams coming out at half the frequency. Well, they're correlated because it's energy conservation. You have other forms. You have conservation by momentum, either linear or angular. So yes, the system that generates it would be entangled. And if I remember, every atom in your body and shells around me, the electrons around each nucleus are correlated, they're entangled. Yeah.
So my experience with the entanglement goes back into the 80s with what are called tunnel diodes that they use for, and they use this for making infrared detectors. It's a type of junction called a Schottky junction. And so what happens is you get this diode cold enough, and it creates what I guess would be best called a standing wave. You know what I mean by a standing wave?
Yeah, they're amplifying devices, aren't they? They're used at microwave frequencies, tunnel diodes. I think it's metal.
Yeah, well, in this case, it's just it's an electro-optic device. And so the point is it would produce a photon on both sides, but they'd be the opposite spin, because it's like a standing wave, one going like, a sine wave, and what's in the middle is the barrier. And the barrier is what you call an event horizon. It's a type of event horizon. So in electromagnetic, in the semiconductor, it's basically the barrier is what the junction is. So that led to my other question, which is, about Maxwell's demons. So essentially, a tunnel diode is a type of Maxwell's demon. Would you agree?
I've come across this type of thing before. Where are you talking about rectifier demons? Rectifier demons?
Well, a tunnel diode is a type of rectifier. Yeah. Yes.
Yeah. I wasn't too convinced because I think what might prevent them working is the fluctuation dissipation theorem, where if you get a fluctuation, it's automatically matched by the dissipation, and there's no net gain. So if you take something like Johnson noise from a resistor, yes, you'll get a voltage across the resistor, which is generated by the thermal processes, but you can't draw any power from that, even if you rectify it, because the power generated is just sufficient for the dissipation, hence the
Well, you can't really see this because of the thermal noise, unless it's very cold. This is like below 50 Kelvin is where this is occurring. So basically, the way you take care of the thermal noise is by cooling it down. Okay, but the point I'm trying to make, and then you were talking a little bit about cold, this thing being cold, like the UAP being a cold energy source. So another example, what I was asking is a black hole. Black hole is basically, we don't know what the temperature of a black hole is, for example. Could be cold. If black holes, let's assume for the sake of argument, there really are black holes, because that's obviously controversial. But if there are black holes, wouldn't that be an example of a Maxwell's demon?
Okay, let me think about that for a bit. But just on your point about temperature of black holes, you have black hole thermodynamics, and the entropy of a black hole is set by its surface area, isn't it? And the temperature. So they do have a temperature as such. Now, what I do understand about these event horizons around a black hole, I think they call this the black hole no hair theorem, where all information is lost. I think the only things that can emerge from the black hole are charge. Oh, I can't remember the other ones, where the information isn't lost. So if you sent a bunch of charged matter at a black hole, it would take on the charge of what you've thrown at it. How would it be a Maxwell's demon? Are you suggesting that somehow the black hole can sort information and spit out higher grade energy? Maybe are you talking about pair production, something like that?
More like a jet. I'm thinking of the black hole as a place where all the energy basically is in sync with each other, where all the protons are singing and dancing to the same tune. Okay, and then a jet is where there's a release of energy and matter, and basically it's a loop. You have an inner and an outer event horizon. At the outer edge, matter, everything becomes energy. There is no matter. All matter is unstable. It's like radioactive materials that are like uranium and plutonium. If we got close to the black hole's event horizon after the jet was emitted, that stuff is all that matter is stable over there. It's not radioactive. It's stable. But when you get over to the outer edge of the event horizon, then it's all unstable, and all you have left is energy. And that's the void. And that's what we call the so-called vacuum energy, okay, is emptiness as opposed to matter energy.
Yeah.
Okay. Let me just say, regarding black holes, they can have several event horizons. If it's rotating, it will have a different event horizon. I think that's called the ergosphere. Yes. Mm-hmm. As regards to what event horizons are, the generally accepted one is the idea that it's a path of no return. You cross it, you're not coming back. Yes. Where you lose information about what's happening on the other side.
Dynamically, I would say that's true. But if you treat it as like a diode junction, then that's not true. It's just a virtual thing. You can't see past the horizon. That's all.
Well, and I should let me jump in real quick because Mark has had his hand up for a while.
Okay, so let me let you go. Thank you for your answer.
Thanks, Michael.
Okay, okay. Where are you, Michael? Michael Ball.
I'm right here.
Hi, Mike. Yeah.
Oh, okay. So I was just listening in on your bit about the Maxwell's demon. I heard from Jeremiah a while back that there's a device that was able to remove very small amounts of energy using a 2-diode system. Basically, if you look at heat, it's just movement back and forth, and if you can separate, movement in one direction and sort of force electrons in one direction, you would end up with an electrical potential that you can eventually take out. Problem is, of course, the high frequencies involved in Brownian motion or heat. So by using 2 diodes, they were able to get a very small potential out of like a hot sample, meaning direct heat to energy conversion. Have you heard of this? Looked into it?
I haven't heard of that one, but as I said, I did mention I have some reservations about the idea of diode rectifiers. I mean, that's just coming from me, but as I say, I believe the thing which limits them is the fluctuation dissipation theorem. What you generate, what you gain on the swings, you lose on the roundabout.
Sorry, if I could jump in really quick, Remi, I can speak to that briefly. I just pasted an article about that into chat, and this came out last year. Actually, it was listed in Science Daily, so I guess it's credible. My understanding of the article, I could be mistaken, was that there was proof in the 1950s that you basically couldn't convert Brownian motion using a rectifier, right? Maxwell's demon using a rectifier in a circuit. And that proof was considered to be like inviolable, right? There was no way around it. It was a theoretical proof. But apparently there was a loophole where the proof only involved one rectifier diode. And so the Science Daily article was saying that when you use 2 rectifier diodes in a circuit, there is a way around that. And that was what was demonstrated, I think, in September. I think it was around September 2020.
I'll have a look at this. I'll have a look at this. I may have read this some point last year, but I'll have another look. Always willing to have my ideas changed. That's what it's all about, isn't it?
It's interesting. And then just today, and I don't have a link for this yet, I could probably dig it up. Remi, I thought this one might interest you. You were talking about entanglement. I guess there was a new demonstration just hit the news. They were saying that physicists have been able to measure an entangled photon without destroying it. It was non-destructive measurement of an entangled photon.
Yes, that's known about. That's weak measurements and so forth. Yeah, that's known about. But if you want to pass that one on to me too, that would be great.
Let me find that one. And so I'm sorry, Mark, did you have anything more, sir?
Oh, I was just going to say that although there was minuscule amounts of power that was being generated, if anyone will take on the mantle of making, bringing the efficiency level of that up, we'd be able to eventually turn on the air conditioners in the summer and create electricity versus, sucking electricity out of the. Yeah, and that would really solve the world's energy problem. Imagine just cooling off the oceans in order to create the energy we need during the winter and whatnot.
The biggest problem, we're all wonderful people, but the biggest problem is the peer review system. It's really bad right now. I mean, Julian Swinger was saying 6 decades ago how he hated the system, how someone could review his papers, and you could not know who they were and have a face-to-face with them. And he also
that's what we started APEC for. This is peer review. This is live peer review. I can pull out a contraption, and just like happened 2 weeks ago, Brian Sinclair pulled out his contraption and said, "Anyone, come at me right now. This is your chance." This is peer review. This is modern peer review.
We need more people like us because it's just too comfortable. The situation in the universities and things like full economic costing, where they've just handed it over to the bean counters. We need more people who stand up for their ideas, even though they are left field ideas. Yeah, and you'll just find many salary men. And unfortunately, industry and government funding are just enthralled to university. And we should really be living in an age like the Belle Epoque. If you look at the end of the 19th and start of the 20th century, so many inventions funded
the
by
Mansfield Amendment.
gentlemen scientists. Yeah.
The Mansfield Amendment is really the cause for that. In 1972, I think it was, they passed a bill basically stating that anything that goes against the norm cannot be funded through regular channels. So government agencies and even universities wouldn't touch any of this stuff with a 10-foot pole because it risks getting them defunded, and that's how they kept it secret.
We're our own, as a species, we're our own worst enemy as a species. We should be 100+ years on. For the rapid developments at the start of the 20th century, you should be much further along. Yeah. But I don't fight the system anymore. I don't bother with them. I look up with people like yourselves, and we can have our own.
We're not fighting the system. We're just creating a new system.
Yeah, indeed.
So let me see who else has questions. There was Mark. Jeremy Reese. He was asking about scale when separating heat. Jeremy, and Jeremy's on YouTube also. I should see if he has any.
Hello, Jeremy. You've got your microphone off.
You're still muted, Jeremy.
Hey.
Hello, Jeremy. How you doing?
Yeah, I was asking my audience if they had any questions for you, and everyone, if you have a question for him, you can shout out live. Just put it all in caps. But he was asking about what scale you were talking about with your heat dissipation thing. This was a question from someone else.
I'm an engineer by background, and I wanted to develop a system which would rival power stations. You'd have to look at the papers. I was talking masses of power generation. I was talking megawatts per meter cubed. So if you had a heat exchanger, imagine you had a huge tube like at a power station with all that enthalpy flowing into the conversion device. I was looking at figures of megawatts and more. Yeah, where's a will, there's a way. As I said, I got to the point where the cost of developing ferrofluid, lovely guy, liquids research, and Kevin O'Grady, really, really splendid chap, and Vijay Patel, who works there, really splendid people. But that's the cost of doing research. You try to use the system, try to use a peer review system and publication to put accolades on your research, but there comes a point where you realise it's not set up. I mean, we have these stupid windmills in the Thames estuary. It's pathetic. It's a bloody windmill, and there's hundreds of them. We'll do better than that. There's a will, there's a way. But anyway, that's my answer. We're talking about megawatts per meter cubed power conversion rates once we have the system up and running with the correct ferrofluid. Yep. Right.
Yeah, I don't have any other questions. I'm trying to find like some of these are just off topic and not appropriate, so I'm not going to ask them.
Could you drop your YouTube channel here so I might see what's going on? I'm not aware of the questions.
Oh,
yeah.
I just looked as well. You might get feedback because it's live streaming, right? So that would be an issue. But
I see.
Yeah, it's youtube.com/alien scientist. Looks like we've got about 150 people. And let me just shout out to everybody who's on Jeremy's channel.
Here's the video link right there, and I just dropped it in the live chat. So you can go there.
Alien system, was it? Alien, I can't remember what the
alien scientist. Yep, he just dropped it in there.
Excellent.
Yeah, and my only worry would be feedback because the YouTube is streaming, but it's actually a few seconds behind, I've noticed. So let me, if it's okay, let me go back to Michael. He's raising his hand again. Sir?
Hi, Michael.
Hey, so I'm curious, you had that little device that had the, that you were spinning and it had the little like L-shaped spokes on it.
Let's find the slide. I'll put it on screen again in a second. Where are we now? Bear with me, Michael. Just finding the slide.
Take your time.
And I'll put it on the screen.
Let me know if I can help you at all with that.
You'll be right. I think I just got to share the screen now. Share the screen. Screen. This one. Are you seeing what I'm seeing at all?
Yeah.
Yeah. This slide.
Oh, it's not, your screen share isn't up.
What's happening now?
Oh, it doesn't actually. It doesn't look like it's shared.
I know. It's all right. I know what I've done wrong.
There we go.
Right.
Now you got to open up.
There we go. There we go. Can you see?
Yep.
Yeah, there you go. You got it.
Okay. Right, Michael. What was your?
Let's see here. Now these metal L-shaped things, those are like the spokes of the, and this is on a disc and it's turning, right? And
Yes.
and then in between there's a on the right there, you're showing a cross-sectional view of the metal disc that's above it.
Yeah, it's a cutaway diagram. I would have been better to sort of chamfer the edges to make it look
Well,
like
no, that's fine. So now the little the whitish area, white with the blue stripes in it, that on that image, that's the dielectric.
Yes, the cross-hatched area, the hashed area would be the high permeability material.
So now my question is the charge, the stored charge, not the mobile charge, but the stored charge. Where is that? Do you consider that in the metal or in the dielectric?
Maybe I didn't quite get the point across. If I go to the previous slide, this is the electrical dual of this system. So this system, you've got the electrets, the charged spheres, and in the middle you've got the solenoid. So you've got the magnetic.
The disc is made of what material?
Well, this could just be made of an insulator, something robust.
So the disc is an insulator, so say a piece of glass or something.
Yeah, well,
and then you've got charge centers, basically, right?
Yeah.
And so the question then is, so in this case, is the stored charge in the little dots, or is it in the disk itself?
Now, the way Feynman set this up, he had to say the stored charges are in the little disks, so they could be something like wax.
So they're in the little dots, you're saying?
Yeah.
Not in the disk. Okay.
Not in the disk. Yeah.
Okay. So now back to the other slide.
Mm-hmm.
Now, in this case, though, you don't have those dots. You have these L's, right?
Yeah, it's the electrical dual.
And then the disk is the dielectric again, correct?
Yeah, it's different this time. It's not.
So again, the same question is the stored charge. I'm not talking about the mobile charge. I'm talking about the stored charge. Is it in the metal or is it in the dielectric?
No. I'll run it by you again. This is the exact electrical dual of this system. So magnet here, electric here. Go to this system. You have your capacitor on top. So that's the electrical system and the magnetic system around the edges. So it's the reverse. It's the flip of the reverse. May confusing the issue by showing.
So you're saying the disc on the right, which we're seeing half of, that's made of that's the dielectric. That's not the.
Yeah, maybe I'm confusing the issue.
Well, basically the question is,
let him finish answering, Michael.
Yeah.
Okay. If you took the dielectric, if you could remove the dielectric, would it stop?
Yeah. No, it works fine. Maybe I'm confusing the issue. I was thinking ahead. Let's forget the grey bit in the middle. I added that on to boost the electrical field from the capacitor on top. But if it's confusing you, imagine it's not there. Just imagine it's white space. So it'll be the complete electrical dual of this system. So you're just reversing. Where you've got charges here, you've got a magnetic system where you've got a solenoid here, that would be the capacitor on top. It's the flip side. It's the electrical dual of that system, which I believe would be easier for me to make. Yes, forget this. If it's confusing you, forget the half-tone area. Forget this. Yeah. So it's just a simple flip side, electrical dual. Does that make any sense to you? Imagine, I'll try again. Imagine this part here.
So imagine that. So you're saying, imagine that the hatched area, the whitish hatched area, wasn't there. Is that what you're saying?
If it's easier for you.
Okay.
I was just thinking ahead.
So yeah, that's fine. But then the metal plate on the top, that's still a dielectric, though, right?
No, a dielectric. It's an equipotential surface. It's a capacitor plate.
Okay.
It's literally
so there's two pieces of metal. So there's two pieces of metal with a dielectric between them of something. What is the dielectric between them?
You could just use air.
Okay, air is dielectric.
It's just a plate.
Again, I could use air. I could use air to ask the question. So
Michael, slow down a little bit. You got to let him answer, because I think you're over.
Two metal plates with air in between it.
Mm-hmm.
Where is the charge being stored? In the metal or in the dielectric? In the.
Well, when you say charge,
the charge.
You've got a magnetic charge, so you magnetize these strips, as in this diagram down here.
Right.
And you've got electrical charge, which is the field is perpendicular. So this is a plan diagram. So the field would be going down, the electrical field would be going down into the paper. It's just a plate capacitor sitting on top. This is a plan view of the device. Cutaway diagram here showing the plate on the top. So it's like a sandwich. It's like a sandwich, yes? Do you use that term? American term, sandwich? I always thought it was a sort of pretty expression.
But the meat's the dielectric, correct? And the bread is the metal.
No, both. Forget the dielectric for a bit. Forget the dielectric. Just consider the pole pieces. Yes. I'll just run you through some a little bit of EM theory. Imagine you've got a plate capacitor. When you charge it up, ignoring the fringing effects, the field comes straight down. It's perpendicular to the plate. The electrical field comes straight down. When you cycle the voltage on the capacitor, the magnetic field will circulate around, be circumferential around the axis of the disk. Yes, that's how it will come out via the Maxwell equations. What we're saying here is that when you're changing the voltage on this capacitor, the magnetic field will react against these magnetized segments here and make the disk rotate. It's the electrical dual. If you look at this system here, when you change the current in the solenoid, when you switch it on, you'll get a magnetic field coming straight up axially. So along the axis, there will be the magnetic field. When you change the current, you get a circulating electrical field. So when you switch it on, it will act one way. You switch it off, it will act the other way. It's this electric field which is reacting against these balls, these electric balls around the outside, making the disk rotate. And the spooky thing is, if it's just suspended in space, if it's in free fall, it will start to rotate without pushing against anything, apparently. That's the mystery of the Feynman disk. Yeah. So you could have the thing in free fall and have this thing switch on, and it will start to translate. When you switch the current off, it will stop rotating. What I'm trying to do is to try and make that a cyclical process where you don't have this start-stop, where you can just build up this very small effect and build it up so that when you switch off, you don't get the electric field. I've got here, one and two, cases 1 and 2. Switch on, you'll get the electrical field in one direction from the solenoid. Switch off, it will act in the other direction. If you can get rid of that, the disc will just keep spinning up, getting more and more torque, more and more angular momentum. Yes?
So it's kind of like magnetic hysteresis is what it sounds like. You know what I'm talking about?
Not really. I can't see the connection. Magnetic hysteresis, when you've got a BH curve,
Right.
so H is your magnetizing field and B is your response of your material. When
Right.
you get hysteresis, initially it will start out linear in the linear region, then it will saturate. And when you take the field off, the hysteresis effect, if it retains its magnetization, and then you will get that. It'd be good if I had a sort of writing pad. I'll just 1 second. You might be able to get this on the camera.
Okay. Yeah, and then pretty soon I have more questions to take as well.
Okay,
so-
yeah. I appreciate you taking time to answer my questions. I don't want to monopolize it.
Okay, it's okay. Excuse the very bad drawing. I don't know if you can see it. Well, if I just scroll up and just see if I can find where. There we go. Is that coming through at all?
Yeah,
So
there we go.
Yeah, that's the kind of magnetic hysteresis effect. So it starts off linearly, and then when you take the field off, it's retaining some magnetization. It's coming back. It's a hysteresis effect. Yeah.
Yeah.
Excuse me. I think I've slightly got that wrong. Excuse me. I think that's I'm missing out on coercivity there, but I'll have to revise all that.
Well, Remi, if it's okay, I'd like to move along to Mark Fiorentino. He had a question.
Hello, Mark. Hello, Mark.
Hello. I'm also interested in the Feynman disk. It looks to me like it's an electric motor of sorts. I'm interested in the efficiency of this device. Do you have any idea how efficient it is as compared to an electric motor?
Well, I have to say that the effect, the Poynting field effect on a singular cycle is a very meager effect. And if you look at the magnitude of it, I find, here we go. It's this constant. Can you see? Am I
Yes.
still on the screen?
Yeah.
Yeah.
Permittivity.
Yeah. This is defining the momentum. If it's angular momentum, you just put a cross R in there. So you've got this very small constant, which is something down like 10 to the minus 11. I can't remember, 8.85 times 10 to the minus 12, something like that. So on a non-cyclical basis, so just a one-shot cycle, it's a very meager force. If you want to compare that to an electric motor where you've got the Lorentz force, or if you consider the force between magnetic poles, it's going to be minuscule. So this is why I'm trying to make it into a cyclical device where you can have this cycle going many, many times per second. Then it will add up and make a big force. Yes?
Yeah. Well, if it works and it gains momentum, then its efficiency will increase over time. True?
Efficiency. Normally when I think of efficiency, I'm thinking about energy and energy wastage and so forth. I think you're sort of talking about a figure of merit, aren't you? When you talk
the thing of you're putting some energy in through current, probably. I'm talking about the second Feynman disk, the one with the L-shaped devices, which looks a little bit like a metamaterial to me in some ways.
I haven't done the calculations, Mark. I'm at the stage of doing the theory just to make sure I'm not barking up the wrong tree.
I mean,
the only difference with
what you're saying is correct, eventually its efficiency would reach or exceed 100%, hopefully.
No, that's not.
If it doesn't, then
what I'm trying to say to you is it's not like an electric motor. So you've got a drill in your hand. You switch it on, you feel a jolt in your hand as it's pushing against you to spin up.
Right.
This thing would spin up in free fall. Yeah. Electric drill can't do that. It's not going to make a propulsion device for you in the vacuum of space. So that's the advantage to it. I'm not looking at this stage for efficiency, however you define it, by whether it's wasting energy whether you're getting bang for your buck from it, whether you put a
Yeah,
lot of point in.
I'm looking for it as a replacement or an energy generating device rather than for propulsion.
As far as I know, it wouldn't generate net excess of energy. I spent quite some time talking about the momentum and where it was being dumped to. I'm not trying to violate any sacrosanct laws of physics apart from the second one.
Conservation laws, right?
Yeah, because they're founded on very, very good principles to deal with, well, symmetry transforms in space. And what it comes down to on an intuitive level, if you're going to break the first law, you'd be changing the constants of nature. So, for instance, if you have a brick, you lift it up, and then a million years later, when that brick is still held up, if the gravitational constant has changed, then the brick was, when you drop it, you're going to get more energy out than you put in. Yeah, that's what it amounts to. Violating the first law would mean violating the constants. The constants would not be constant. Momentum, conservation of momentum, is to do with the homogeneity and the isotropy of space. So every direction you look in, it's the same. I give this example for conservation of momentum. Imagine you have an athletics track. Yes, on the one side is a conveyor belt. So when you're running around the track, you can take it easy on the leg with the conveyor belt, because that would be a violation of conservation of momentum. You're getting a free ride on one side, or if it's a headwind or something like that, or is it a tailwind pushing you along? Yes, that's what violation of conservation of momentum would look like. Yeah. When they look up into the night sky, they see that space is the same. I know they talked, I think about 15 years ago, they talked about this axis of evil in space. I think it's around the time of the Second Gulf War, which was quite funny, where there might be an effect where space is not isotropic, but at least locally we know that everywhere you look, up, down, left, right, back to front, space is the same. And that's the basis behind linear and angular momentum. Yeah. Does it help?
Yeah, I was just curious to see if this thing could be used for power generating. I'm interested in looking for new ideas for power generation.
Yeah, I keep an open mind once again, but I'd be very surprised if the first law wasn't broken. If it does get broken, I believe it will be something like somehow cohering zero-point energy, or some kind of what they call a fifth force. Yeah. It'd be something like that, but a lot of people tried. As Hal Puthoff and EarthTech said, they tried building these devices and they weren't able to rectify zero-point motion. I don't know, maybe they just weren't trying hard enough. I don't know.
Now,
bunch.
Remi, if I could ask a question quickly, one of the things you mentioned this kind of early on in your presentation, you talked about UAPs running cooled, and again, I've heard that in a number of these different experiments. But one thing I wondered, I don't have any firm thoughts on this. A few weeks back, Gary Stevenson suggested that UAPs might actually be upshifting infrared spectrum heat into the visible spectrum. And that was why it looks like, and again, I could be mistaken, but it looks like they are very dark on the IR scale of things, right? Like they appear just black against the outline of the planet. And then in the visible spectrum, they glow bright white. So his suggestion was they're still emitting IR, but for some reason it might be getting upshifted. Do you think that might be the case?
Well, they talk about gravimetric effects around these devices. Somehow they've found a way of warping the space-time around them. If you take gravitational redshift, if I were to launch a beam upwards, by the time it got to the top of the atmosphere, it would be slightly redshifted because it's doing work against the gravitational potential. Now, if you have a reverse curvature, it will get blue shifted. So maybe that's part and parcel of the way these things work, and it could be it. I mean, I think if you can, and if he's not too irascible, try and get Jack Safati on. I laid into him a bit a few months ago about his approximation, using the linear approximation where he should have been using full general relativity. Get Jack Sarfati on, give him a slot, yeah, if he's willing to do it, and let him argue his case. Yeah, I'd be more than willing to do that. And if I have some time, I would like to try his ideas in the full set of the general relativity equations and see if they hold water. Once again, it's a very tiny constant, which not just me, as several people were pointing out, that you're not going to warp space-time with small amounts of energy, but he believes he can. Get him on one day, and I'd really be interested if you could do that, Tim.
Okay, yeah, I will try again. He and Keith had talked about coming on together, but the scheduling was just difficult for them. So, well, let me go to Alex next. And I should ask Remi, are you doing okay in terms of, I mean, do you need any water or anything like that, or?
Oh, I've got a little bit of water.
Oh, okay.
This room makes the back of my throat tickle. There's something, I think there's dust in here or something.
Yeah, I just felt guilty. I know we've been going pretty heavy here, so I don't want to just grill you for 2 hours, you know.
Well, if you hear me coughing, I haven't got COVID. At least I haven't killed over yet.
Well, let me go to Alex next then.
Okay. Hello, Alex.
Hey, Remi, great presentation. Really a lot to think about here. I just had a quick question. It's a little bit tangential. I know you had been talking about like tachyon communication and violation of the no communication theorem. Can you talk a little bit about that and like whether, you know, if that were true, whether that would violate causality or not?
Oh.
Like where you could send a message to yourself before you sent it, you know?
I don't believe that. I believe, this is what I believe people are taking the Lorentz transform too literally. Yeah. I think I was on here a few weeks ago. Yes, I was. I was talking about a situation if you had bats in a cave and they're using echolocation. They've got some still vestiges of sight, but they've been in this cave so long and they're using this echolocation. They think it's the be all and end all of how you use metrology, how you measure your surrounds. And one day a group of cavers break in and they shine a light, and these vestigial eyes in these bats are saying, hang on, when I echolocate, I can now see that I'm dead reckoning. So by the time the sound wave has traveled and bounced back, in reality, the other bat or food morsel or some insect is not where it's supposed to be. And if you look at the Lorentz transform, it does have does have terms in it to do with time. Sorry, bear with me. I'm just thinking and doing it at the same time. Bear with me. I want to find the slide. There we go. Can you see that slide? Can you? Is it still on share? Yes, it's on share. Here's the Lorentz transform. So for the prime frame to the unprimed frame, prime frame. So that's for time. That's for space. So the gamma function is just the 1 over square root of 1 minus v squared over c squared, yes? Now, the second term here and here is the time retardation term. It's simply the time it takes from light to get from one point to the other. If you knock it out, you'd end up with these transforms. And I think I'd have to look at my history of science. I think these were what Lorentz originally proposed. Yeah. If you don't take this Lorentz transform too literally, you don't get these reverse causality effects, because let's try and think this through with time simultaneity. Yeah, imagine A and B are, I think they'd need to be vertical. No, I'd have to think this through. I'm not going to think about this on the fly, but the problem is coming from when you transform to different axes, that the axes don't stay perpendicular. Yeah?
Yeah.
They do this transform, and this is what a Lorentz transform looks like on the space-time diagram. And this is where all these notions of sending, yes, it is here, sending information back in time. If we look at A signaling B, yes, I've worked it out now. If we're looking at A signaling B, excuse me, if you project, so in A's frame, So imagine the unprimed frames, OA's frame. It believes they're sending a signal to B. I shouldn't have really shown that as horizontal because that's, well, it is showing superluminal. You'd be on the light curve, light cone. It's shown a superluminal signal from A to B. So in A's frame, everything looks fine and dandy. It's taking absolutely no time at all, and the signal arrives immediately at B. If you're in B's primed frame, you're seeing that A is in the future. So if you project across to this frame and then project B across, it's somehow sending information back in time, but it's an illusion because you're using this Lorentz transform with these time retardation terms on them. And if you could use a signal that's faster than light, you wouldn't be using this diagram, this space diagram. You'd be using this one. So I don't buy this idea that you're sending signals back in time. Yeah?
Yeah, makes sense. I was just curious because I heard you talking about it last week and, sounded like you knew a lot about this. So thank you for answering my question and for a great presentation.
Thank you very much, Alex. Yeah.
Thanks.
Thank you very much.
Well, it is an interesting question because it brings up that idea of, I've heard several people ask whether UAPs might be time traveling or something along those lines.
More things under the sun, Horatio.
Yes, sir.
Those UAPs are doing, I don't think we have all full knowledge. So I wouldn't rule out anything. I'm not ruling out time travel. Just, you don't see people from the future. Maybe these UAPs are.
HT Alvarez had a question, and I think he's been on multiple times. I think he has a bad connection, so I usually ask these for him. He was saying, and it's in chat, he's saying, thank you for your excellent and well-detailed presentation. In his 1952 Nature paper, Kulwick explains a similar idea about the EM pointing vector and dumping of energy on ZPE space. He's wondering what you're theorizing on using, let me see, dump the energy in ZPE space to create propulsion.
Right, dump the energy.
I hope I asked that correctly. I should apologize.
I think what you're talking about is energy and momentum conservation. If you consider both systems, if you consider the ZPE system and the mechanical system as one entity, and you'll find that momentum and energy is conserved. Whereas if you don't, then it just appears a mystery. It's a bit like radioactivity, say, when it was initially discovered, and you would put something that just spontaneously generate heat until they understood the phenomenon and say, here's another term we need to add on to the energy equation, then everything's conserved. What you don't know appears to be a violation, but when you include it, then it's not a violation. So does that help?
Yeah, I think so. I think so. And let me see. He just thanked me for asking in chat, so hopefully he'll mention if he has more questions. But yeah,
I think Michael was a bit keen. He was asking. Yeah, here we go. So he was asking a question. Just if you permit, Tim.
Oh yeah, Michael, did you have another question, sir?
Yeah, I'm still working on that one I was talking about with the question about the magnetized metal versus the dielectric, and I have this short little video I wanted to show you that to give you, if I could share.
Sure. Yeah, if that's okay with Remi, you just have to slow down a little bit so we can answer you though. You were getting ahead of him.
That's fine. Here we go.
Or dissectable Leyden jar in this case. Leyden jar is just what the first discovered capacitor was called. First, to prove it works as a normal capacitor, I charge it up here with a wind source machine. I disconnect it from the wind source machine, and then I discharge it. From the spark, you can see that the capacitor was in fact charged. Now to show you the neat thing, I charge it up again, but this time I remove the inside plate. And then I remove the outside plate. I touch them together. Notice that there's no spark, nothing, which seems weird. You'd expect that the plates would have been charged. I pick up the original container, and when I put my hand inside, I do feel some prickly sensation on my skin, and my hairs react. Next, I put the capacitor back together. What do you expect to happen when I discharge it? A spark happens. How does it work? Let's look at a cutaway view of the capacitor. Each plate has charge on it in the area between the two plates. One plate is negatively charged and the other is positively charged. We can also draw a line between each pair of charges, representing the electric field. The closer the lines are together, the stronger the electric field. As we pull the inside plate out, the area between the two plates decreases. The negative charge on one plate moves to stay close to the positive charge on the other plate, and vice versa. That means the charge on each plate is more tightly packed together, and so the electric field lines are closer together. The electric field is stronger. And as we pull the plate out more, the area is even smaller. The charges on each plate are even closer together, and so the electric field is even stronger yet. The electric field gets strong enough to begin ionizing the air in between the two plates and the container. That's done by pulling negative charge off the negative plate. It's also done by pulling negative charge from the neutral atoms on the container, leaving positive charge behind. The container is made of an insulating material. It doesn't conduct electricity, so the charge can't get from one plate all the way to the other. Instead, it ends up on the container. This side of the container becomes negatively charged, and this side positively charged. Having lost a lot of the negative charge on this plate, it's no longer very negatively charged. And having gained negative charge on this plate, it's no longer very positively charged. So the act of pulling the first plate out of the container has caused most of the charge from the plates to be deposited on the container. And that's why you can remove the plates, touch them together, and put them back and still get a spark. There is another phenomenon called dielectric absorption. It means that the molecules in the dielectric will be rearranged as dipoles, and so a sort of charging happens in the dielectric. But that takes a longer charging time and charges up the dielectric much less than we see here. Well, thanks for watching. See my YouTube channel, rimstar.org, for more informative videos like this. That includes one on how to make low voltage capacitor.
Okay, so what I was trying to show there is that it's not the metal doesn't store any charge. It's only in the dielectric. Whether the dielectric's air or whether the dielectric's a vacuum. A vacuum is a type of dielectric.
Okay.
So the point I was trying to make is that it's not the metal. And in this, and I've also worked a lot with hard disk media, where you actually have a thin film of ferromagnetic material that you magnetize one polarity to the other. That's how your hard drive works. So yeah. It's not that. It's and the inertial effects I've observed have more to do with that. The storage of the charge in the material.
Okay, I think there's some confusion here. I never did say that there was any electrical charge stored on the magnetic system. I called it magnetic charge. And also, you tend to find with most ferromagnetic materials used in a magnetic setting, they're like ferrites. They're specifically designed to not conduct electricity. They can't be equipotential surfaces. Yes.
Well, it depends on the polarity of. It depends on. So, if it depends on the polarity relative to the moving charge. So, if you have a positively charged magnet or a negatively charged magnet.
You mean electrical or magnetic?
On the magnet itself, on the outside. So.
Yeah, that's quite possible for it to take a surface charge. It's an insulator. Yes, it can take a charge, but it's not relevant in the situation I'm describing. Yeah.
Okay.
Maybe offline, if you want some more help on this, I can explain more to you. But the best way to understand something is not to come with too many preconceptions, because they're going to load your thinking. You're going to be trying to push it one way where you want it to explain the other way. If you just take
how do I describe
it?
I agree.
Yeah, yeah. If you take how I describe it, then it will fit. It will fit in to your knowledge base. Do you have access to the Feynman lectures? They're online. I could. It's somewhere near the middle of volume 2. There's an awful good lot of classical theory of electrodynamics in there. It's a good read, and it's at a level where it can take you from a sort of teenage student right up to about end of second year degree course, even the third year course.
Okay,
It's online.
Thank you for your suggestion.
Okay,
Yeah.
well, thank you, Michael. So let me go to Jeremiah, and I think we're probably almost out of time then. Jeremiah, welcome back, sir.
Hi, Jeremiah. Hi.
Okay, sorry, yeah, got myself unmuted. I can answer pretty much all those questions, Michael, about the Feynman disk. I studied it very extensively and have tried to replicate several different variations of it, and even tried to develop materials with trapped charges to maximize the effect. So Feynman states a couple of important things in the lecture that are critical in order to make the thing work. First off, he states that the disk itself must be made of an insulating material, like acrylic, like fiberglass. It should be ideally a low mass material, and in the most ideal situation, there will be no disk at all. Just open space in a vacuum. Each individual sphere, the black circles around the edge of the disk, are all supposed to be hollow, very lightweight spheres on which you charge to a very high potential that cannot leak with no sharp points, and they are just resting on the surface attached to the disk, sort of to all keep them in relation to each other. So what happens is the field, when you connect the current from the electromagnet, builds up slowly over time. So the overall volts per meter that are radiated out from the acceleration of the charges within the wire as the current begins to build is a relatively small value, and as a result, the radiated flux that exerts a force or a Lorentz force on the charges that are trapped in each individual charged sphere is relatively small. However, when you disrupt the current, all of the forward momentum from the accelerated charges that had accelerated slowly over time and are now at a reasonably higher velocity suddenly stop. And that instantaneous change equals a very, very high volts per meter that only travels outwards from the now disconnected or open circuit electromagnet. And because that field is a space field that does not have anything to do with the charges any longer in the wire or with the coil itself, because it's effectively disappeared from the circuit now that it's open, and charges can no longer reflect from it because they'll just freely move around as if they were just in open air. What happens is the field travels outwards radially from the center of the solenoid electromagnet, hits the spheres that are charged, and exerts a Lorentz force on them that causes them to experience a slight angular momentum that was the difference in the change of velocity over time that the electrons took when they were already moving at a velocity v through the wire, and they suddenly stopped.
So it was because there was no power to the coil at that point. It's
because there was power to the coil previously, and in originally the thought experiment, he says, imagine that the system starts out with current already flowing through the coil, and the battery is connected in the start of our experiment.
So you need a battery to start it.
He suggests that you actually use a superconductor for a practical experiment, and that you let the superconductor go from a magnetized state in its superconducting state, where you basically place it down the center of a disk where it's already containing charged spheres. This could be done theoretically in a vacuum, where you have a superconductor that you can somehow cool down.
A magnet.
Has anyone made one that works?
Basically, you let it warm up and let it go from being supercritical to not. And during the transition, it'll automatically expel a tremendously strong flux that should exert forces on the charges trapped in the spheres.
The question is, did it work? Did your experiment?
Yeah, it's been replicated. It's not by Feynman, but by a couple of independent labs. There are a few papers that were replicated to show that there is a very small force. There's a problem, though. I want to point out a problem with this experiment, and it's one that almost everybody overlooks. Imagine that we have four large individual spheres. They're isolated from each other, but they're physically large. What happens to the charges that are trapped on the surface of the sphere, which normally would self-distribute sort of evenly across the surface of the sphere? Well, when the B flux from the radiated field that's angular, that means it's going to be just, pointing from, if you have a disk, it's going to be pointing towards, the rotation of the disk. It's not going to be pointing outwards or upwards or any other direction. It's going to try to make the disk rotate. So because it's angular like that, you're depending on the amount of charge that you have trapped on those spheres, and you're also depending on that rate change over time. Let's see, how can I put this better?
Well, Jeremiah, we're almost.
Go ahead. Yeah, maybe I shouldn't take all the time. Let's talk about this, Remi and Boyd. I'd love to
talk about this. Yeah,
because I have a lot more information and some papers and experiments that link to showing this demonstration operational. But I can tell you this: the larger the spheres are, the charges will move over the surface of the conductive spheres. So ideally, you want them to be as small as possible. Ideally, they be trapped ions, so that the electrons that can move, that are mobile over the surface of any metallic conductors, can't move very far. Therefore, they have to exert their force to the disk instead of simply moving within the conductor.
Yeah, I get what you're getting at. Yeah.
Okay. Well, let's do that. Okay.
We'll talk later. Yeah.
Yeah, Michael too. Yeah, joining too. Yeah. Okay. Then thank you very much. Yeah, thank you.
Wonderful. Okay, so I'm going to mute everybody out. Again, I'm going to put it back on gallery view. Again, everyone, please give Remi Cornwall an enormous hand. Very, very in-depth presentation, a wonderful Q&A session. I mean, just going through tons and tons of material. So thank you, Remi. I very much appreciate it, and I'd love to have you present again in the future if you're up to it. Okay, so now I'm going to go back to speaker view, and we have Sandy Kidd with us. Sandy, welcome, sir. You know what? Before you get started, let me read your bio. Sandy Kidd is a Scottish inventor and former RAF radar technician who developed a novel approach to gyroscopic propulsion in the 1980s, based on the principle that a gyroscope set at various angles could provide a lifting force. His work has been described as being based on the principle of forced precessed gyroscopes and has been reviewed by Eric Lathwaite, David Hatcher-Childress, Dr. Harold Aspden, Dr. Bill Ferrier, and many others. So Sandy, welcome, sir, and take it away.
Hello, everyone, and thank you very much for your kind invitation allowing me to address this conference. My name is Sandy Kidd. I'm nearly 84 years old now and have been hunting down anti-gravity for many of these years. This for me has been a very lengthy hunt in this quest, so I shall air my rather extended story one salient piece at a time. Many times during this quest I've been asked, why did I do it that way? On the face it's a very reasonable question. I had visualized turning some easily generated centrifugal force in an upwards direction, and the generally held belief pertaining to the conservation law that this was possible using gyroscopes. However, during continued development, it was found that the reasons for the operation of my devices got further and further away from the original thinking. I have consequently learned many strange things about gyroscopes and flywheels. That said, I was in a quandary as to where to make a start. I have therefore decided to highlight anything I think may be of interest to the conference.
And I can help with, oh, okay, there you go. Wonderful.
Right, Tim, thank you. I must say at this time that my relationship with gyroscopes and inertial drive has now endured for many years, was the result of seriously flawed thinking mixed with success born out of sheer good luck. I started off, I was thinking all weird things at the time, but I had an idea that back in the 70s, I gave a bit of thought to create a device which could divert some momentum in an upward direction. I had the notion that a person could rotate a couple of bricks, one each from a string on each hand, say about 6 inches from the center of the person to the center of the mass of the brick. We must assume that this person has the ability to make himself rotate rapidly around the same spot on the ground or turntable, such that the person can generate copious amounts of centrifugal centrifugal force via the accelerated bricks in this system. If we consider each brick weighs about a couple of pounds, which would relate to approximately 300 pounds of centrifugal force generated by each brick if the person could rotate at 300 revs per minute. However, no matter how fast these bricks could be rotated by the person, these bricks could never reach the horizontal position, a line, say, through the person's shoulders, because of the effects of gravity. I thought to myself that somehow, by some magical force, rocket motors, of course, were disallowed, and those bricks would be made to rotate at the same speed, but at the angle of 45 degrees of inclination to the horizontal. That would do it. This was impossible, but if these bricks could be somehow raised to this angle, the vertical components would be equal to the horizontal components, assuming that the radii of rotation were the same. Consider 600 pounds of vertical acceleration with a man in bricks weighing, say, 200 pounds, a big man. That would be around 3 Gs of vertical acceleration. Unfortunately, it was all impossible, an altogether fruitless idea. After seeing the 1974 Christmas lectures presented by Professor Eric Leithwaite, when he accelerated a 50-pound flywheel effortlessly around his body and head, I immediately started designing a device to incorporate a pair of gyroscopes into my bricks on strings idea. I hoped that the gyroscopes would be driven fast enough in machine rotation to create the level of centrifugal force I required, and the gyroscopes themselves would rotate fast enough to carry up to 45 degrees or thereabouts to give me the vertical thrust. Such was my knowledge of gyroscopes at the time. Eventually, after a great deal of trial and error, a set of dimensions were finalized. Expediency was always the name of the game. I have abbreviated this very extensive story at this time to get through this part of the saga quickly. The first problem was that the input drive to the gyroscopes had to be on the center line, the vertical rotation axis of the device, and had to drive the gyroscope from outside the machine. As I already decided to rotate the machine itself by means of my pedestal drill, the input for the gyroscopes had to be at the lower end of the machine. In order that the gyroscopes rotate in opposite directions, I decided to make a bevel gearbox to handle this function, although unfortunately I could only find a pair of matched brass bevel gears from the tuner of an old valve radio. Belt drive from the gearbox to the gyroscopes had already been decided upon, which meant that the output shaft would carry a driving pulley and a driven pulley. The driven pulley would have to freewheel against the direction of the driven gearbox shaft. The engine delivered over 1 brake horsepower at about 14,000 revs per minute, which was ideal for driving my gyroscopes. I thought it would be easier to run the rotation speed of the machine at a fixed speed and, if necessary, work from there. I had a pillar drill available to fill this need, so it was set up to support the top end of the machine. The original rotation speed of the device was set at 350 revs. Much later on, the speed was reduced to about 250 revs after being successfully run at that speed on a different make of pillar drill in Newark, Boulder, Colorado. My first attempt at the problem produced, after much trial and error, a very useful device, which eventually became shown on YouTube as Anti-Gravity Machine Part 1 and Anti-Gravity Machine Part 2. Please accept the fact that this was designed to be a human interest story, so a lot of the personal sacrifice info was exaggerated and added to suit. That's the 2 links there. I'm not opening it this time, I'll be here forever. Originally, the device delivered on demand 16 ounces of thrust for 15 to 20 minutes at a time, if required, or as long as the engine was fed fuel. It could be controlled by gyroscopic rotation speed to rise or fall, or even be held midway if required. This part is pretty well the documented history of my first machine. The rest of the story has been the struggle for acceptance. It is strange, often funny, how people, including myself, can go through their lives believing things which are totally untrue, which are never ever affected by their beliefs. I remember a teacher explaining to our science class how gas was liquefied. The process which was explained to us seemed to be quite reasonable at the time and was received as gospel. Much later in life, I subjected myself to a considerable amount of embarrassment when I discussed the process with a knowledgeable American friend of mine who just happened to be a gas compression specialist in the offshore oil and gas industry. I was very diplomatically corrected and educated. I often wonder how the rest of the class fared. In light of the fact that most of them were oriented on literary subjects, the truth would probably never ever affect them. one has to ask who taught the teacher. Similarly, over the years, I've noticed there exists misconceptions or misunderstandings relating to physics surrounding aerodynamics and the operation of gyroscopes. And in many cases, these misconceptions and misunderstandings are held by learned people. Only when scrutinized at very close range, by that I mean actual experiment, can the truth ever be known. If a mass is accelerated in a circle, angular momentum and consequently centrifugal force is produced, the quantity of which depends on the weight of the object, the radius of rotation, and the radial rotation speed. At no time in my life was it ever suggested to me that if the weight is rotating whilst being accelerated in the radial path, loss of angular momentum would occur. This undisclosed information caused me a great deal of time, money, and grief. The success of my first machine depended heavily on the fact that this was not the case. In any event, whilst my first machine was being stonewalled in Dundee University, I went ahead and built a rather expensive second machine, which I thought would perform much better than the first one. This was an updated but very similar device, incorporating many improvements over the original. I will apologize at this point that there is no photograph of this device available, which is unfortunate, as I learned more from this device than any other one. I will be able to rake up some drawings if I look hard enough. However, it is in many respects similar to the Australian laboratory test device, but it had no cams actuating the gyroscopes in and out. In other words, just a plain machine. I had not considered the use of cams at all at this time. When testing my original machine, I was aware that something was amiss. The copious amounts of centrifugal force which should have been apparent was not in evidence. The alarm bell should have started ringing then. I commenced to test a newer machine and a whole range of unexpected issues were thrown up. In light of the fact it was built so much better than the original, the gyroscopes lifted themselves incredibly easy to a position just as high as the structure of the device would allow. I thought at the time that this was very good. There appeared to be no lifting force or vertical thrust at all. This baffled me. Raising a 1 pound weight, rotated at 6-inch radius at 300 plus revolutions per minute, past an elevated angle of 60 degrees and more, should have driven it through the garage roof. Something was fundamentally wrong here, and I didn't have a clue what it was. I had managed to get 16 inches of thrust out of the first machine, and it just didn't have the ability to do what the newer one could do. In my diary, which I used to keep, I've written that something appeared to terminate the ability of the gyroscopes and supporting arms of the original machine from climbing any higher. What this could be, I did not know. I tried several pathetic mechanical modifications to exert some kind of control, but this was found to be a wasted effort. I just could not stop the gyroscope accelerating inwards towards the center of the device. As the gyroscopes went through this motion, the machine rotation speeded up and the machine apparently unloaded itself. Gyroscopes often appear to have minds of their own, but this was something completely different. It seemed sensible to me to accelerate the gyroscopes in hub rotation to increase the rotation speed of the device. This would drive them out again as the centrifugal force increased. This approach seemed reasonable to me at the time. The next month was spent building a little twin-cylinder hydraulic pump to fit onto the main drive of the device. The pump was set such that as soon as the pump detected any inward movement of a gyroscope, the pump would no longer allow oil to pass and create a hydraulic lock. The pump was designed and set to slip under normal circumstances at 250 revs. When gyroscopic movement was detected, a very precise rotary valve was designed to close rapidly, increasing the rotation speed instantly to 500 revs per minute, doubling the speed squares the centrifugal force generated. The expected result was that the gyroscopes would accelerate inwards until the pump stopped the flow. The immediate increase in speed to 500 revs would drive the gyroscopes out again, and so on. When the machine was run up, the system worked very well, apart from the fact I just could not believe the speed at which these gyros accelerated inwards. Instead of slowing the gyroscopes down, the opposite had happened. I sat in the front of that machine for hours watching the motion, total disbelief. Complete confusion now set into my mind. Why the first machine operated so successfully when the second one, much more powerful, much more efficient, much better constructed machine, failed so miserably, caused me a great deal of anxiety. and caused me to spend many successive years of my life clutching at straws. My first thought was that there had to be some sort of cyclic motion take place within the first device to allow it to work, although there appeared to be no such action visibly taking place. I was, however, convinced that this had to be the case and examined what I thought at the time were all the possibilities that could allow this action to take place. In the end, I just don't know enough about idiosyncrasies and gyroscopic behavior, but I was learning. Excuse me. From that, a bonus from the above testing was finding the elements which were necessary to create what later became known as the pre-launch scenario. Consider a system such as previously described and let it be rotated at constant speed. Let the gyroscopes be elevated to their highest position. From experiment, we know that there is no reaction during this motion. The device is still rotated at the same constant speed. We mechanically arrange to hold the gyroscopes temporarily in this position. We then slow the gyroscopes right down, or better still break them to almost stopping, eddy current breaking perhaps. We then release the gyroscopes from their elevated position and allow them to descend freely. The angular momentum which was previously removed from the system will return in total when the gyroscopes are stopped. The large vertical pulse regenerated units return part of the cycle. I admit the gyroscope system will be slow to recover, but if made large enough and designed to include numerous opposing pairs of gyroscopes, and though the craft would unfortunately be space-bound, it would create a much cheaper, much safer and controllable alternative to rocket travel. Australia. About this time, I heard about Scott Strachan's machine. Scott Strachan was a fellow countryman of mine who hailed from the city of my birth, Edinburgh. Must be something in the water. Scott had a patent application number 8803860.9 in the name of John Scott Strachan. He'd apparently got some useful results from a gyroscopic device some time before I did. Scott contacted me shortly after my claims were made known and we chatted of it. It transpired that Scott had taken his machine to Eric Laithwaite sometime previously to my visit, but Eric Laithwaite never ever told me about Scott's visit and the demonstration of Scott's gyroscopic device. This caused us both some concern, but I carried on regardless. An interesting point was raised by Scott that was that his gyroscopes were physically actuated by use of cams to oscillate his gyroscopes simultaneously up and down. Immediately I thought that my gyroscopes could somehow be being oscillated in a like manner in line with my previous thinking. This was about the time my struggle in Dundee University came to an end, and an Australian business showed considerable interest in my device, offered to fund its development, and accordingly a contract was drawn up. I was given the task of building another device, any other device, even a copy of my first device, which would produce the same effects as my first machine. The decision I made in relation to building a cam actuated device turned out to be a very bad one and sent me off on a 20-year wild goose chase. Needless to say, a cam actuated device was designed and built. In fact, a pair of them were eventually built, one for in-house development and one specifically for a lab test. The machine built for in-house development was a straightforward machine built into a suitable frame and was powered by two speed-controlled electric motors. This setup turned out to be very useful, the findings of which were used to determine the operating parameters required for the machine built specifically for the laboratory test. On the other hand, the laboratory test was, for very good reasons, a compromise in many aspects. When deciding on the setup for the device to be tested for inertial thrust in the laboratory, I came to the following conclusions. To reduce weight and mechanical complication, both the gyroscopes and associated machine rotation drives would be from the same source. This was a risky thing to do, but as the operating parameters had been gleaned from the in-house development, but identical device, I believed that this was a risk worth taking. The power source would be a water-cooled miniature two-stroke engine of 6.5 cubic cc's capacity with a considerable power, 1 brake horsepower at 16,000 hours. Power to the device would be through a tried and tested centrifugal clutch, which I had originally made for my first machine and which I had brought with me to Australia specifically for this test. The idea behind the water-cooled engine was that the complete engine and its power unit to be built into a small closed wooden box. This would help eliminate claims of aerodynamic or other outside interference with the results. There would be 2 water tanks on board, both of light plastic construction, one being a feed tank and the other a catch tank. At the commencement of the test run, water would be released from the feed tank to go through the engine, cooling it, ending up in a slightly larger catch tank. It would also ensure there was no chance change in the weight during the test runs. The engine exhaust was set up using a long piece of manufactured for the purpose silicon tubing facing slightly upwards, again to eliminate any claims of exhaust gas thrust influencing results. Power transmission was via gears to the main machine rotating drive and a gyroscope rotating power via Bellwood gearbox and pulley drive to the gyroscope. Belts were 6mm round section polyurethane. The enclosed box was suspended in the laboratory on a Kevlar cord via strain gauges from an overhead beam. Unfortunately, this time I had not used radio to control my machines, and to some extent, this limited the machine's capability to produce thrust. This test is described over many detailed pages in my book Beyond 2001. Once again, Lady Luck smiled upon me as the device achieved 20 consecutive and successful runs of non-zero bias. The thrust was not of a large order, but was consistent and definite. Although subsequently deliberately ignored, this represented the first official ever test at which proved that inertial drive was possible and has ever been achieved. Now, later on, Thomas and I were in the process of writing a book, more of a human interest story than a technical description of inertial drive, and the success of the book depended very heavily on the outcome of the laboratory testing. I had previously made it clear that the book would not go into print unless the aforementioned series of laboratory tests were conclusive and positive. The series of tests were carried out under the instruction and supervision of APEC Laboratories, Port Melbourne, Victoria, Australia, probably the highest profile laboratory in the Southern Hemisphere. Against while the device was tested in the APEC laboratories showing positive results, the operation of the device posed more questions than answers as to its mode of operation. There again was something going on which I didn't fully understand, but which I thought I had a fair idea. I thought a differential in angular momentum had to be created during the oscillation of the gyroscopes. Some vagaries of mechanical accelerator. On the way there, this is the sort of stuff I found out. The only cases I know where a gyroscope will appear to float above its horizontal plane of rotation of its own volition are whilst operating in a gravity accelerated system in precession or in a mechanically accelerated system in precession, or what I tend to call saturation. A gyroscope in a gravity accelerated system is one effectively in decay and therefore dropping, while a gyroscope in a mechanically accelerated system is absorbing energy and rising. Contrary to what the clever people say, in either case there is no angular momentum or centrifugal force present, which is really not much good for our use of the inertial drive system, except perhaps in a free lunch scenario. A gyroscope in a mechanically accelerated system with a fixed system rotation speed, or as it's often called hub rotation speed, will show a loss of centrifugal force at the gyroscope if the rotation speed of the gyroscope is increased, and will show an increase in centrifugal force if the rotation speed is reduced. The term hub rotation speed avoids confusion with gyroscopic rotation speed. I avoided using the term angular momentum, which is really more suitable but less easily understood by the average person. Whereas they are both created by the same acceleration, you can't have one without the other, even if they are different animals. It will be realized that if this is true, it casts serious doubts on the credibility of the conservation laws, in this case, the conservation of angular momentum. Centrifugal force will be at maximum when there is no centrifugal gyroscope rotation. However, at the other end of the scale, when the gyroscope rotation speed is sufficiently raised, the gyroscope will reach what's commonly called precession, but what I now for good reason call the saturation point, where and only at this point centrifugal force has totally disappeared, and the gyroscope will then accelerate inwards and upwards until it is mechanically stopped. If not mechanically halted on such time as the plane of rotation of the gyroscope is at right angles to the axis of the hub rotation, i.e. as far as it can go on the point or the position of least action. At this point, the gyroscope rotation axis and the hub rotation axis effectively become the same. Assuming that the machine is a plane twin opposed gyroscope. When operating below the saturation point, it would be almost impossible to judge them. Sorry about that. Oh, Jesus. When operating, sorry, sorry about that. When operating below the saturation point, as there are no visual clues, it would be very hard to know, apart from serious imbalance, if one gyroscope was rotating faster than the other. I've already stated that the point precession starts or the saturation point is reached, there is no further increase of energy into the system, whilst the gyroscope will travel, if possible, vertically through 90 degrees without stopping. There is no balance point on the way. The most intriguing thing is that the system will be found to be rotating without acceleration. There's no angular momentum present in the system. There's no centrifugal force present in the system. There's no accelerated mass. What we have is just a vision, something like a holograph of the system magically rotating with no measurable inertia. As far back as 2004, I stated that no mass cannot be accelerated. This is the only occasion I know where gyroscopes or flyfields operate in precession, or as I prefer to call it, a saturation can actually produce positive results, and that would be in the free lunch scenario. I built a very simple device from spare parts found in my scrap box. Expedience has always been the name of the game, and this device was treated no differently. It was designed to demonstrate the effect that gyroscope rotation speed on their generation of centrifugal force. It would be more appropriate to call it angular momentum, but I'm using centrifugal force, which is more easily understood by folks. The device, as far as I'm concerned, was able to demonstrate that the variation of gyroscopic rotation speed was capable of raising and lowering the gyroscopes against the central bias spring. Unfortunately, I invariably attract the lunatic pitch who were convinced by virtue of their deep knowledge and experience of gyroscope behavior that it was gyroscopic precession which was doing the job. I obviously did a lousy job with my introduction statement. May I apologize for the very noisy screaming gear. I needed a 14-tooth gear. I think the only one I could find was made of steel and not quite the correct tooth shape, but it did the job though. That's a link to that. The first publicized inertial drive. During the 50s and 60s, there had been a fair amount of publicity relating to an alleged inertial drive, which was invented by a Norman L. Dean and popularized in American astounding science fiction magazine by the then editor, one John W. Campbell. The device became well known as the Dean machine or the Dean drive and became the subject of much discussion and controversy. The device was probably the first of more publicized anti-gravity machines, of which there have now been thousands. If you check his background, Dean was nobody's fool. In fact, he would appear to have been quite a rather bright individual, but whether his device produced one-way thrust or not has never been proven. Of course, this announcement only served to fuel the fire of determination within me. I suggested many times previously that any action capable of producing inertia must be a cyclic one. The late B. Harry Stein of Dean drive evaluation, amongst many outstanding achievements, made the comment that a successful inertial drive system would be in the form of a device which could be effectively cyclically change itself from one mode of operation to another. In other words, cyclically change itself from one type of machine to another. His words were permanently fixed in my mind. Harry was a great promoter of model rockets and did a great deal of testing of these things. From that interest in Dean drive evaluation came the Stein-Davis ballistics pendulum test. This pendulum test is cheap and easy to set up and test, and lends itself to visually displaying the outcome of the test. Providing the device on test has been designed to move in the horizontal plane, this pendulum test will very easily show if the device is genuine or not, without the need for sophisticated instrumentation. Well, it's just after the completion of my VIPAC lab test in Melbourne, Australia, I had occasion to contact Harry in Phoenix. He said, Sandy, I've been witness to and suffered every kind of screaming, snarling, and vibrating gizmo for 30 years without a positive result. But I believe it can be done, so please succeed. I think you can spare you the rest, gentlemen. That's a bit. I'm going to the film photographs now. It's stuck here.
Wonderful. And Sandy, do you have photos to show us?
Yeah, that's what I'm trying to find. I'm an amateur at this.
Oh, no worries, sir. No worries at all. I just wanted to make sure. I found your videos on YouTube also. I can play the anti-gravity machine part 3 if you'd like.
You got that, did you? Okay. It's a noisy thing. I had. Oh, wait now. You have liftoff. We get back to the start of this. Oh, maybe. This is all new to me, this. Sorry about this.
And you may need to do share screen again, the green button at the bottom.
Ah, wait a minute. It's still, my photographs are not there, though. Dreadfully sorry about this, chaps. Jesus. Where am I now? You see that?
No, you'll need to hit the green share screen button again. It's at the bottom of that.
Where's it going? Jesus. There's something stupid here. Ah, dear.
Well, Sandy, while you look for that, why don't I put up the, I will share my screen and I'll put up the video of the anti-gravity machine.
Okay, that's good. Thank you.
Oh, sure thing. Absolutely. Okay. And I have the sound off. There we go.
Lost it. I don't know what I've done. Lost it.
Oh, God, Sandy.
No, I'm just fine if I got it read through them to put on the pictures. Lost my file. Yeah, I found it now. We can just get back in here now, it'll be fine.
What happened?
It's helped me out, he's shown them that while I got sorted out. Sorry. I'm done on my reading.
I'm bloody never been so tired in my life. Chocolate everywhere. I just you have no idea. I'm waiting for bed. Your water bottle beside your
Away you
bed.
go.
Sorry, can you guys hear this okay? Jeremy's saying no audio. No, no audio. Okay. Okay. You know what? Here, let me stop sharing. And that's why. Okay. Do you guys want me to play that again with audio, or are we good? Okay. Well, Sandy, did you have some photos that you wanted to share for us, or?
See what I can do.
There we go.
This was my first idea. Oh. Basic man standing there, holding the bricks, spinning the bricks at the angle I wanted them to go to. That was my first machine. I can't move it on now. Good. What have I done again now? I've done something stupid again. Can you see that?
So I can see the thumbnails in your photo manager.
I'll have to, yeah.
There we go, and I can see your mouse cursor as well.
I could hardly believe it. There was a feeling of sheer joy and relief. I'd done it.
Should have put them straight up and down.
Throughout this project, Sandy had worked alone without help from experts, not even from Professor Laithwaite, who had inspired him 10 years before on television. Now, in his hour of jubilation, he was the man Sandy wanted to give his news to first of all.
Well, I watched this effect for 18 months now, and I couldn't figure out what it was. But I've now proved conclusively that from 0 to 1,000 revs, you're absolutely correct in what you said.
Sandy was so obviously
that was my first machine.
And so almost self-effacing.
That was it down at Imperial College. That's Eric Laithwaite standing
And of
behind.
course, it was gyroscopes. And I asked him a few questions, such
That
as...
is the first Australian machine for the lab test. That's the one in the box that was set up to get the correct running parameters for the test machine. That was the patent. That's the two guys. He was the co-director of APEC, actually, John Simmons. He did the test. That was the result of the test. A series of 20 identical tests were conducted on this gyroscopic machine. Quickly goes, the force bias was non-zero for all 20 tests. The average force bias generated accounted to 2% of the highest force peaks. And that was the book. And that's the machine you just showed just now at rest with a spring on it. This machine here was a much better version of that anti-gravity 3. It's never been shown, designed to show everything from basics, from zero hub speed, from zero gyro speed. It'll show you everything that gyro will do under these accelerated conditions. It's fully instrumented. It's telemetry, all telemetry. Even they're not fitted yet, but there's two little strain gauges fitted under each side, and the outputs came out through this miniature rush gear. What do you call it? Forget what you call it now. The price of old age. They're all just more copies of the same thing. I've got hundreds and hundreds of machines, but I don't want to bore you with them. That was the old machine and new machine together. It's replacement. That's the replacement. That's another view of the replacement. That's about it, Tim. I'm sorry about that. I made a mess of that lot.
Oh no, that's wonderful. Yeah, I'm just wondering, do you have more that you'd like to show us, or
I've got hundreds, but I'll leave it just now. I'll sort them out so they can be a bit more intelligible.
Oh, okay. Well, if you'd like, we could go to our Q&A session.
Yeah, you can do that, please.
Okay. Yes, sir.
Sorry about that. I'm dreadfully sorry. I had my little granddaughter showing me what to do, and I must have done something she told me not to do.
Oh, no worries at all. I just genuinely appreciate you presenting this for us and showing us all of these things. Well, so who would like to ask questions first? Would you guys like to raise your hand in chat? Or Jeremiah, looks like you're unmuted. Did you have a question?
Yeah. You were mentioning that one of the things you really wish you had known early on was about the acceleration and precession of that system and how you could reduce the inertia of that system during acceleration, I think is what you were saying. Could you clarify a little bit more on that? About what happens when you're accelerating a gyroscope and you're precessing it at the same time, I think is what you were talking about.
Both accelerations, it will lose weight faster. It'll lose angular momentum faster. If I have a gyro rotating at a fixed speed and rotate the machine faster, it will lose. It actually transfers its weight to the center of the machine. And that's why it goes up. None of this Euler stuff, this mathematics they give you, it's just not true.
I got you.
Actually,
that's what I needed clarification on. Thank you. Okay, that's all.
Okay, and then I think Mark Sokol had some questions too, and you had some. Mark was pounding stuff out there in chat.
Oh yeah, I was just thinking there was a couple people who brought up gyroscopic devices like this in the past. And one thing I noticed, I actually built a device similar to that I was showing to you earlier. This uses a two-axis system where they can move both on the Z 90 degrees, and also they can move on the Y, I guess you'd call that, while it's spinning. Have you ever built a device like this, or have any idea if something like this would work?
Probably not, Mark. Probably not. I built this about every other conceivable shape and form. But one thing I did find out, and it's going to, sorry, I'm upset you, but no gyroscope on its own, no matter how enticed, accelerated, bounced up or down, can deliver thrust. I've discovered that. It doesn't mean to say it can't do it, but on its own it won't.
What do you mean by on its own? What needs to be added?
If I take a gyroscope, I can accelerate it any way I like, up or down, do what I like. There's no way it will ever give me inertial thrust. Other things have to be done to do it.
What other things?
Well, I've just given you the fact that if you believe it, that the angular momentum can be taken away or altered, and you manipulate the angular momentum, you can get anti-gravity.
Or you can get inertial. You can change the angular momentum to linear momentum, right?
Yes.
Okay, and that
you can't do it with one gyroscope. You got.
Well, think of it this way. What's inside the core of the atom is a whole bunch of gyroscopes, which are
Yes.
angular momentum. So if there is a connection between angular momentum and linear momentum, then that's where inertia comes from. When you actually throw a baseball or a cricket ball out there in Europe, you're actually changing the subatomic spins of the particles and energizing them. And that's where your inertia comes from.
Well, the thing that gives the giveaway, Mark, is the thing I thought you personally would have got interested in before I even thought of going on to this thing, was the fact that if you have two accelerations at right angles, it seems to cancel inertia. There's a guy on the website, or the forum I used to be on, and he used to call it dark motion, he called it. And he did purely on the gravitational systems. Mine have always been accelerated systems, but he's seen the same thing. And there's absolutely no angular momentum or any kind of mass acceleration between the level. Can you see this thing?
Yeah.
You see what it was. That was that other machine.
That's what
if I go all the way up with that, if I go all the way up with that, that gyro is actually trying to run around there. And that one's trying to do the same. The only thing that stops them is the linkage or the stops. But forgot what I was saying. That's the price of old age. It's murder. Don't get it 84 for it. But
which setup gave you the best thrust to weight ratio?
The best I've had.
Yeah.
Well, I've got one that's I've had for a few years that I daren't divulge it. I'll get shot. See, at the end of the day, I discovered I can always get thrust. And I'll tell you, there's very simple ways of doing it. That you do it accidentally, you don't even know you're doing it. But in the end of the day, it's the pulse rate that's going to beat you. My first machine, that one did 16 ounces, but to start with, it was down to about 8 ounces by the time we finished for different reasons. That was done at about 300 revs per minute, which was down on the rotation speed of the device because of the mechanism it did it. It's not obvious how it did it or why it did it. It took me years to find out. But it was only about, say, 300 revs per minute. One pulse, 300 pulses per minute. That is not enough to get you into space. But 5,000 might. So that's what I worked on immediately after I did the Australian test. I on a machine to do that. It can be done, but it's not easy and it costs a lot of money. I'll have to borrow your NC machine there.
Our CNC machine, yes. We'll show you that later.
Well, I built one of these already on the Murray Seaky, and it cost me $9,000, and that was 30 quid, 9,000 pounds about 30 years ago. So I actually got myself a 3D printer to make which did an awful lot of good work for me. Showed you, I made a, what do you call it, a model of it, and it's good.
If you have the models, we do have a state-of-the-art CNC machine here at the lab in Jersey, and we can replicate your
Is it
devices.
a mill?
What?
Is it a mill or a lathe?
Oh, it's a mill with a fourth axis.
Oh, okay. Yeah, I was looking for somebody with a Murray Seaky lathe about a foot diameter. It would give me this. It's a special hybrid device to do it. But you can, it follows all of my print. I showed it to Ron Evans. You know, Ron saw it. These guys were quite tickled pink with what it did. But that was about 30 years ago. So
ours can do, I think, 16 inches on the Y, 20 on the Z, and 30 on the X.
You know, I should mention, I think Ron Evans is actually here today, too.
Is he?
Yeah, yeah. I'm not. Yep, looks
Old
like
friend of mine.
Yeah, and then I think Rob Chambers is as well. Yep, he's here. So yeah, him and Ron are both here. So, okay. Well, let me go next to Mark Fiorentino. Mark, would you like to go, sir?
Yeah, I have a question for Sandy and Mark. What's the highest revolutions per minute you were able to achieve with your machines?
I never tried much more than I did about 500 revs, but that's about as much as I wanted to go. It was not. I don't think it was necessary to go that fast. But an average of about 350. The first machine was 300. It's just a speed I picked. There was a radial drill that did that. That's why I used it. I've had gyros rotating about 15 and 16,000 revs, bronze ones, but the machine itself, 350.
Yeah, my gyroscopes, they're made in England actually, and they go about to 10,000 RPM, roughly. They're about we checked it with an RPM meter. They fluctuate a bit, but around 10,000 RPM. I think what's his name? There's another presenter who's working on this as well. Oh, Mike Gamble. Oh, there he is. Yeah, Mike is also building similar devices.
Thank you.
Talk about the RPM speeds and whatnot.
Okay, so let me see. And let me go to Ross Small next. Ross, I'll ask you to unmute.
Yeah, hey, Danny.
Hi.
So yeah, you said it perfectly when you said the way to create linear thrust is basically what you're doing is you're converting angular acceleration into linear acceleration, essentially. So, well, I have a friend that figured out 3 ways to do it. So he did it with angular acceleration. So only while the machine was accelerating faster and faster and faster and faster, he had a linear tether that stayed linear with the gyro, and it created linear thrust only during acceleration. And then he did it after the gyro was already at a super high speed, and while it was decelerating the same way with the linear tether, slowing it down, it did the same thing. So he was creating linear thrust for acceleration or deceleration, and then he figured out how to do it with acceleration and deceleration in a wave pattern. So is your machine changing speed, or you're staying?
Gyros are changing speed.
Okay, so you are accelerating and decelerating constantly.
The first machine, the gyros change speed all the time.
Like, but microscopic.
It's not obvious, but it is.
It's just a teeny bit, right? Just a teeny bit.
It's enough. No, it requires, what happens actually is one gyro accelerates, it loses angular momentum. So the other one actually drags it across off the center line. If you notice my machine, it bends in the middle.
Yeah.
And that's what it does. And as it does this, it pulls it up, and you've got basically an empty bucket at the top, filling up with angular momentum as it comes down.
And you could also think of it like they're 2 separate gyroscopes and they have a center of gravity in the middle.
Yes, they're joined.
So the center of gravity is what actually is moving linearly.
Yes. But
okay, that's exactly what I thought.
I had that machine to start with. It worked well, and I tidied it up to take it down to see Eric Lathwaite at Imperial College. And tightened up all the rivets on the frame. If you look at the frame, it's a bit tatty-like, but there was rivets in it. I tightened up all the rivets and it stopped working, and I couldn't figure out why. And that's what it was. It was the thing could rock and roll back and forward. When it did that, one gyro could always lift the other one, and away it went.
And last question. So, do you use springs to slow it down and speed it up, or there's no springs involved?
No, the shaft actually was the counterweight was actually creating the spring. Because it was the weight of the machine. So as it bent across, it peeled back again. And
okay, so that's sort of like storing up, releasing energy.
Pretty well, yeah.
Yeah.
As one went slower, the slow one is the active one. As you speed one up, the slow one goes downhill and it pulls the other one up. It's actually pulling it up, and it could lose its speed at the top. It'll gain angular momentum as the other one gets dragged back by the spring as it gains speed. And it works.
If you geometrically trace this on paper, you can actually see that you're right. The center of gravity moves straight while the others would move in space.
It took about 12 years for us to figure this out. When it went to Dundee University, there's a guy there, Bill Ferrier, he's an expert in 3D laser holography. And he died before he got in there, so I never used it. If they'd gone in there, it had been all over and done with a week it went in, but because we'd have seen what I was doing. You can't, very hard. See, I got this thing out basically to show you if I have this running, you can see it, and it's level, you could never ever tell what the angular momentum in there is, because you don't know what the speed of the gyroscopes are. It's altering all the time. And it's only when it goes, it all goes, that's when it starts to go uphill. That's what precession is. It's no angular momentum left to hold it down, no centrifugal force left. It's that simple, but that's not what they tell you. That's not what Mr. Euler said. So really, I can say, because I'm not a professional, that Newton's laws are bunk.
Oh, yeah, definitely, for sure. I mean, it just took people creative enough to figure out
I can
how
say
to
it.
do
I'm no
it.
professor. I wouldn't lose my job. But
Well,
I can prove it. I can prove it anytime you like.
Well, that's what we
Mark was
needed.
on about it.
Yeah.
He's the guy. He'll prove it.
Yeah, we've needed people that are just down to earth guys that just do it. That just get their hands dirty. They don't sit on chalkboards all day. They actually get out there in the garage and work.
The unfortunate thing was that the machine that went through the lab test in Australia worked for a totally different set of reasons. And that was what threw me. Both gyros went in and out at the same time, but it still delivered and it gave me the lab test. But Strachan's machine was the same. But as Ron Evans will tell you, Strachan's machine vibrated like hell. It was very hard to discern what it was actually doing. But it was built on the same principle.
Yeah, I think you're right. You're going to have to get it up to some really higher RPMs one day. Build it stronger.
No, I think a wee bit cunning design will do a lot better than that.
Yeah, you got to build it really strong, like outrageously strong, and then.
I don't think so. I think you can be clever. There's other ways. I mean, you're just assuming it's a gyroscope. What does a gyroscope do? Find out what it does and alter it.
Well, it's great. You're one of the most. You're one of the guys that everyone follows in this area. So.
Oh well, I had to get on here before I snuffed it.
Okay. Well, thanks again, Ross. So, so let me ask who else has questions for Sandy. And would you guys like to raise your hand in chat, or I see a bunch of discussions in chat, but I'm not sure who else actually has questions. Okay. Jeremiah, let me go to Jeremiah and then William Gregory after that.
Yeah, one last question, and that is thinking about the fundamental effect that's going on here, where you're taking advantage of shifting your center of mass and losing angular momentum, or you're able to precess much more easily as a result of the angular momentum stored along a certain axis. And I'm assuming that only works along that axis. You couldn't say, move it forwards and backwards. If it was a disk, you couldn't say gain any advantage if it was already spinning by moving it like this.
No, none.
Or by moving it like this. But if you try to move it like this,
it's got to be twisted.
It's an advantage, right? You get an advantage basically when you rotate it like this. Yeah. But along any other axes like this or like this, you don't get any advantage.
Do nothing.
Okay, so that was the big secret that needed to be defined and clarified. I think I just wanted to verify with a physical example, so my brain can grasp it because I'm a visual learner in that sense. Well, I guess a lot of people think they're visual learners. Whatever. Thanks. That really helps. That really helps me understand what's going on here and how to take advantage of this effect. So what I really wanted to ask you is, gyroscopes are a physical demonstration that we can see with our eyes, and they're great for the principle to be, shown. But atomically, we should be able to do this solid state with with making individual atoms precessed, or electron valences precessed, or doing something else that doesn't require the physical motion of gyroscopes. Even say, Ron Kita has a patent about a material that happens to have these Chiro molecules that have well, they're almost superconducting gyroscopes. They're little chains of charge that are bound together, and they can just keep on rotating around these clusters of atoms in free space, and they can do so uninterrupted. So there's another way of maybe we could do it with a solid state material, and we wouldn't need gyroscopes, we wouldn't need moving parts or arms or mechanics or anything. What do you think about that?
I think it could be done electrically, but I'm a mechanical engineer. I'm a tool maker. That's my limit.
Well, I hear you. But thinking of what you've started, and then imagining what you've done here 100 years into the future, would you like to see it become a solid state device that has no parts that can ever break down?
That's quite a question. I maybe like to see it, but what is required to do it?
That is the question, indeed, for the engineer to figure this out and play around with materials and spend.
I see people with little things flying around, and unfortunately they're attached to the ground. I worry. If the power plant is in the unit and it's going up, then okay, I'll consider it. But I think I saw Mr. Ventura there the other night discussing with somebody, and he was very unhappy about a tether on the bottom of the device.
Yeah, and I can't say that I'm particularly a fan of it either, but I understand the necessity for it in the design. And even
okay.
I don't have a better solution for you, so I'm not going to say anything bad about it. And I don't know what else to tell you as far as what you could use instead. So until such time as I have a solution.
Well, you see, I used to use motors, little oily, smoky, lovely glow plug engines. And they messed up everything. The belts were continually covered in oil. So when I came back from Australia, I thought, well, from now on, it's going to be electrical, and it's going to be radio control. And that's the way I've gone ever since. And it's a lot easier, but you can put a LiPo battery on, and away you go. I mean, no problem. I couldn't do that then.
And come on, David Mathis, of course you can do it with no moving parts. NMR, EPR, and DNO already are 3 examples of doing that. So yeah, definitely possible. We just have to figure out how to do it the right way, and how we, exactly what motions need to be made, and how we can slow down and speed up the amount of energy stored in the valence bands. So there are ways, to do that. You add photons, and you're going to increase the energy of the electron valence band, especially if it's storing, partial energy of a photon and it hasn't released the next one. Theoretically, energy state should be higher. So everybody wants to argue about its quantization level, and there are these substates too between transition bands. So something we need to consider. That is energy that we can utilize, and it should change the precessional momentum of an atom's electron valence cloud. So I think it's possible. I do. I think it's totally possible.
Well, let me.
Thanks. I'm sorry. I'm done.
Oh yeah, so let me go to William Gregory, and we're ahead of schedule. So maybe like next week, maybe I'll sneak in with a UAP update again if you guys are open to it. But let me go to William Gregory first, sir.
Oh, okay, I'm unmuted now. Okay, hey, great presentation. I'm really enjoying this. This is more my speed. I'm not a scientist. I'll make that statement again. I make a lot of mistakes, but everybody's so good to explain to me where I went wrong, and I learn a lot, because to fail, I wrote a little note here, to fail is really like the back door to success. So one of the things I did, I put a motor in the center of the device, and I put 2 motors on each side of that motor with a cross member connecting them. And so I turned on the disk. It sort of looks like your machine, the reason I'm bringing this up. And so they were all spinning the same direction, clockwise. Let's say they're all spinning clockwise. And the outside disk had an angle of about 45 degrees, or not even quite 40, about 30 degrees. And as I spun the center motor faster, The only thing that happened was my two outside motors spinning those discs on the outside, they just flattened out. So it just became like like one disc in the same plane. So I had all these ideas. Like I said, I'm not a scientist, so some of these ideas might be, well, they're just theoretical. We'll put it that way. Is that when the disc is spinning in towards the axis of the main axis, the particles on the disc, on that side of the disc, are actually moving. Seems like they're moving slower as compared to the particles on the other half of the disc that are on the outside of the orbit on that disc. There's a lot of ways you can spin those discs. You can spin one clockwise, one counterclockwise, both of them clockwise, all three of them clockwise. Do you have anything that you could give me to help me find whether they should all spin the same way, or the center disc the center motor should spin the opposite way? What do you think?
Everything I've done, the gyro has always rotated, looking from the outside in the same direction. Like if the device is rotating anti-clockwise, the gyros will rotate anti-clockwise from the outside. That forces the gyro to precess or try to turn the torque up the way. If you do it the other way, it'll just get heavier or appear to. You do the same if you're clockwise, the other one's clockwise, but they've all got to be in the same relative direction. Every device, every gyro on the outside of the rim will have to spin the same way, looking from the outside.
Oh, okay.
Oh, that may be wrong. That's the way I see it.
Okay, and then one other question. Since you've been doing this a long, long time, I'm sure you've probably run across this, because this is what I'm sort of working on at this particular time, is static unbalance on a wheel. If you have a wheel spinning and you have a static unbalance on it, that wants the disc to just pull right out of its housing because it's wobbling. And so my thought was, instead of having a static unbalance, if you could have a dynamic unbalance where somehow you could put weight on the outside of that spinning disc just momentarily, like for 180 degrees, or what they call 1 pi radian, and then make that weight disappear either by temperature change, in other words, making the weight appear and disappear on every half rotation. And then it would sort of, instead of wobbling, you'd get this effect that in free space, it would want to do like a chop wave or a cup wave acceleration. Have you know what I'm talking about a static unbalance? Instead of having a static unbalance, have a dynamic unbalance without violating Newton's third law.
Forget that one. Go nowhere.
Well, I do have a workaround Newton's third law on that particular one, because to me, and I've got into arguments about this, about acceleration being a one-way street. Gravity is a one-way street. So if you could move a mass inside the spinning disk using only acceleration, could you possibly beat that equal and opposite reaction, Newton's third law?
To try it.
Does anybody want an answer to the mechanical, how to get past these imbalances? In terms of, it's very, if you want to proceed without wasting much time, when you spin a drum of water, it self-balances. Are you with me?
Yes.
There are a whole bunch of fluidic devices that run off of spinning fluids. And when you have, I'll give you an example. if you were to momentarily, we all know the specific gravity of water is 1. And if you have an ice cube, which is for all practical purposes, specific gravity is 1. If you throw it into a drum of spinning water, the drum will self-balance. Are you with me?
Yes.
If you pull the ice cube out quickly, it goes back into balance again. So what it is, the whole thing is to work with spinning fluids, have the eccentric match the specific gravity of the fluid. Pull it in and out. You can do it with a solenoid or anything. It will self-balance. And what happens is there's an equal and opposite reaction to the center axis of the thing that self-balances. And so in terms of dealing with mechanical things that can break, you have a very smooth running device. The only requirement is to put a mass into the fluid. As soon as you put the mass into the fluid with the same specific gravity, the dynamic does not recognize the material because it's of the same specific gravity. And you pull it out, it goes into dynamic balance. And if you get 2 of them together, clockwise and counterclockwise, you will get linear propulsion. That's it. So I'm out for the day, I think. So in terms of, but at the gyroscopes.com, there are a whole bunch of fluidic devices. A lot of them do not use the same specific gravity of the rotor, but you can use a fluid, but the combination of a solid and a self-balancing liquid will give you propulsion if you want to go to mechanical things. But that's all. So enjoy the day, guys.
Hey, thank you, Ron.
Doesn't look like Tim's around. Tim?
I don't know if no one else has a question for Remi, real quick.
Yes.
I do, have one more question for him. Would you be interested in working with us to try and take some of your concepts and experimentally test them? Because our expertise is mainly focused in turning ideas into experiments so that we can check some of these interesting theories to see if there's something to them, since they might just be, the new revolutionary physics we need to get to space with very little energy. So if, would you be interested if you're still around, Remi?
Oh, were you asking Remi? Remi actually had to leave. Yeah, because it's late UK time.
Yeah, I'll have to get a hold of Remi because I'm wondering, he's got a lot of interesting ideas and he's saying he's having problems implementing them into experiment, but that's kind of like what we like to do. So.
But you should ask Sandy as well, see.
Well, does Sandy have anything that he'd like us to test that he's having trouble testing himself?
just prove that Mr. Newton's wrong.
We are trying to do that, but we're trying to do it in a very different way. We're trying to do.
I'll give you a simple way to do it. Just rotate a mass and put strain gauges on the beam. You'll find out very, very quickly. Angular momentum will disappear. Newton says it doesn't. Well, Euler said it doesn't.
Yeah, we will have to try that because we do have a beam balance and we do have gyroscopes, so might as well.
Okay.
I'm sorry I goofed with my photographs, but the last machine I showed you was actually the last set was for a machine to go all the way up from zero gyro speed, to go right through the whole motion with strain gauges underneath showing you the losses and centrifugal forces that went. And it was all telemetry. It's been run, it's all telemetry. But you can have that one if you want.
Yeah, that would be the 2 gyros, almost like in the perfect center position so that you could decelerate them right dead center axes, somehow, instead of having them any other angle. Yeah.
Try the what I said, the free lunch experiment. And you put that together, you can go into space yourself, no bother.
Okay. Oh, sorry, Jeremy, I didn't mean to mute you out. So I think we're just about all set for now. Sandy, I think that was just about it, right? For Q&A, or?
Yep.
We do have extra time, but I was gonna, well, let me do this then. Let me put it on gallery view, and everyone please give Sandy Kidd an enormous hand.
But don't invite him to do it.
Well, again, thank you for presenting, Sandy. Yeah, it looked like questions had to kind of wound down to nothing. So let me meet you out then. And I guess the first thing I should ask is, we do have Mike Gamble scheduled for 4. I do have a UAP presentation that I can do. We have Frank Milburn, who joined us as well. I guess the question is, would you guys like Mike? Let's ask Mike if he would like to go now. Mike, would you like to present now, or would you like me to do a brief UAP thing first?
Go right ahead. I'm interested in watching the UAP.
Oh, okay. If you're up for it, I just didn't want to.
No problem. If you want, I can go right now, but I'd just soon watch the UAP.
Okay. I just didn't want to be disrespectful at all. Well, let me do that then. And we do have Frank in the house, and I will pester him for updates as well. Here, let me launch my presentation then. Okay, and I'll do full screen. And I believe that's the one that we want. Yep, UAP news update. Okay, and hopefully you guys can see the screen okay. I'm guessing everybody can. I'm not seeing any complaints. So, okay, so this is basically just kind of a new UAP news update. The reason I put this together was I had good feedback on the one from last week, and the news on this is just coming fast and furious. So I wanted to try and kind of wrap up everything I have seen over the last couple of weeks, as well as some of the older stuff. So UAPs are real. Starting out, UAP reported probably do represent physical objects, given that the majority of UAP were registered across multiple sensors to include radar, infrared, electro-optical, weapon seekers, and visual observation. And 144 reports originated from US government sources. Of these, 80 reports involved observation with multiple sensors. We were able to identify one reported UAP with high confidence. So again, these came from the Office of the Director of National Intelligence UAP report. I just kind of wanted to start out with that. So I think pretty much the entire world has agreed now that UAP are real, or UAPs, because I'm a little sloppy with my English. They're real, we're not sure what they are. UAP performance can't be explained. Estimated accelerations range from almost 100 G to thousands of Gs, with no observed air disturbance, no sonic booms, and no evidence of excessive heat commensurate with even the minimalist estimated energies. The number and quality of witnesses, the variety of roles they played in the encounters, and the equipment used to track and record the craft favor the latter hypothesis that these are indeed technologically advanced craft. Furthermore, these craft appear to violate the laws of physics in that they don't have flight or control surfaces, any means of visible propulsion, apparently violating Newton's third law, and can operate in multiple media such as space, low Earth orbit, air, and water without apparent hindrance, sonic booms, or heat dumps. That was from Kevin Newth, Robert Powell, and Peter Reale. Again, that's the SCU, and so they were doing basically acceleration analysis and performance analysis on this. UAPs exhibit stealth. The F-18s couldn't obtain lock with their radars because they were stealthy, but the forward-looking infrared radar could pick them up to some degree based on their heat signatures. The advanced aerospace vehicle appeared to demonstrate advanced acceleration, aerodynamic, and propulsion capabilities beyond anything that we knew existed on this planet. That's from Hal Puthoff in a paper he published, I think, back in 2019 on this. The UAPTF holds a small amount of data that appear to show UAP demonstrating acceleration or a degree of signature management. And that's, again, from the UAP report that came out on June 25th. So we've got two different indicators of stealth from scientific sources. UAPs exhibit relativistic effects. There's a group of thinkers in the field of UFOs that point out that phenomena reported around some UFOs do, in fact, look exactly like general relativity effects. The idea that somebody has figured out how to manipulate space-time on a local scale with a low-energy approach would explain a lot of things across the UFO phenomena. That's from Larry Lemke. That was an interview that he did recently. Now, this from Thor on the UAP theory site, we can see the background behind the object and look for the following effects: gravitational lensing of the background around the UAP, apparent shape-shifting of the UAP whenever it maneuvers due to changes in the distortion field, unimpeded motion through water, and partial invisibility. So again, that was looking at the Puerto Rico sighting UAP video. And then finally, I found this online by our very own Michael Boyd, who said, I observed a dark torus-shaped balloon rotating counterclockwise above the UAP that appears cooler on IR than the other regions. Also, I observed a large dark region to the left of the UAP and a small dark oval-shaped balloon rotating to the right and below the UAP. And that's something Michael has described several times. And so we've had him on and he's described that in a few different sessions. UAPs aren't Chinese or Russian. This is obviously a contentious point, but China has well-documented issues with basic jet engines. They rely on espionage to develop their most advanced weapon systems. So I struggle with China having developed this. That's from Marieke von Rennenkampf. Russia has a defense budget that is a fraction of the United States, and much of its military infrastructure is crumbling, so I struggle with that too. Again, he was quoted in The Guardian as saying that. And then again, Luis Elizondo had said, we're pretty confident that it's not Russian or Chinese technology. Again, these are contentious points. Some people say it is, other people say it's foreign, but human, but unspecified. So it depends who you're talking to. UAPs may be extraterrestrial. This is another hypothesis. The observed flight characteristics of these craft are consistent with the flight characteristics required for interstellar travel. I.e., if these observed accelerations were sustainable in space, then these craft could easily reach relativistic speeds within a matter of minutes to hours and cover interstellar distances in a matter of days to weeks proper time. Again, that was Knuth, Powell, and Reale with the SCU in their performance analysis paper. Former CIA Director John Brennan said, some of the phenomena that we're going to be seeing continues to be unexplained and might in fact be some kind of phenomena that is the result of something we don't yet understand and could involve some type of activity that some might say constitutes a different form of life. So that's probably about as close as you're going to get to extraterrestrial from the US government, at least right now, but that's pretty darn close. UAPs may be a threat. Incursions into our training ranges in designated airspace pose safety of flight and operation security concerns and may pose national security challenges. DoD takes reports of incursions by any aerial object, identified or unidentified, very seriously. That was from John Kirby at the Pentagon, and that came out right around when they unveiled the UAP report. A group of senior American politicians have warned that UFOs pose national security concerns after getting a confidential briefing. Clearly, something's going on that we can't handle, said Tim Burchett, Republican congressman from Tennessee. So again, that was about the classified briefing that I have no direct knowledge of yet, but there were some quotes about it from various lawmakers after they were briefed. We take the issue of unexplained aerial phenomena seriously to the extent that we're dealing with the safety and security of US military personnel or the national security interests of the United States. So we want to know what we're dealing with, said Representative Sean Patrick Maloney of New York. That was in the New York Post. Okay, so UAPs have a nuclear interest. This is well documented, not very well understood. As I've reported, the Navy is front and center here for a simple reason. Its nuclear platforms keep attracting UFOs. UFOs tend, since the late 1940s, to appear near military nuclear weapons sites and nuclear-powered platforms, such as the Navy's aircraft carriers and submarine forces. The potential threat here is that the UFOs can detect and intercept these platforms on land, on sea, or undersea, and with impunity. That was Tom Rogan in the Washington Examiner. And then Luis Elizondo said that UAPs have been observed at US nuclear sites as well as at sites all over the globe. There does seem to be some sort of congruency or some sort of intersection between these UAP or UFO sightings and our nuclear technology, whether it's nuclear propulsion, power and generation, or nuclear weapon systems. Furthermore, those same observations have been made overseas in other countries. They too have had the same incidents. So that tells us this is a global issue. Now, in this country, we've had incidents where these UAPs have interfered with and actually brought offline our nuclear capabilities. So he was quoted as saying that in the Washington Post. I put a little bit more in here because UAP nuclear intent is concerning. I'll just kind of leave it there because we don't know exactly what's going on. On October 4th, 82, near the Ukrainian town of Byalokorovich, when a disc-shaped UFO apparently hovered over a nuclear missile base for an extended period of time. At one point during the encounter, a number of nuclear missiles suddenly activated without authorization from Moscow or any action being taken by the missile launch officers and were preparing to launch. So that's one documented instance a little bit further back in history. At a US Air Force base in Minot, North Dakota, on October 24th, 1968, an object was sighted in the sky above a number of Minuteman missile silos. As the object flew over the silos, the electronic consoles at the launch console facility began acting strangely. At one point, crew members had to hit the inhibit switch because a launch in progress indicator had inexplicably been activated. When the flying object disappeared, the consoles reset to normal. That was from Robert Hastings, who has done a lot online. He's actually published many blogs and articles on UFOs and nuclear weapons and the intersection there. And then, of course, he is with us, and we'll pester him to speak in a moment. One particularly alarming claim concerns the destruction and flight of an ICM by a UFO. Another serious consideration is the possibility of accidental nuclear war through misinterpretation of UFO data by our very own Frank Milburn, who is also with the SCU. Okay, so just some of the recent political headlines, and I should apologize for the background noise. Senator Rubio calls it a defense issue. Men and women we have entrusted with the defense of our country are reporting encounters with unidentified aircraft with superior capabilities, Rubio told Fox News. We cannot allow the stigma of UFOs to keep us from seriously investigating this. The facts are that there are things flying over our military installations. They don't belong to us. They seem to evidence some sort of technological advancement that we don't have and have never seen. So that was on Fox News. That was where that was reported. Senator Reid calls it a defense issue. For the record, Senator Reid has blamed this on Russia. If you choose to believe that, that is on you. I may differ, but Mr. Reid said UFOs were something that cannot be ignored and insisted that Joe Biden take the issue seriously and sit down for a briefing. I believe that there should be an ongoing entity within the Pentagon would be the best place for it, whose sole job is to stay on top of the issue of UFOs, Mr. Reid said. The federal government no longer, including people at the Pentagon, no longer criticize or harass or stop promotions of people who report on these occurrences. And that was cited in The Independent. So again, he has said that he believes it's Russia, but he also feels that it should be thoroughly investigated. This is recent. This is after the June 25th UAP report. This is brand new. Representative Carson wants UAP hearings. Democratic Congressman Andre Carson, who chairs the Subcommittee on Counterintelligence and Counterproliferation on the House Intelligence Committee, said that it is his hope there will be a series of hearings, including one that is public, in the very near future. He said, the report is inconclusive. What we do know is that there have been nearly 150 sightings, 80 of those sightings have been detected with some of the best technology the world has ever seen, Carson said, and we can't rule out something that's otherworldly, but that's a very small percentage. So he was quoted on CBS News, and again, that's only a few days old. That's a new news item. Some of the other things you may have missed these, UAPs in the news. NASA is studying UAPs. NASA's new chief is setting up an effort to further study unidentified flying objects within his first month in office. Bill Nelson, the former Florida senator and spaceflight veteran, told CNN Business Rachel Crane, "We don't know if it's extraterrestrial. We don't know if it's an enemy. We don't know if it's an optical phenomena. We don't think it's an optical phenomena because of the characteristics that those Navy jet pilots described. And so the bottom line is, we want to know." Nelson did not establish a formal task force to begin investigating UFOs in NASA. However, he did direct researchers to move forward with exploring any lines of questioning around the topic as they see fit. So that was CNN. The Pentagon is studying UAPs, or I should say they're continuing their study. The Pentagon plans to formalize the study of UFOs following the release of the report from the Director of National Intelligence on the subject called the Unidentified Aerial Phenomena. Okay. In a memo from Deputy Secretary Kathleen Hicks, she instructed the Office of the Undersecretary of Defense for Intelligence and Security to create a formal mission for the work currently done by the UAP task force. Hicks framed it as a question of national security, stating, "It is critical that the United States maintain operation security and safety at DoD ranges," noting that many of the observations have been near military areas. So they're going to formalize the UAP task force that created that report that was released on June 25th. That's kind of the long and the short of that. The DoD is also expanding their scope of study. The report confirmed that the scope of UAP activity expands significantly beyond the purview of the Secretary of the Navy, who heads the UAP task force. Okay, so they're expanding out of just Navy oversight for it. And again, Kathleen Hicks had written, "I direct the Office of the Undersecretary of Defense for Intelligence and Security to develop a plan to formalize the mission currently performed by the UAPTF." So it's official. They're going to make it bigger. They're going to expand their scope. They're going to do more research. China is studying UAPs. This made headlines probably last month. They kind of snuck this in before the June 25th report. The People's Liberation Army calls them unidentified air conditions, and artificial intelligence is the best way to keep up with them, they believe. Chinese researchers confirm that sighting reports from across the country are on the rise, but they think aliens are unlikely to be responsible. According to Wuhan-based researcher Chen Li from the Air Force Early Warning Academy, human analysts have been overwhelmed in recent years by the rapidly mounting sighting reports from a wide range of military and civilian sources. The frequent occurrence of unidentified air conditions, again UAPs, in recent years brings severe challenges to air defense security in our country, said Chen in a 2019 report to a conference of senior information technology analysts. The PLA's task force, dedicated to the unknown objects, increasingly relies on AI technology to analyze its data, according to Chen's report, which is in line with several other military studies published in domestic journals, most recently in August last year. That was in the South China Morning Post. So China is also doing study, and other nations are working on this as well. And in fact, the next one here, I'm going to get into Gaipan probably in our next meeting. Other nations studying UAPs. Japanese news agencies reported in September 2020 that Japan's Defense Minister Taro Kono has requested the self-defense forces follow new protocols regarding possible interactions or sightings of unidentified flying objects, which might pose a threat to national security. So that was on Fox affiliate in Phoenix. So that's about Japanese investigation, which again made headlines a couple of months ago. Gaipan is a part of the French space agency studying UFOs since 1977. They've been doing this a long time. Of the 2,923 cases studied, 3.4% remained unexplained. And again, I'll drill down more on what they did in the future. They just published a large report on this as well, but I wanted to get those numbers out there. So again, they're pushing 3,000 cases. About 3.5% are completely unexplained. Russia's Institute 22 organization was created back in 1978 by the Academy of Sciences and the Ministry of Defense in the Soviet Union. Institute 22 investigated around 3,000 UFO reports. About 5 to 10% of all cases remained unexplained when the organization dissolved. And that was cited through Wikipedia. So Institute 22 is now long gone, and there was some controversy at the time that they might have been using UFO reports to cover up Soviet missile testing. But nonetheless, we've got close to 3,000 reports, and 5 to 10% of all cases were unexplained. So that's what I had for mine. And here, I'll stop my screen share. And let me bring Frank on and see. I'll ask Frank to unmute. Frank, are you with us?
I am here.
Thank you. Welcome back, sir. Welcome back. Thank you for joining us. And do you have any updates on what's been going on the last couple of weeks? Because I know it's been hot and heavy with the UAP news.
Yeah, to be honest, I've kind of been focused on that. I have been looking further, doing research on the power plant for the Chinese Chengdu, the J-20, which is their supposed 5th gen aircraft. And basically the Chinese, they're still trying to buy, they want to get hold of the Russian Sukhoi, the Su-57, because they want the engines out of that and the radar system. The Chinese are basically in the Chengdu, they call it a 5th gen, but it's still got a 1980s era power plant that they developed. They managed to get hold of an engine basically before an arms embargo was slapped on them. They've been trying to develop this sort of 80s technology. So they've got a 5th gen, what they call a 5th gen jet with an 80s engine in it. So they've been trying to get hold of Russian engines, which the Russians don't want to sell to them. They've been trying to buy from, trying to purchase actually a Ukrainian aero engine company, which the Americans and the Ukrainians have blocked thus far, because that would be a sort of a legacy manufacturer of what was former Soviet kit, but basically has the expertise to build the kind of engines that the Chinese want. So that kind of tells me that they don't have sort of 5 observable, beyond next generation tech, because they're still messing around with 1980s engines for their 5th generation fighter. And you could even go further and say that they're trying to buy kind of like a more 4th gen jets. Sorry, my cat's just attacking everything. They're still trying to buy more 4th gen fighters, rather like the Americans are with the F-15X, because the Chinese realize that they're having problems with their 5th gen fighter and they still haven't sorted out the engine issue. So better to get something with a more reliable engine.
Awesome. Okay. So is that everything that you have, or has there been more going on?
No, to be honest. I mean, I've been really focused on the doing my sort of reply and analysis to the preliminary assessment that came out. So that's what I've been focused on.
Oh no, that's totally cool. Yeah, well, I appreciate you joining us. It's good to see you back. It's good to have you kind of update us on that. Yeah. So I guess, let me see. We still have a few more minutes. I guess I'll ask. Does anybody have any questions on kind of the presentation?
I think Michael Boyd has his hand up.
Oh, does he? Wait.
So I just curious if you saw that that video I sent you from Stephen Greer.
Yes.
I thought it was kind of curious that they're basically, my understanding is he's alleging that it's a conspiracy by the defense establishment to create a scare of a UFO invasion as a pretext for putting nukes in space. would that be a fair assessment in your mind of what he's trying to say there?
Frank, do you want to take that, or should I?
I watched that video actually twice. He's not saying that this is what's happened. He's saying this is what's going to happen. So I guess we're going to have to wait and see.
Yeah.
So
I actually missed the question. Sorry, what was the question?
Oh, no, that's okay. Well, so Michael was wondering whether Stephen Greer's Cosmic Conspiracy, right, which was just released, whether that's going to basically, whether the US government is using UAPs as a pretext to put nukes in space.
Well, what a load of crap. Why would they need to use the pretext of aliens? I mean, they've already got, China and Russia and potentially, Iran, because the Joint Comprehensive Plan of Action, even if they get that, the failed nuclear deal with Iran up and running again, that's not going to stop the Iranians going after nukes, and they've, got space ambitions as well. So I don't think they need to have, aliens or some kind of cosmic threat when they've got enough terrestrial ones. And I don't have very little time for Greer. He did good work back in the day. He's basically become, in my humble opinion, a sort of a clueless conspiracy theory cretin and an utter charlatan. And he's on a par with that other creature, what's his name, Michael Salas, who, the one who's always going about UFOs and Antarctica, and that other bloke, Corey Good. I mean, they all just spout bullshit, basically.
Yeah. Well, I mean, I guess if I was going to weigh in on it, Michael, my thought would be, so I watched Cosmic Conspiracy 1.5 times. I don't think I've caught up to Mark on it yet, but my gut feeling is that that Greer and his organization, right, have had a narrative that goes back. I mean, this goes back to, I think, the 90s. I used to listen to him on Coast to Coast AM. And they've had a narrative that has kind of been unchallenged because the government has been silent on this. And now that the government is starting to open up and say, hey, we have a problem, something's going on, it kind of threatens the Greer narrative, which I think has been shaped in part by, the conspiracy community and just, I mean, a lot of the fears and uncertainties and anxiety that's out there. And so what I kind of picked up, I guess I picked up two things from Cosmic Conspiracy. One of them was it seemed like it was kind of an attempt to control the narrative, right? They're saying, no, it's our story that's correct. The government is not correct, and here's why, because they're trying to, do this fake thing. So I think that was part of it. I think the other part was they seemed like they were speaking to kind of a larger, I mean, basically in many different ways over and over again, they were saying the government is lying, the government is lying. And I guess just my thought was, I'm not going to say that it was wrong. It just seemed like it would maybe fit better in a broader context, right? Because there are a lot of different social groups out there who echo the same thing. So it's not just him that's saying the government is lying. It's like, you can take a look at whatever group you want, and everybody seems to have the same complaint. So it seemed like that was just kind of echoing, I guess, a larger concern about truth and transparency in government.
Well,
can I just sorry, go ahead.
I observed was this. He was mentioning this friend of mine. His name's Daniel Sheehan, and he's attorney for Elizondo. So it was like I felt cognitive dissonance because he was putting it in the context that why would he be representing someone like that? I thought to myself, well, I just got this. I got a Twitter yesterday evening from Daniel Sheehan, and he's basically, this is what he says. He says, on April 24th of this year, in my capacity as the 2001 General Counsel to the May 10th, 2001 Disclosure Project event at the National Press Club in Washington, D.C., I attended in Scottsdale, Arizona, the 20th anniversary gathering of many of the principals who organized the 2001 event. At that time, I granted an interview reflecting on the progress that I believe had been made since 2001 in bringing forward the cause of getting our American public and our American policymakers to take seriously the fact that UFOs are real, and that the most probable origin of many of these UFOs is indeed some extraterrestrial planet, very likely from elsewhere in our own Milky Way galaxy. During that interview, I was asked if I believed there existed some extra constitutional group of people who possess a substantial amount of information about these UFOs and about the likelihood that the origin of many of these UFOs was extraterrestrial. In response, by providing a lengthy explanation of why I believe that there has been and still presently is indeed such an extra constitutional group restricting access to this knowledge. And I explained further that I suspected that it was likely members of the same group were responsible for secreting other important information and activities from the American people and from our democratically elected congressional and executive branch officials. Unfortunately, this part of my interview was extracted from what I understood to have been the 20th anniversary documentary about the 2001 disclosure event. And it was inserted into a documentary film dedicated to promulgating what I expressly stated in that interview was, in my judgment, an incorrect theory on the part of Dr. Stephen Greer, the founder of the Disclosure Project, with which I most emphatically disagreed. Moreover, that portion of my 20th anniversary interview, in which I criticized what I believed was an unconstitutional cabal, as I referred to it, was spliced into the midst of a later recorded interview of Dr. Greer, in which Dr. Greer was aggressively attacking Mr. Lou Elizondo, the former director of the entirely constitutional, congressionally authorized Advanced Aerospace Threat Identification Project, who I happened to legally represent, and attacked Mr. Chris Mellon, the former entirely constitutionally authorized Assistant Secretary of Defense for Intelligence for both President Clinton and President George Bush. Chris Mellon being the man whom I personally greatly respect for the courage he has displayed in joining with my client, Lou Elizondo, to move forward the strategic objective of revealing government information, authoritatively verifying A, that a significant percentage of reliable reporting sightings of US over the past decades are in fact real physical vehicles, and B, that the most likely origin of these real UFOs is extraterrestrial. I am issuing this official public statement to make it unequivocally clear that I do not agree with Stephen Greer's theory that the recent confirmation by our U.S. Defense Department that a clear majority of the 2004 to 2017 reports of UFO are real physical vehicles is part of some secret plan on the part of our national security state bureaucracy to stage an imminent false flag, fake alien invasion. Nor do I agree with Dr. Stephen Greer's public assessment that either Lou Elizondo or Chris Mellon are part of such a covert plan. I instead am firmly convinced that both Lou Elizondo and Chris Mellon are engaged in an entirely good faith effort to expose the fact that some members of our United States government are in possession of information that reveals not only the UFOs are real, but a significant majority of the experts within our United States government are briefed in on a significant portion of the information that our government agencies possess regarding UFO or UAP phenomena, hold a good faith and well-founded belief that a substantial portion of the reliable reported sightings of UFOs are indeed off-world vehicles of an extraterrestrial origin. he goes on. Do you want me to go ahead and finish reading? It's only about.
Oh, I don't know. It's up to you. Do you need some water? That was a lot to do.
I know,
do all
it's a
at
lot
once.
to digest, and I expressly stated my disagreement with Dr. Greer's representations to the contrary in my April 24th interview. But this statement was edited out of my interview. And what I said about the cabal that is secreting this information was inserted into Dr. Greer's attack on Lou Elizondo and Chris Mellon. That made it look like I was attributing them some role in Dr. Greer's projected planned fake alien invasion. I want it made clear that I am expressly publicly disagreeing with Dr. Greer's characterization of Lou Elizondo and Chris Mellon. And I'm publicly stating that my statements of April 24th, 2021 made about an entirely different unconstitutional cabal was placed out of context in that documentary film entitled The Great Hoax, which gave the false impression that I was indicating that I believed that my own client, Lou Elizondo, as well as Mr. Christopher Mellon, were privy to and part of such an unconstitutional conspiracy. They are not.
Okay.
That's it. But I wanted to share that. I thought that.
No, and I appreciate you reading it. I appreciate you reading it. We did have somebody who mentioned they could read it themselves faster, but then at the same time, we're putting it up on YouTube. So it's good to, it's good to have it kind of recorded. Yeah, I mean,
it's pretty. So I'm basically when we do the open thing,
it's infighting in their community, right? Kind of.
We do it later after all the presenters. We do that open thing. I have put together a little presentation on what I call intergenerational trauma. That's what I think is the root cause of all this violence. It's our culture. It's part of our culture, and it's a cultural issue we're dealing with. And I want to, like I tried to explain for nonviolent communication, I want to get to the root cause of this.
Yeah.
And so later I'd like the opportunity to present that if it's okay.
Okay. Frank, you have your hand up again. Wait.
Yeah, I was just going to.
Okay.
Yeah, I was just going to hang on. Let's just put my hand down. There we go. Oh no, I put it up again. Yeah, I was just going to say quickly about Greer. I mean, the bloke is a self-obsessed narcissist on a par with that criminal fugitive Assange. He wants, like, was it $10 for an app for his CE5? And then, according to my friend and colleague Tom Rogan at the Washington Examiner, he wrote a piece back in July 31, 2020. Did Stephen Greer fake a UFO with flares? Right? So Tom was tracking aircraft in the area and saying, well, were flares being dropped to induce people to think that they were having some kind of experience with extraterrestrials? I mean, the other point I wanted to bring up was, yeah, sure, the government knows more than they're telling us about UAP. That seems pretty self-evident. The CIA and the Air Force, CIA were absent from the preliminary assessment. The Air Force, if you read between the lines, they kind of weren't being very helpful at all. But you have to ask yourself, okay, so the government has a conspiracy to keep the UFO truth from you. So why are you reliant on the government to tell you what's really going on? Does not anybody see that as ironic? That's all I wanted to say.
Yeah. Well, so I think that's probably just about it for us for our news update. And so, Frank, thank you for joining us, sir. I sincerely appreciate it. Okay, so everybody, let me see. Since Frank is exiting, why don't we do this? I'm not going to ask you guys to applaud me, but why don't we go to Mike Gamble? Thank you, Michael. Mike, are you ready, sir?
Well, yes and no. I'd like to comment a little bit on your pitch.
Oh, go for it.
I got time here. This is only about a half-hour presentation. Instead of checking with the Russians and the Chinese, you ought to check with the Germans.
Oh, okay. I'll dig. I'll see if I can find reports from them. They're probably studying it.
Well, they not only studied it, they built them back in World War II. They were known as the Foo Fighters of World War II.
Well, yeah, but I mean, they've changed governments a few times since then. So
Well, that's true. However, I have reverse analyzed one of those machines, and it is flight worthy.
oh, okay, okay.
And if you listen to what Dr. Von Braun said when he was asked that question, he says, "Yeah, we had a little help."
I'm trying to think of which one. I'm trying to think of who in our audience here knows about. I mean, because I know they had one with 4 engines, right? Didn't they have one with 4 turbines?
Well, yeah, they've had those, but they also had one. It's called a Hannibal. It's EM drive.
Yeah. See, and I've heard of them. I've even seen some photos, right, that are purported photos, but I've never seen how it was supposed to work. I don't think. Those weren't inertial though. That was EM, you were saying.
That was EM drive, yes.
Well, could be. That, I don't know. That would be a difficult one to accept
well,
on an emotional level, but
it's been over 50 years ago.
Well, no, I don't mean that they built
1940.
it. Yeah, I mean it would be difficult to accept that today's UAPs are related to the Nazis. I would struggle with that. I don't know. I can't say no. I mean, we don't know what they are, but well, Mike, do you want to go ahead and present?
Sure.
I hope I didn't sound negative. I'm not trying to be negative. I'm not trying to be.
Hang around for my next pitch.
Okay. Well, I'm here, sir. Let me hand it over to you.
Yeah. Well, I got one more comment on this stuff. One of the other guys on here is Chris Munch. Anyway, he's got a good movie out on this very subject. It's called The 11th Green. I'll put in a plug for him.
Okay, look here. I'll put the link in chat. Yeah, and again, I wasn't trying to be pessimistic. It's just it's like we're mixing conspiracy theories now. UFOs and not. Yeah.
Well, true. Except I don't deal in theory. I deal in fact.
Oops. Okay. Here we go. I think I found it. So I will post that in there. Oh, and Rob posted to Iron Sky, which I've seen. So.
Yeah. Anyway, if you want to start talking about inertial propulsion, we can get started on that if I can figure out how to get this thing going there.
Oh, yeah. Yeah. Well, let me mute myself out. Thank you again also for joining us and presenting on this. I think this is number 3. You actually have 4 different presentations.
Yeah, I got a whole bunch of them on different subjects. Yes. Where's the button here? Slideshow. From the beginning. Oh, I forgot to push one button. Hang on, we got to back up. I got to hit screen share first. We'll try that again. Okay. Can you see that?
Yeah. Perfect.
Okay.
Perfect.
Okay, from the beginning. Oh, come on, there we go. Okay, I think we got it going here. Okay, won't worry about the introduction. I think everybody knows me. I'm retired from Boeing, and when I was there, I did quite a bit of work on their gyroscope systems there. And this is a pictorial of what's left of the system. I had a lot of trouble getting it out the door. The intellectual property guys went through the ceiling because I was releasing Boeing photographs, and they fine-tooth combed them, something about picture being worth 1,000 words. As some of you know, there's usually a good story behind most of my pitches. Oops, we did push too many buttons already. Let's try that again. Okay. Yeah, this presentation is non-technical. It's a history of Boeing's CMG work. And it started back in the early 60s and continued on into the 90s. I got involved with it in 1995 when I took over operations of the GNC lab. It's at the Kent Space Center there. And my lab there and the building it was in were trashed during the earthquake 2001, and these pictures are pretty much all that's left of it. This picture of the Kent facilities there with Mount Rainier in the background. On a historic note, the Apollo moon rocket, the first stage was designed and built here. Matter of fact, that tall building you see in the middle of the complex there was specially designed to house that thing because it's 80 foot tall. And then also the lunar rover was built and developed here in the GNC lab, but that's long before my time. When the building was trashed, and they found in one of the cubbyhole closets the prototype of the moon buggy there, and it's now on display at the Boeing's Museum of Flight. All the GNC work with the CMGs and that was all done at this facility. Starting off with the basic operating procedures before we dig into the details, a little short tutorial on gyro operation for people that are not familiar with them. Basically, a gyro has three vectors that control it. One is the spin vector, it's highlighted in red there. And then the torquer input, which is highlighted in green, and then the gyro's output vector, which is highlighted in blue. And they're all at 90 degrees or orthogonal. When you run the numbers, this makes the gyro's output force proportional to three things. One is the mass of the rotor, and then the speed of the rotor, and then the speed of the torquing. All those contribute to the output of the gyros. Now, the term scissoring I picked up from my boss. The correct technical term is actually differential or dual operation. But when you have two gyros operating in this mode, you can get linear force out of them, which everybody says you can't. The ground rules are you have to have two gyros that are equal, same spin, same mass, but you torque them in different directions. If you look at the torquer vectors here, the green one, this one's torqued one way and this one's torqued the other way. The blue is the output vectors and the red is the spin vectors. This particular model has a figure-8 belt that does the scissoring. The torquer motor is on the back side, so you can't see it. But this was a little demo model we had. So that makes the output vector 2 times the torquer rate plus the differential angle between them, assuming the rotor mass and RPM are the same. Now this scissoring operation, which I just mentioned there, it generates a sawtooth torquing rate. We use the term scissoring, which may or may not be correct. I'd say it's differential operation. What you do is you move them slow in one direction and fast in the other. And depending on whether it's fast together and slow apart, it generates a force. When you move it slow, you get a small force. And then when you move them fast, you get a large force. And that generates an average force. That's the principle behind the operation. Now we'll just dig into the pictures of what Boeing's had used over the years. They started with small test articles and they moved up to some pretty good sized ones. This is one of the first small ones around there. You can see 2 gyros here, and then there's a silver figure-8 band that does the scissoring. Torquer motor is not shown there, but that was one of the starting ones. A little electric motor, gyro operated, kind of like the ones we get from gyroscope.com. Another type that we used at Boeing was reaction wheels. These are about 6 or 8 inches in diameter, and they run in a vacuum can. The black color is a little difficult to see the thing, but I have an exploded view in the next picture. where you can see the motor with the rotor and the bearing and the vacuum can it sits in and electronics. And there's the thing just sitting together. And this is without the armature. They had quite a few gyros that we ran, different sizes and for different operations. This was the next bigger size. I call them a medium-sized gyro. They used quite a few of these around there. The flywheel is basically in the middle here. It sits in a vacuum can, and then the torquer motor and the sensors are on the end. And then we have these big fellows here. These are big Sperry gyros. These are the ones I worked on when I took over the lab. There was 4 of them on the test article. Your torquer motor is over here in blue. The power electronics is down here. And then the position sensor is over here. The red can you see is actually a vacuum can. The rotor inside there is about 2 foot in diameter. And Boeing Safety made us put these plexiglass bubbles on to protect your fingers. They're an absolute joke, because if that thing lets go, a 1/4 inch of plastic isn't going to stop it. However, Boeing Safety, what it is, they don't want to pinch your fingers. Side note there, my boss told me to take very good care of them because they were worth more than me. Approximate value is about $1 million a pop. And then also show you a few pictures of the GNC lab facilities through the years. This was when they were building the space room. It had an air pad in there for seismic isolation. It was 20 foot square, and it floated on 7 air cylinders. They were about 2 foot in diameter. 2 of them you can see in the picture. There was actually 7 of them that held it up. It was 20 foot square reinforced concrete. It weighed about 70,000 pounds. And it provided seismic isolation down to micro Gs. And then in the middle, there was a 4 foot post that had a, I call it a bowling ball sized air bearing on it. You'll see pictures of those later. Myself and another engineer happened to be standing on this air pad when the earthquake hit. And we didn't feel anything. It worked perfectly. It was only when the overhead crane started dancing that I knew something was wrong. This is a picture of the doorway going into the room there. When it was running, nobody was allowed in there because it was very dangerous. But this was our space room. You could look through that window there in the little peephole, and you didn't know any different than if you were looking through space. There were stars and sun and satellites and everything else in there. And we could simulate everything in there except for vacuum. You had to calculate air drag when you were doing the movements, but the chamber was EMI, thermal, optical, vibration, and acoustic shielded. So most of the stuff you could simulate except for air. And looking over here at the console, the controls on the left were for the air pad. Controls in the middle were for the air bearing, and the controls on the right side here were for the test article. Now there was a little 4 foot lip on the air pad so that we could mount measuring instruments. We got a theodolite here looking through the peephole. That's the same stuff surveyors use. So we could take measurements directly calibrated to the test article. Inside the chamber, we could position Helmholtz coils in there, anywhere from 1-dimensional, 2-dimensional, or 3-dimensional to generate magnetic fields around the test article to simulate space conditions. In one of the walls there of the chamber, we had the sun, what we call the sun simulator. The brightness and the number of lights lit and the focus of the lights could all be adjusted to simulate any distance from the sun. And you see it's a honeycomb assembly, and then in the center of each honeycomb is a light bulb, and the intensity and the distance in the filtering could all be adjusted. There was also star pattern lights. However, I don't have any pictures of them. if you're familiar with the Light Bright toy that kids use, where you poke little plastic things into a pattern to make stars, and then it's lit from behind. They were very similar to that, only industrial strength. Here's an oldie but moldies picture of the control room, dated about the early 70s. As you can see, all the data was collected on strip chart recorders. If you count them, there's 9 of them there. Not a PC in sight because they hadn't been invented yet. Taking a closer look at the test article, we'll show you a little bit about it. It had a sun sensor mounted on it, and that was look at the sun, or the simulated sun anyway. There was 4 sensors, and then they take differential readings, brightness and displacement, and that's used for navigation and control purposes. On top of the test article, they had a sun tracker, which did pretty much the same thing with the star patterns, only this worked more or less like a TV camera. It was a Vidicon tube. Figuring out the star patterns was a little more difficult than figuring out the sun. And then we had one antique machine here. That's the data acquisition. If you look up there, 16 bits address, 8-bit data. You could replace the whole kit and caboodle with one laptop right now. We use all the battery packs to keep this thing running as counterweights and ballast to balance it. And then we move on to the test articles that I've been using. This one is it's a circular one. You can only see one little gyro here. It had a whole bunch. There was about almost a dozen little gyros in there. A lot of electronics and battery packs. If you look at the guy's shirt and tie here, we got a white shirt and a tie, black and white picture, 260 Simpson voltmeter. So this places it very early 60s. Now take that test article and they put it in the black room there. There's a good picture of the air bearing. High pressure nitrogen comes up the hose, and there's a whole bunch of little holes in this bowling ball, and it floats on nitrogen gas, so there's zero friction. And then the pivot is allowed to move, and then the gyroscopes control the movement of the test article. Again, you got a black and white picture, white shirt, bow tie, so you're looking maybe mid-60s there. This picture here is of it operating. The arm here is locked, so it's not going to flop around, but they were testing the degrees of movement. It's a time-lapse picture, but you can see how it floats on the air bearing there, and then all the movement of the test article was controlled by the gyroscopes on board. This is another one that they had in there on the air pad. A little bit bigger system. This uses the medium sized gyros. There's 2 of them on this arm. There's a tripod here, and then the air bearing, the bowling ball sits up in here. It's counterbalanced by the data acquisition and all the battery packs. Again, you got a black and white picture, and she's got a mini skirt on, so we're looking at about late 60s. Okay, this one is another one back in the black room here. They're measuring degrees of freedom using protractors and pointers. You can see the sun simulator in the background, and then you got pointers and protractors for 2 axes of movement. Okay, this was another style. You come in there, you have there's 6 gyros. There's 3 on either end of the medium-sized gyros, and there's 3 back here. And this is the right side view. And again, you got a black and white picture. That hairdo puts it at about early 70s. Here we go. This is looking at the other side of the test article, a little bit closer view. You can see the electronics and all the battery packs stuffed all around there. And he's got the control box. Now we got a colored shirt and tie with lamb chops, so we're looking at 70s now. Okay, this is the same test article. You can see a little bit better view of the 3 gyros on this end. The back 3 are hidden. We have an antenna on this end, and he's now wearing a white lab coat, and we got colored pictures, so we're looking at late 70s. You can also see a picture of the overhead crane. It's a 2-ton crane, and that's like I said, I was standing on this pad, myself and another engineer, and when this thing started dancing around, that's when I knew there was trouble, but we didn't feel a thing. It compensated 100%. Now, this was the large test article that was in use when I came into the lab. It was used through the 80s and 90s. Our nickname for it was Old Bug Eyes, because if you looked at it from the front, it looked like the head of a fly. And you can see the sun simulator over here in the background. And that's the front view of it. And the next one, we have a rear view. This is the other 2 gyros back here. You can see the counterweights, a lot of the battery packs. And the batteries are being charged. You got the power leads in here and sun simulators in the background there. But if you notice the scratch marks on the floor, it didn't always behave properly. I told the boss, if you put a chair up on top of this thing, it would beat any mechanical bull in town, because it would whip around in circles, jump up and down and everything else. However, it was extremely dangerous because it didn't always obey commands and it would crash. One of the tests we had to do was when a satellite got out to geosync orbits on station keeping, it had to maintain a stable reference platform because you have an antenna from the previous pictures that had to stay at a certain orientation. So we developed this rig, put around it to do the inertial measurements. Now, this is the side view here. You had this balance beam that as this thing would maneuver, the balance beam had to stay perfectly level. It was in spite of the fact that if this went up and down or twisted sideways or whatever, this article, along with its sensors, had to maintain a fixed position. It had that simulated the antenna pointing of the satellites. And again, you see the scratch marks on the floor for obvious reasons when it didn't work quite well. And that's pretty much all the pictures I had through the years. This was the building as they were demolishing it. My lab sat in this corner here, and where this rust pile of junk is setting, that was setting right on the slab there. And the building next to it has also been demolished, and Amazon.com now has a big warehouse that sits through here. This is the 80-foot tall building that was specially built to test the first stage of the Apollo moon rocket. It's a one of a kind. And that's pretty much all I got. If you got any questions, we'll try and answer them.
Awesome. Well, let's
thing shut down here, offline here. Let's see, how do I do that?
You know what? I can do that for you. Here, let me stop sharing.
I was just gonna hit the button until you took it. Okay.
Oh yeah. Well, no, let me put it on gallery view. Everyone, give Mike a giant hand. A giant hand. It was a great presentation, Mike. Thank you, not just for that one, but for your many presentations.
We got a lot more if you're interested.
Yeah, well, I definitely appreciate you coming in and presenting for us, and that's amazing history too. It really is. It's amazing history. You know.
Yeah. Boeing wasn't the only one that was working with gyroscopes. All the satellites out there have these inertial propulsion systems on them, and including the space station has 4 big gyros on it for the same purpose.
Yeah. Well, let me see if anybody has questions. Does anybody have questions for Mike? I think it was pretty self-explanatory. So
well, yeah, like I said, it was non-technical. It was you know, well, just a history of what Boeing has done along those lines with gyroscopes.
Yeah. Well, maybe. Oh, okay. Michael Boyd has a question. Okay, go for it, sir.
So, did you guys get actual lift off of any of this, or you were just measuring forces?
No, it generates linear and torque both.
Oh,
the big test article will generate about 100, little over 100 pounds of force.
Wow.
The only problem is it weighs 1,500 pounds, so you're not going to blast off with it. However, once you get it out into space, the 1,500 pounds goes away, and you have a force generator of 100 pounds.
So, is it would you be able to build? So the heaviest part of the assembly is the gyros?
Not necessarily. The gyros are about 300 pounds a piece, and they generate about 100 pounds of force. The frame is probably another 500 or 600 pounds. The whole kit and caboodle, we had to use a 2-ton crane to lift it.
So how about if you made the assembly frame out of something else, like aluminum?
Well, that's what it was, but
oh, it was aluminum.
Yeah. Yes,
okay.
The frame was aluminum. The problem is the gyros, when you start torquing them, they generate a lot of twist that has to be sucked up by the frame. And if you don't have a very sturdy frame, it'll come apart. Gyros will tear it apart quite rapidly.
So you couldn't make a laminate or some kind of
well, your carbon fiber might have held up, but this one was aluminum. Like I said, it was built the early 80s. I got in on the tail end of it myself.
Carbon fiber, yeah, that one. Interesting. So, but then you show at the end they're like tearing it all down. Does that mean they stopped, or are they still?
Yeah. Well, the building got trashed in the earthquake. If you want the story on that,
oh, so that's what you were talking about when you said the thing was swinging back and forth. Is you were sitting on the air table?
I was on the air pad, and when the earthquake hit, and it remained perfectly stable, but the building is going up and down.
Okay, and the other question is, you had this like dark room that simulated the space.
Yes.
But it had everything but a vacuum.
Yep.
Was it? Was there any electrical, like EMF shielding or anything like that?
It was complete Faraday cage.
Did you have mu metal around it or something to keep out something like that? You know, when I used to do infrared detectors, they had this box called a mu metal box, and it would shield all the EMF up to 100 kilohertz, I think it was.
Yeah. This was basically steel panels in the wall, and under the floor there's a grid, and in the ceiling there was a grid, and your cell phone wouldn't work in there. It blocked out gigahertz, which is your cell phones.
Gotcha.
You had to crack the door in order to get the cell phone to work in there.
So okay, thanks for your answers.
Okay, let's go to, let me see, let's go to Mark Sokol next then.
Question, what they do for bearings? Was that a problem?
Well, we used air bearings. We had a bowling ball, well, it's about 10 inch in diameter. It had a whole bunch of little holes drilled on, I don't know, 1/4 inch or 1/8 inch pattern, like an air hockey table. And then we put 2,000 pounds of nitrogen up through there. And so there's zero friction. It held the 1,500 pounds.
Oh, I'm not talking about that. I'm talking about for the actual gyros themselves. There probably was a lot of torsion on the.
They had two big bearings on the end of them, and then the gimbals also had big bearings. There was a lot of force being generated when those things torqued.
I can imagine. I know this from personal experience. The bearings tend to go bad. If you're going to make a spacecraft using this type of device, you'd have to be sure that your bearings aren't going to go out.
Well, they had to replace one gyro on the space station here about 2-3 years ago. Bearings went out. Yes, that's the trouble with mechanical systems.
Okay, so there's no secret sauce there to the bearings, titanium or anything, or.
Well, actually nowadays you could probably use these ceramic bearings that they use like skate. What's amazing to me, they got these skateboards that do 70-80 miles an hour on about a 2 or 3 inch wheel. That thing's got to be pulling hellacious G forces, and they use ceramic bearings.
Well, those are for very low tension. We're dealing with torque, like.
Well, that too, but you got it. I mean, the gyros are spinning 20 grand, so you got high RPM to boot.
And you also have a lot of torque going on there. That's a major
hundreds of pounds.
Right.
Yeah. The ones that were in this thing, they were Torrington bearing, or not Torrington, Tinkham tapered bearings. They were tapered bearings, but they were specially built just for the high RPM. I don't know what that means, but they were very expensive because we had to replace a few of them.
Okay, so you ran into that problem yourself, not just the space station.
One of my duties was before we fired up for a test, I had to go around and make sure I had vacuum in all the cans. We started with a rough pump, and then we'd pump it down with an ion pump. Because you couldn't get them over 10 grand if there was any air in there. They'd just drag themselves down.
Oh, and Thomas Anderson's asking in the chat, what about magnetic bearings? Was that ever looked at?
Well, I don't think they existed at that time. Yeah, some of these new electromagnetic ones, like they, for your high-speed trains and that, I'm sure those would work. The torquing might be a problem. For handling the high speed spin, I don't think it would be a problem. But when you torque these things, it has to transfer a lot of torque through those bearings to the gimbals and then to the frame.
Well, let me go to Jeremy Reese. He's got his hand up. Jeremy?
Let me unmute here.
Wait, there
Can you hear me now?
Yeah, there you go, sir.
All right, so I got a couple questions. Ray Carr wants to know, why did you guys need to simulate the sun?
Well, the control system, we controlled off, it would go for certain star patterns and then sun intensity. All those were for orientation and station keeping. That's the biggest problem with the satellites up there, is they're not stationary, in spite of the fact, when you're in geosync orbit, the movement relative to the Earth is 0, but they're moving at 17,000 miles an hour, and they do drift a little. When we'd shoot them out there, we used the IUS, which was the little rocket in the space shuttle, and they'd go out the 22,000 miles, and then your parking orbit's like plus or minus 3 feet. So you had to get them fairly exact.
Jeremy, did you have anything else?
I don't see anything else. No, I was just curious about why you guys were simulating the sun, and if there's anything going on with that.
We were capable of simulating any space conditions except for air drag. We couldn't pump it down. The room was about 30 foot cubed, so it'd be almost impossible to pump that down.
Oh, yeah.
So with the sun simulator, then basically this thing uses the gyros to orient itself so it's facing a certain
Yeah.
And then it's based on the sensors, right? So the sensor says, okay, it's a sun lock, and then we're going to orient based
Sunlock
on
and then
that.
star lock. There was three star patterns that we would go for, plus the sun, and then it had to maintain, in spite of the drift and movement and all that, it had to keep the stable platform because usually there's a microwave antenna that's pointing to Earth, and you're only allowed a certain position or it would cease to function properly. You know, a couple of degrees is all you got to work with.
Interesting. So let me see who else has questions. HD Aberras had one. He said, Mike, since MG is the input to the gyroscope, what is the change in performance in orbit in comparison to the gyro at surface level?
I don't understand that.
Yeah, I'm a little confused also. Okay, and then
If you're talking about efficiency, they're fairly low. You know, if you're talking power versus torque or something, they're fairly low.
yeah, let me see. And then Thomas Anderson. Thomas, do you want to ask? Let me see if I'll ask Thomas to unmute. He's pounding stuff into chat. Thomas, you with us?
Yeah. Do I sound all right?
Yeah.
Okay.
Can I trouble you turn your camera
for
on?
once? Let's see here.
Ah, there we go. Welcome back, sir. Welcome back.
Thank you. Yeah, I was going to say, you know, not really questions, but like you said that you had it not pumped down, but normal atmospheric pressure at sea level, which it looks like you were not at sea level, you were a little above it, is still only one part of gas particle, you know, solid mass in the room for every 990 or every 1,000 parts of vacuum. So that's still pretty decent. Even in deep space, there's like 2 hydrogen atoms per cubic meter. So you're going to run into that no matter what. And knowing how that affects it is beneficial.
We had that in the control algorithms when we'd run simulation versus the real McCoy. We'd throw in this dummy factor for air.
Right. Well, I was going to say the other thing too is like if you're putting them into space, launching them without a bearing, holding them up, just using a magnetic bearings, waiting for the gravity weightlessness of space so that the magnetic bearings could then push them up into position might be the you know, ideal condition.
Yeah.
I'm just wondering what data, if someone were able to dig through all the data you have, would be useful for centrifugal energy storage, where you know use a motor when you have power, like say solar cells, to spin it up, and then when you don't have power, like behind a moon or something, let the spin function force the motor to spin as
people
a
working
generator.
on flywheel energy storage in a different department that I was aware of. Yes.
Yeah, I'm guessing you guys exchanged a little bit of information then.
They were using a composite carbon fiber composite flywheel, and it did come unglued on them one time, and they got a little setback.
Ouch.
Yeah,
That can be quite
about
devastating.
20,000 RPM. It come right through the casing.
You know, I bet these days, because electric vehicles use that for regenerative braking, right? I bet there's a lot of advances in that area.
Right. Something else I'm wondering too is, has anybody considered using the gyro's rotation as an advantage by building like a cyclotron component inside of it, so that way you can combine the two technologies together?
I don't know anything about that.
Right, high speed spinning particles, you know.
One of the reasons that they don't use that technology too much anymore is half the gyro work used to be for navigation, and your little ring laser gyros have kind of taken over that niche because they can be built so small. You know, your cell phones got them in them. You know.
Right. The MEMS gyros.
Yeah. Yes.
I've got a few of those for building some drones for testing with.
Yeah, they use them on those too. Yeah, but that was basically half the gyro work they were doing through the 60s, 70s, and 80s was navigation. I mean, you used to have your artificial gyros on airplanes also, which, well, some of those are still in use, your artificial horizons.
Right.
Which are a vacuum operated gyro system. But as the laser gyro started taking over, Boeing started winding down that side of the work. And then when we hit that earthquake, that put the kibosh to it, and they shut down the lab. What's left of the lab got moved to St. Louis. I was offered a job back there, and I decided to pull the ejection handle instead.
I was gonna say, I kind of figured the reason for simulating the sun is, the electromagnetic effect from the direction it's coming would probably be what you were doing, is basically finding out how that affected it.
Well, yeah, that was what we used the Helmholtz coils for. Is when it was pointed towards the sun, we had a 2D magnetic field aligned with the sun simulator. So yes, we can simulate that.
Overcome that 1/1000th of a percent of the EM field that was still able to get through the Faraday cage from it emitting something internally.
Yeah.
Basically bring it down to the same levels like you brought down your vacuum by just having atmosphere.
Yeah.
So.
Okay. For many years, they did a lot of research with those gyros.
Well, if it's okay, let me go to Alex now. He's had his hand up for a while. Alex?
Hey, so that was really fascinating history. I just had a quick question, which is that the conventional wisdom is that a gyro, or I guess the two gyros, can't generate a linear acceleration from the torque. So did you guys publish anything about that, or are there any papers that came out of Boeing about?
Well, that's a very good question. If you were watching the first guy's presentation there, Rem, he had a chart there that showed exactly what we were doing. You have two torques operating oppositely, which we called scissoring. You can get linear approximation from that, and then by varying the rate, you can get it which direction you want to go.
Okay, yeah, sounds good. And do you know
I have a demo model that I built for Tom Balone for the coffee conferences, which he's given some presentations here on it. But it's a working model. It generates linear thrust. Yes, on my workbench here, that the little gyro. Well, there's two of them. They're about 3-inch gyros, and they'll generate about 1 pound of thrust.
Very cool.
It's pulsed. It's not a DC. Yeah. It goes pulsing movements.
Yeah, I saw the graph.
But in order to convert the rotary torque into linear motion, you have to have two of them that operate alternately.
Right. Okay, well, thank you. It sounds really interesting. I wonder if they're going to put those on satellites someday.
They're already up there.
The linear ones that produce linear.
Well, it all depends on which way you spin them. You can get torque if you spin them together, and you get force or linear force if you spin them alternate. It's just a matter of which way you rotate the motor or the rotors. They're already in space.
So a software update could cause a satellite to generate a linear acceleration, maybe.
Yeah, they have what's called station keeping, where it's up, down, left, right, in, out. They have a very small parking orbit, and these gyros will lift them up, push them down, move them back, whatever it takes, twist them, you name it. It's propulsionless. Or propulsionless. It's fuel-less propulsion. I'll get it right yet.
Awesome.
Hey,
okay.
Great. Thank you.
Thanks, Alex. So let me go back to Jeremy Reese. He has his hand up again. Jeremy?
Hey, Mike. Yeah, I had a couple more questions here from the live chat. One was, have you ever experimented with 3 or 4 gyros? I seen the thing with the 2 gyros. Did you ever?
The big one had 4 gyros. The medium one had 6 gyros on it.
Oh, wow. I had a couple other questions. Hold on. Let me just dig in. Oh yeah, they're asking if anything you tested or made is anything still up there or in use today.
Space station's working quite well.
Right,
yeah,
they have the gyros on the space station.
Every geosync satellite out there And some of those are the size of school buses that are parked out there at GeoSync. They all got them on them because that's how you keep station keeping. Hughes did a lot of work in this area. They're the primary, well, Boeing bought them out, but they're the primary satellite builder.
And then they had a lot of questions about you mentioned that you used 3 star patterns for timekeeping or station keeping.
Well,
and
yeah, well,
what were the star patterns?
well, one was the pole star. What's the
Polaris?
Polaris. I'll get it right yet. I'll tell you a good funny story about that. We had a little port in the lab. It was basically a little like a stovepipe sticking out the wall, and it pointed straight north, so we could use a theodolite to zoom in on Polaris. Well, anyway, one of the other Boeing divisions wanted to duplicate part of our lab, and they had the window facing, I think it was east or west, and couldn't figure out why they couldn't get a reading. And we just laughed. We had a big granite slab in the center of the building where we'd put the numbers after we'd used the theodolite. So you were never lost. You know the exact latitude and longitude of the building.
Awesome.
Awesome.
Okay.
Yeah, that was it. Thank you.
Thanks, Jeremy. Okay, let me see. Does anybody else have questions? Okay, well, I think we're all set for now then. Again, we're running a little bit ahead of schedule, but so let me do this. I'm going to put it back on gallery view. Everyone, give Mike Campbell a big hand. Thank you again. And I want to hand things over to Mark Sokol, who has been relatively quiet recently. So you've got some updates for us today, right?
Yes, I do. I just need to share screen. 1 second. Maximize this. I'm going to give a update. This is also for last 2 weeks ago. Jeremy Reese, Travis, and Aiden Schaefer were down here at the lab. We just had so much going on. I couldn't concentrate on APEC to give you guys an update. So this is like a 4-week update on what was going on. And I'll just do it in pictures over here. Okay, can you guys see that? That's a 3-roll mill.
Yeah, it looks great.
Okay, so yeah, this is a piece of equipment that arrived a couple of weeks ago. This is for making really fine powders of similar size. Oops, let me see what's going on here. I'm trying to. Okay, so this is Tom Butler. He is a local dude who helps out in the lab, and we started work on the Alzafon waveguide for the dynamic nuclear orientation experiment. And here we are putting it together. Basically, it starts off with a circulator with a dummy load over here. And then these are 2 isolators. Basically, this is all for reverse signal filtering to make sure that the any bounce, standing wave doesn't end up inside our klystron, damaging it. And then we have a cross guide, which basically tells us forward and aft power. And it ends off over here with a filter. Now, the next thing we did, I met up with Aiden Schaefer over here, and we flew into Chicago to check out this CNC machine that I found on eBay. We were shopping around for a CNC machine for the lab for quite a while, and there's been a lot of demand recently. And this was a sweet deal. It came with everything, like all the tools, tool holders, the bench, the vices. It came with everything. It was the whole caboodle, as Mike Gamble says. And here it is all packaged up and stuck on a truck. And then, oh, there's Tom again. And this is, what was his name again? Oh, Sam from this is a kid I met on APEC here, and he promised to come down to the lab and help out. And he sure did. We are getting the machine ready to take it inside. And we had to bring these riggers in order to actually bring it into the building, because it was there was a problem with the forklifts. One was too big to fit in, and the other one wasn't strong enough to lift it properly. So they came down and did the job and stuck it in the corner for us. Oh, and then these guys came down. This is Kevin Knopf and Keith from the University of Albany. They head up the physics department over there. They came down to check out the lab. Keith actually is an EPR expert, and he's never heard of the Alzaphan experiment before, and was pretty interested in it. One thing he did note, though, is that the Alzaphan experiment requires pulsed EPR. He said EPR machines don't have a pulsing option. They're just continuous. And yeah, he's never read anything about weight changes inside of a EPR chamber, which would be pretty hard to detect because you'd have to actually take the chamber apart and make holes in it. But he's very interested in this experiment, and will probably be coming down here when we're ready to run it. So this was one of the first things that I made on the CNC machine. We got all Fusion 360 and the tool paths, and here's how it came out. Cut that out on what is that, 6061 aluminum. The guy also gave us a whole bunch of stock aluminum because he wasn't going to be doing any manufacturing anymore. So we got like a whole package deal. It was really awesome. And then Aiden Schaefer came down to the lab again, and we're just getting organized over here, building the toolbox. This guy, Aaron, showed up. He shot a documentary film. Yep, here we are out in the parking lot, and look who showed up. That is Travis and Jeremy Reese. They drove down in this in this truck. He covered it with graffiti. The alien scientist disclosure now. My other vehicle is a TR-3V, declassify everything. Jeremy was getting all different kinds of girls on the highway were honking at him. It's pretty cool. Here's this was 2 weeks ago when he was down here just getting the stream ready. Everything happened last minute. He showed up literally right after APEC started. Oh, and then this guy Aaron did interviews for his documentary. Oh, and this is at the lab house. So we do have a guest house. It's a 5-minute walk from the lab, and everyone was staying there. This was at breakfast. And here's a picture later on. Me and Ada were working on the waveguide for the Alzaphan experiment. That's the end piece where the coherent waveforms are supposed to happen. We started off by trying to mill out the copper, and then decided to just go with sanding and buffing. This was an end piece that I actually had to cut using the CNC machine, so that worked out pretty well. That's the end device. That's like the attachment grommet. I reinforced it with lots of copper on the side because it's going to be holding quite a load when it's finished. And here he is buffing it out. Okay, this was our ARV coil. Jeremy probably remembers this. After he was down in, I think, Washington, D.C. by Tim Pool's show, he came up to the lab and we wound this coil together. It was a couple hours. The plan was to cover it with epoxy to then be able to stuff as much voltage in there as possible without it arcing over. This is an experiment we call Easy Alzaphan. It's basically the core of the ARV coil. And we're prepping it, in this picture, we're prepping it for a potting with epoxy. This is the waveguide end piece. So I plated it in gold. That's the plating setup. Blue Moon really helps. Okay, and this is the coils inside of our vacuum chamber. The reason why we stuck it in a vacuum chamber was to remove all the bubbles. And we actually pulled the vacuum and pushed it down again several times in order to get all the bubbles out. It didn't end up coming out perfect, and I'll show you that in a little bit. Then we stuck it on a CNC machine to sort of guess and pull take all the material out that wasn't the coil. I ended up, this is what it looked like while it was cutting. And here is the waveguide end piece. As we were soldering it, this was like a 2-man job. We needed to hold it from all different angles. soldering it was using 2 torches. We had 2 torches going at like an X formation in order to heat up the copper. Copper is such a good conductor of heat that you really got to heat the whole thing up for a while in order to get solder to run on thick. That's like 1/4 inch plate copper there. And going back to this, the coil, this is the finished coil. Pulled it off of the, I had to pull it off and clean it up. I'll show you those pictures later. These are all in synchronous order based on time. So you see it as it happened in the lab. Here is the completed setup with the klystron, stuck in, going all the way inside the electromagnet over there. You can see it from the other side. And here's Aiden smiling. Oh, and then we got some aluminum blocks over here. That's for a later experiment that I'll get into a little later. Basically, we're trying to make a waveguide. This for a later experiment. We're trying to make a waveguide that's going to be in the shape of the hull of the craft and have the magnetic field lines create sort of a homogeneous field homogeny based on whatever magnet we have in the center, and that would sort of create a flying saucer shaped craft. And to do that, we're going to use 2 big blocks of aluminum as dies and basically pound another piece of thin aluminum plate in between those aluminum blocks. That's what you're looking at over here. And here is the finished ARV coil. There was some damage to the inner lining, so I had to remove some of the bad wires from the center, but this is what we were left with. I then cleaned it up again and epoxied it again just to clean it up. And here is the finished product. It's actually sitting right here next to me on the desk. Okay, the next thing we did was started working on the field homogeny for the electromagnet. Now, last time I spoke, we had this idea to use a 3D printer to map the field. Now we're still going to go with that project, but it wasn't ready, and I just wanted to move forward with this. So I created this grid system with 2 line lasers that are at 90 degrees to each other, and a grid system of ABC 1, 2, 3, and then I stuck a probe in with a 90-degree cut on it. So it will basically cast a shadow onto the grid, and I'll be able to say K7, this is the result, and stick it onto an Excel sheet. And this is the mapping of the magnetic field. This is what we ended up with. Now, using this, actually this line over here, the one that goes all the way through the magnet, I was able to extrapolate basically a field strength graph, and use that to create these lenses, magnetic lenses. The first attempt was done via the 3D printer using a magnetic iron PLA plastic. And here's one of the first attempts at it. That's these are different discs that I made, and then we went with a thicker one because the correction wasn't strong enough. Then it was too strong in the center, so I cut out kind of center hole. And basically what we ended up realizing is that the iron that's embedded inside this iron PLA plastic wasn't strong enough, so I had to go with just pure iron and CNC it out. The next thing that happened was we got flooded. So the shop is in a flash flood zone, and it's actually equipped with these floodgates. So this is not the amount of water that actually made it into the shop, but we're up against a stream, and situations like this can happen every couple of years. It's about 2 feet of water there, and it's gushing past. Like, this is whitewater rapids over here. And this was a situation for about an hour, about 2 days ago. And oh, here's inside the lab. We got like 2 inches of water over here, and this is right after it. You can see over here, these are the floodgates. Luckily, the only thing that could have possibly been damaged, because I intentionally did not leave any equipment on the floor. Everything was just, dead items. There was an oscilloscope on the floor, and thankfully it was not damaged. So here is the metal blocks that I got for the lenses for the magnet, and we're cutting it out. This is the tool path. Lots of fun figuring out how to cut the tool path properly and how to adjust it. There's so many freaking settings in Fusion 360. Yeah, it's a real challenge figuring them all out. This is one thing that I learned is if you're cutting, you want to cut below the stock, you got to do stock to leave and then -1 millimeter. That's a little trick. If you want the tool bit to go underneath it. So basically, this was attempt number 1. We broke a bit because the speed rates were way too fast. The whole machine was shaking when that happened. The next one, the bit did not break, but it didn't go deep enough to cut out the piece. And this is the third one where it just about got deep enough to cut out the piece and I had to do some work by hand. That is the end result of one of the pieces. And I actually, during the conference, we actually were running a second one. They are right here. And these are going to be magnetic lenses to correct for the anomalies, the issues that we were seeing with the magnetic fields homogeny. Good thing about it is, I could change these out as little inserts against the magnetic field plates, and then we can see, how that correlates with the magnetic field readings that we're getting. And here is the scope that was on the floor. This sat in about 1.5 inches of water. It was inside a box though, so it might have been floating, but thankfully it survived. So there was no damage in the lab. We got 2 big ass dehumidifiers in here right now. It's actually pretty dry. And the debrief wrote an article about me, and they made it all about a warp drive detector, or the laser interferometer thing that we were talking about a couple months ago. And I explained to them that it's not a warp drive detector, it's a laser interferometer, but yeah, they just wanted to call it something more exciting. That's it.
That's a lot, Mark. That is a ton. That is a ton. So how have things been going other than that? You guys got flooded. You have a ton of new equipment, a ton of new experiments. Everything's moving along for you.
Yeah, I mean, it's very exciting to having the CNC machine. Really is a game changer. I wanted to hook up with Brian St. Clair and try building his device. Right now, it's just like a push button away. We can build one of those things pretty easily. We actually have a 4th axis on that machine, so if he wants to make one of those fancy gears with the slanted grooves, it could do that as well. But it's the main the only holdback would be the CAD files and the materials you want to work with.
Those aluminum slabs that you showed in the photo, they're big. Are those solid or are those like hollowed out? Those are solid?
No, those are solid. Yeah, those are 4 inches thick, 12 by 12 slabs of aluminum. They weigh quite a bit, even out of aluminum. They weigh quite a bit.
I was gonna say that must be super heavy. Yeah, I was looking at those going, that can't be solid. Well, should we go to open discussion now?
Sure, unless anyone has any specific questions about my presentation.
Well, and you know what? Here, I'll go to gallery view. Everyone give Mark a hand. Well done and detailed update. Well done and detailed update. Yeah, I'm glad to see you guys are still working on stuff and making progress and slogging through all of the, it's a lot of hard work, but I can see, it's even stuff like electroplating, right? It's like a lot of the little details that you got to put together and get all that stuff. So, yeah, well, let's go to, I guess, let's go to open discussion. I'm not seeing any hands raised or anything.
Oh, Michael Boyd. We can always count on Michael.
Okay.
Okay. I had some things I wanted to share.
Oh, you had the, okay, for open discussion.
Let's see here. Now, first I wanted to share this little video that I got from Steve Wozniak. Everyone know who that is? The WADs? Oh, it is my screen share is paused. Stop. What's that mean?
Oh.
Okay, let's stop the share and try again.
Is that the one? I just saw something with Wozniak about repairability.
There we go.
Yeah. That's because we're both surfing LinkedIn. That's the problem. We see all the same stories.
Let's see here. It said there was a little video of this.
The right to repair.
Yeah.
That goes to Mark's stuff right there. Being able to tinker, being able to take things apart, modify them, and fix them.
I'm not getting the video. Oh, here we go.
Hi, Lewis. Steve Wozniak here. I do a lot of cameos, but this one has really gotten to me, really affected me emotionally. I've read a lot of articles about the right to repair issue, but I am so busy with so many other things in my life that I haven't really gotten involved in that area, but I'm always totally supportive, and I totally think the people behind it are doing the right thing. I have now subscribed to your YouTube channel as well. It's that meaningful to me. We wouldn't have had an Apple had I not grown up in a very open technology world, an open electronics world. You could learn electronics at a very young age. I had a ham radio license at 10 years old when you had to build your own radios, every single part of them, transmitter and receiver. You know, and back then when you bought electronic things like TVs and radios, every bit of the circuits and designs were included on paper, total open source. Someone with skill could get in and modify things to fix broken radios or televisions, or to improve them, or to even replace destroyed parts. Way back then, when I grew up, instead of chips, these products were made with vacuum tubes that are like electric glowing light bulbs. And when a TV or radio went bad, it was probably a tube that went bad. So you'd unscrew the back and you'd pull out all the tubes, maybe 5 tubes, maybe a television would have 10 tubes or so. And you'd know that one tube was likely to be bad. And even non-technical family members could pull out the tubes and you'd put them in a bag, paper bag, and you'd take them down to a local electronics store or even to the grocery store. It was that common. And then you'd find a tube tester and you'd look at a tube, each individual tube, you'd look at it. It might have a part number like 12SA7, you know, and then you'd look on a tube up on the tube tester and it would say, oh, slot 25. So you'd plug it into slot 25 and press a button for a little while, and within a few seconds, a meter would go to red for bad or green to blue. And if it was bad, you'd buy a brand new 12SA7 tube to take home for your radio or television. Everyone did this all the time back then. And it made us feel good about being able to fix our things when they went bad. I don't know, you just feel good about it. If your TV went really bad, you might have to take it to a local TV repair shop, which every town had TV repair shops. And I myself, you know, had taken electronics. I could fix, I understood all the circuits inside of televisions, both black and white and color. And I could fix them with my own equipment even. I was qualified to be a TV repairman. I was qualified as a TV engineer, really. When starting Apple, I could never afford a teletype for input and output. You type on this big machine, heavy machine, like you see in movies, you know, and they cost as much as 2 cars. I could never afford one, you know, so I didn't have any input and output possibilities, even though I had taught myself to design computers, and I wanted so badly to figure out how to build a computer that was usable. And for it to be usable, it's got to have an input and an output. Well, I owned a television, right? Everyone owned a TV, and I knew how the signals worked, but I was a TV engineer, but I was also a digital design engineer. In digital design, I could use very few parts. I was very good at that, to get all the signals out at the right time to show up as balls and paddles on my TV. So I could put the signals into the right place in the TV set. I'd look at its open source schematic, and I'd probe around with test equipment and find, yes, this is the place you put video signals in. And I sent in a little video signal, you know, so I was able to build some arcade game projects like Pong. I did Breakout. I designed Breakout for Atari. I had an early ARPANET terminal back when there were 6 computers on the ARPANET. Now we got billions. It's called the internet. And I also have built what became the Apple I, you know, and I could feed my signal into it. And I had my own TV, which I already owned, as an output device. I didn't have to afford something I could never afford. So I wasn't restricted, you know, from anything that kept me really from building that computer and showing the world the future of computers, personal computers, is going to be a keyboard and a TV. Back then, and that all came from, you know, this basically this whole being able to repair things and modify them and tap into them yourself. There were no video in jacks on a TV back then. The phone company, though, was a monopoly in that, Ma Bell. You were not allowed to touch the telephone lines in your home with anything electronic. Okay, nobody was allowed to manufacture a telephone or answering machine, even though they could build much better ones than Ma Bell. Ma Bell would have these crude ones, sometimes dial only. They got up to, time we started Apple, they were up to touch tone. Beep, 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 beep. And nobody could manufacture them. You'd have to buy it in black. You wouldn't even get a choice of color. Can you believe that? No answer machines, only the ones sent to the theaters that cost a fortune. You could only lease one model, a phone or answer machine, from Ma Bell. That was changing around the time we started Apple. Big antitrust suit got settled, and now companies were allowed to build stuff that connected to the electrical specs, the standards of Ma Bell. And look at how many phones, before cell phones, you know, took away everything. Look how many phones you could buy and answer machines at all the stores, and so many choices you had that you never had in the past with the monopoly. You know, anyway, engineers, you know, design their circuits, their televisions in the old days, radios, computers now, with specs and connections, you know, or parts meeting those connections, meeting those specs will work fine. Parts meeting those specs will work fine. You know, sometimes we bring one out on a little jack and say you can plug an earphone in and it will work. And, you know, but you don't get a lot of choice about really all the options you're allowed to do, but you're pretty much allowed some choice there. Thing is, if there's a part inside and you want to substitute a different part that you can get maybe cheaper, it's not going to blow things up if it meets the specs. That's what engineering's all about. And it worked fine. So if somebody if you destroyed a product, you're trying to replace a part and you destroy the product, well, yeah, that's your tough luck. You lost your product. But, you know, if you know what you're doing and you're doing certain steps that others have solved and found that, you know, work pretty well, you can repair a lot of things at low cost, but it's even more precious to know that you did it yourself, you know? So why stop them? Why stop the self-repair community? Why stop the, you know, right to repair people? Look at the Apple II. It's shipped with full schematics, designs, and software source listings, you know, code listings, totally open source. The Apple II was modifiable and extendable to the maximum. People figured out how to convert the early display into having lowercase characters and stuff with their own hardware added. This product was the only source of profits for Apple for the first 10 years of the company. This was not a minor product, and it was not that successful on pure luck. There were a lot of good things about that being so open that everyone could join the party. You know, that movie, The Beautiful Mind. Sometimes when companies cooperate together with others, they can actually have better business than if they're totally protective and monopolistic and not working with others, just totally competitive. Anyway, how is Apple hurt by the openness of the Apple II, I wonder? You know, more than what's right and what's wrong, that aspect of self-repair is also the motivation and joy of just technical people wanting to grow up technical, knowing how to write the right kind of software and develop the right kind of hardware, like doing these things just to prove to themselves they've got a little special skill in the world and they can show it off to others. Very motivating for creative minds. Believe me, that's how I grew up. Anyway, it's time to recognize the right to repair more fully. I believe that companies inhibit it because it gives the companies power, control, over everything. And I guess in a lot of people's minds, power over others equates to money and profits. Hey, is it your computer or is it some company's computer? Think about that. It's time to start doing the right things.
So that's a pretty interesting subject. I think that I don't think I'd be where I am if I didn't basically have the ability to tinker with stuff and look at the specs. In fact, I had jobs where I was basically given a spec sheet and a chip and said, okay, test it. Tell me if it works. So now the next subject I wanted to chat a little bit about is this intergenerational trauma. And I have let's see if I can get this to show. Okay, oh, that's not the one I want.
Well, yeah, and Michael, just a thought, we want to be sensitive to potential copyright issues also.
Okay. These are just like what would you call it? Like a presentation image.
I think at least for me, your screen seems to be blanking out.
Oh,
I think it's the Opera browser. I think that might be what's doing it.
Okay, let me shut this one down. You saw that other thing with the was okay though, right?
I did, yeah, I did. And then when you stopped it now, all I see is kind of gray with light gray stripes, which is kind of weird.
Yeah, it's coming up right now. It's just for some reason it's pausing. Maybe I lost my share. It said screen sharing is stopped. Let me see. That's what the problem was. Okay, let's do this again.
It could be the video plugin did something weird.
Yeah. Okay, here we go. I got it.
Yeah, there we go.
Can you see that?
Yeah.
So this slide shows basically this intergenerational trauma. And this shows like 3 different scenarios, let us say. Okay, and the one starting on the left, we have surviving European wars. Jane's great-great-grandparents. Trauma passed through to the generation. And you see PTSD, alcoholism, sexual abuse, emotion, repression. And then on the left of that, you see this looks like DNA, and the word is epigenetics. And what epigenetics is that this trauma basically is being passed on from generations through the expression of certain genes. An example would be alcoholism. They've linked alcoholism to genetics. So it's not just this trauma is actually affecting our DNA. Okay, and now the second scenario is in the middle here. We have surviving slavery and racial violence in the American South. Ashanti's great-great-grandparents, trauma passed through the generations, abandonment, domestic violence, low self-esteem, CPTSD, I don't know what that is. And then you have this child Ashani. And then on the right, we have surviving famine and oppression in British India. Ashok's great-great-grandparents, trauma passed through the generations, poverty, consciousness. Can't see some of these words. suffocating shame based on social rules, severe anxiety, depression. And then they show when you work on your trauma, you choose to not pass it on to the next generation. Okay, and then I have just a little short video. Probably because I have too many windows up. There we go.
The story of our communities, people, and nation starts a long, long time ago. More than 60,000 years, in fact. This was when our culture and our law first started to thrive. We knew who we were and where we belonged. We took care of each other, our land, and our waters. We ate food that made us healthy, lived on country, and abided by our laws and song lines. Our families, our children were happy, with strong minds and hearts, because they were where they belonged. But then everything changed.
Colonization came, bringing wars, disease, famine, violence, and the destruction and violation of our cultural laws, sacred sites, families, and communities.
We were denied our knowledge, language, ceremonies, and identity, the very things that tell us who we are and where we belong. And our connections with each other and the land grew weak.
And then our children were taken from us. They had their names changed and their identities stripped away. They were told that Aboriginal people were bad. Worse still, they were told that their parents and grandparents did not want them.
For years this happened, and those children became known as the stolen generations.
Our children were denied love and experienced physical, emotional, and sexual abuse. This left very deep, very complex, and very real wounds, leaving scars that are still being felt personally, socially, spiritually, and collectively.
In the time when our story started, we were able to parent in the cultural way that has seen our families survive and thrive for generations. Our people were strong, and our culture flowed and healed us in times of hurt.
But since the trauma of colonization and the stolen generations, we have not been able to heal in the same way. And we have unknowingly passed this trauma on to our children through sharing our sad stories and having them witness and experience our pain. This is known as intergenerational trauma, and we see symptoms today in broken relationships, disconnected families, violence, suicide, and drug and alcohol abuse.
But this is not where our story ends. We still have strong minds and hearts, and we still know who we were and where we belong by creating safe and strong communities together, supporting our families to be free from pain, returning to our culture and building a strength of identity. We can stop the cycle of trauma and bring about positive intergenerational change so that we can continue to thrive for the next 60,000 years. There are simple things that we can all do to help heal our trauma.
Visit healingfoundation.org.au to find out more.
How does this relate to alternative propulsion engineering?
Yeah, but we should probably try and get back to our core focus. I think it's
Well, the context was what we were talking about was this Stephen Greer video and this whole narrative of an alien invasion and the government's trying to put something over on us. Basically, this narrative is built on this culture of violence. Is my point. And if there are extraterrestrials, would you be afraid? I mean, we all have feelings, okay? Even though we may not agree on political stuff or religious stuff, we all have these basic needs. We all have feelings. We all share this stuff. Why wouldn't they share? Why wouldn't these other intelligent species share this same feeling too? Why? And fear is a feeling that affects.
That's true. That's true. But even the Stephen Greer conversation was off topic. This is just taking the off topic even farther off topic. I'm not saying anything like positive or negative about it, but it's not the place for this.
Yeah, we should probably try and rope things back into the.
Okay, well, I'm done anyways. I just wanted to show though that.
Well, no, thank you for sharing it, Michael. I think it's something that's important to raise awareness about, and I think that's something that probably applies to a lot of people. So I think there's definitely value, but Mark has a point. So
yeah, I agree.
The epigenetics part is the key, and also that.
Oh, sorry, Bernie, you're fading out.
And that we have to tie that into engineering and into the equation of everything, and that military has had this knowledge or this science classified for so long, but for good reason, because it is dangerous if you're essentially sending or using energy on the same wavelength that light and brainwaves operate on, right? But sorry, that's just what I feel Mike was trying to tie in as well.
I'd like to add to that conversation. This is Bill. I'm a epigenetic experiment in a way. First time I got on here, I said I was taking Dr. David Sinclair's NMN. So it makes me younger. And that's based on epigenetics. NMN is a molecule that they developed that there's like 7 sirtuinins that are connected to changing your genetic structure. And they found that some of these are connected to longevity. And so it's really interesting to me, but I'm trying to get all the way back around to the propulsion aspect. And it's like stuff like this might become the new normal whenever, we got to live longer in space. We need to understand our genetic code more. All these are really interrelated. Richard Branson's going to be flying off from New Mexico tomorrow. I'm in Albuquerque right now. And anyway, they're going to have a big concert out there. Khalid is going to perform New Normal. I think this is all part of becoming the new normal, moving ahead. It's progression. I'm not a progressive type, quote, progressive. I'm more of a conservative. I am a conservative. But yeah, I think that, as far as the propulsion aspect goes, yeah, we should be more specific on the propulsion because they just started another space company in New Mexico. We got 4 or 5 of them now. We got spin launch. We've got the spaceport. Guys are going to be flying in and out of there, giving rides into space. And then just right there in West Texas, we've got the guy who owns Amazon. He's going to fly up, take his brother up into space. So there's some really firsts going on that and we need to understand these things. We've got a lot of homelessness in Albuquerque. Yeah, if you guys come out to the Tesla Tech, you're going to see homeless people all over the darn place.
Well,
and you need to be.
Yeah, and actually, I talked to Steve Ellswick today, and I kind of mentioned he's been talking to Mark Sokol. Yeah, we're going to do a live feed from Tesla Tech. That's our goal, at least. We want to try and do a live feed. So
great.
Yeah, I'm really excited.
Well,
I'm
moving out of Roswell. I'm moving to Albuquerque. So I just bought a place. I'll get resituated just south of Albuquerque here. I think it has a lot to do with our genetics, and I think the reason these people are on the streets is because the homeless is because of greedy people. Greedy people's got all the darn money, and I'm not going to say just throw money at these homeless people that are on every street corner and begging at every street light, and you will see them when you come to Albuquerque. I don't know if you got them where you're at, but we've got them all over the place. It's so sad. It just makes you.
I think
what are you going to do about it?
Homeless people tend to congregate around places where they can live overnight. And New York, New Jersey, Milwaukee is not a very good place to be homeless. But yeah, we are going to be at Tesla Tech. Steve Ellswick gave me a slot on Friday the 13th at 1300 hours to give a lab update. So
awesome.
Well, Mark, so while you're there, I would love it if you could connect to like hotel Wi-Fi, right? Or something like that. You could do Zoom from your phone or, Zoom from a laptop or something like that. Do a live feed, walk around, give interviews, talk to people. I mean, I hate to use the phrase roving reporter, but it would be cool, And
I think Jeremy Reese, we're in talks with Steve Ellswick about that. It turns out that Bill Alec, he was going to present his free energy device, but he's got the boot on his house. So he's not going to be able to present. So there's an open slot for Jeremy to come down there and do a workshop. And that was kind of the plan, getting a Wi-Fi device and just going around showing everyone what's up.
Yeah. Well, no, I think that'd be really exciting, and I mean, who knows, with the impact that this conference has had and with Tesla Tech, I think a lot of people are going down from this conference. So it'll be interesting to see kind of how things go, and maybe you'll I don't know what you call it, pick up some synergy, right? I mean, that's the big thing, where people come together randomly and things click, and then everybody discovers new ideas. So
yep, lots of synergy. Hopefully we'll get Jeremiah down there too. Have to get up to Milwaukee and kick his ass.
Yeah, I was very much considering, especially if we're going to do a workshop, we might as well set up some demos, right? If we're going to have a whole room dedicated to being able to set up things and isolate them properly from people, so no one's in danger. Yeah,
Jeremy was actually talking about taking his van down there so he could stop in Milwaukee and just like load up.
I don't know, man. It's a lot of mileage and a lot of gas. I was just thinking, gas isn't getting any cheaper either.
There's a reason I designed things to be compact and efficient. So,
but that's also why we got to figure out how to make this hydrogen and use it in car engines so that we can all drive around for free burning water.
What's up, buddy?
Bernie, that doesn't really look like hydrogen. I'm not sure, but
I have some machines that produce hydrogen. They certainly don't make anything that looks like that. They do produce nice, clean output gas, and they don't darken the liquid. But there are more than one ways.
Is that doesn't methane have hydrogen in it too, though?
Bernie, is that your tie-dye? That's your tie-dye stuff, right?
No, not at all.
I think he's trying to turn copper into gold.
No, I'm making monoatomics and hydrogen and Brown's gas, as well as different plasmoids in the different metals. That's copper with steel, zinc on copper.
Just don't let your neighbor. Cloud there. You will be terrified. So they will not understand what they are looking at.
I thought I saw Aunt Tilly's legs
That
in
big
that liquid.
cloud is Pesci says, but it's actually replicating your amino acids off of the cathode as well.
Interesting.
I don't think I go eating any of that.
Oh God, no.
Not food.
I'll show you guys in a sec the
I'll get my amino
monatomic
acids.
gold made from gold on gold.
Oh man. You using a ventilator? You're not breathing in the off gases, right?
This is all outside. This is outside. If anyone is left that knows about moving electric fields and wants to talk about that topic regarding propulsion, I would love to get across E cross B fields and talk about a device that I'm working on that may help in that research.
Yeah, well, go for it. Go for it.
What do we have left? All right, so what we have here, I know the lighting is terrible in this room, so let's see if I can get my cam to adjust. Probably not.
There you go.
Yeah, good enough. So this disc has, you can see 6 segments. 3 of them go to the center hub and go underneath it. 3 of them go to leads that you can see on the top of that center hub. Those are 3 copper conductors that go to the top, and they actually run up through the frame. If I can kind of show that. So anyway, on the top side, if I put in charge, I get 1, 2, 3. I get those plates polarized in one direction, and on the bottom side, if I put it in charge, I get plates polarized in the other direction. So on the bottom side, this is an insulating disc. These are partially conductive, painted on carbon or graphene containing lacquer pads to counterbalance out a neutralization plate, so that these capacitor plates can effectively have their fields closed, sort of like, a Hall effect array, where the fields close on the bottom side with a material that doesn't allow charge to circulate very well, so it doesn't produce a countermagnetic field. And on the top side, the connecting flux lines would have to radiate outwards into space, and they should stretch at least, at least I would say the distance between them, which is at the minimum a 1/4 inch at the pitch point, and at the most probably about 1 1/4 inch average between the plate centers. So this will be charged to over 100,000 volts. It's a sanded off CD-ROM, and these are great disc materials to make stuff like this. So what needs to happen is this has got to go in a vacuum bag and be squeezed. It's already got surface dielectrics, and on the back side to cover this up, this other plastic plate, which is good for 50 kV, just simply covers that, and then this whole thing gets sandwiched down, epoxied together, and then there will be 1 small charge contact that comes into the motor shaft and 1 small charge contact that comes in through a sphere that's on the top that will have a ion beam pointed towards it to deliver the top plate neutralization charge.
So where's the high voltage going to be applied?
The high voltage is applied between this side of the disc at the center hub, which is fully isolated up to 160 kV. And the shaft, which is the other side of the disc. That's so those 2 points, the shaft and these 3 wires, which will attach to an electrode, are isolated from each other to 160 kV DC.
Okay, and the charge is going to be in the dielectric?
Yeah, the charge will actually be both in the dielectric material itself and on the surface of the plates.
Gotcha.
Or at least, the displacement charge will be on the surface of the plates. Because if all the electrons are pulled to one side of the copper pads, then it's going to leave a whole bunch of protons on the other side, so that electric field can still be emitted out. Then in either case, the goal of this device is to basically rotate it at a high RPM, at least 5,000 RPMs, maybe upwards of 9,000 RPMs if I can get it balanced well enough, and to have an electric field in upwards of 100 kilovolts, so that I can see what the effects of that electric field are on surrounding objects, space itself, and maybe even test the device in a vacuum, ideally.
So the metallization that you show on the other side, it's a film on the top of the dielectric, or is it?
Yeah, it's a film made of basically nail polish and graphene. And it's semi-conductive, meaning that the charges that get deposited on it or displaced into it from the dielectric will effectively be trapped by it. They won't be able to circulate very well, so there won't be a conduction current that would normally produce an eddy current and a consequent magnetic B flux that might counteract any
any emitted fields that we get out the front side.
So the electricity that goes into that, the electricity that you're going to put into it, how does that, is it contacts? How does that work?
Yeah, it's physical contact directly input from a high voltage power supply.
Mm-hmm.
And you measured the dielectric strength of the insulator, so you know that it's going to be able to take 5K. How many kilovolts did you say?
100,000 volts.
100,000. Okay.
So you basically need about a 1/4 millimeter thickness layering of like mylar to fully block that, since a full millimeter will block 400,000.
Yeah. Yeah, in this case, I'm using polypropylene and polycarbonate.
So how are you going to measure the signal that comes? Are you going to use
Well, I tried a crude experiment with a very large machine that I showed, I believe, before. But this is the floppy disk motor machine. So this can rotate, and I can deposit charges on the surface of either side of this very thin polypropylene disk. Now, this is an interesting material because one side is very smooth and the other side is quite rough. And the reason for that is this is a diffraction lens from the inside of an LED TV in order to spread the light out more evenly for the LCD panel. So the interesting thing is ions like to stick into the pores on the rough side, but they'll blow right off the smooth side. So if I want to end up leaving a negatively charged disk negatively charged, I can put a bunch of electrons in the rough side. I can put a bunch of positive ions on the smooth side, and I can spin the disk. And all the positive ions will fly off, and the disk will suddenly develop a negative potential. And if I then continue to rotate this disk left with the negative potential, it'll develop a scalar field because now it has an unbalanced negative charge that's in motion. And that motion has angular velocity, and I can apply changes in RPMs to the motor to get the acceleration deceleration field plus the angular momentum, which allows me to detect and actually change the vanes on an electroscope that's hanging there and make them, you know, move or bend based on the RPMs, showing me that I actually have a scalar field that changes.
Gotcha.
So this is an optimized version of that, designed to enhance the effect in a more controlled way. There we go.
Interesting. Very cool, Jeremy.
So yeah, something curious, but no one, I don't know of anybody that's working on experiments quite like this. You know, theoretically, if you get enough, okay, space has a variable refractive index. We know that. If we move a large electric field, it's going to produce a longitudinal displacement of charge. It's basically the same thing as an electron experiencing acceleration or moving around a B-flux, because we're rotating charges around a circular path. So might as well be the same thing as moving charges through a wire, except for not quite, because there's no balanced charge on which to reflect against those charges. So instead, only the electric potential part of the field ends up showing up. We don't actually get a magnetic field. Contrary to Maxwell's equations, there is no magnetic field for the moving charges. They don't produce one because there is nothing to, I guess, create a frame of reference, a stationary frame of reference by which there becomes a field interaction to collapse the wave function. So it just becomes a scalar potential that's only the dot product of each individual charge. And it never neutralizes out. It's an unbalanced or radiated force that you only lose. It's sort of like a radio antenna only emits the radio waves. You never get them back.
But the charge that you're moving is the charge that's trapped in the dielectric.
Right. You never lose the charge, but you produce a field that acts as if you've added more charge. So as long as you don't let ions come in and neutralize that charge, you can effectively continuously rotate that thing and continuously produce a scalar field which should be unbalanced and build up over time. Eventually, you should have a whole bunch of charges that want to rush in from all around you and try to neutralize it out. And as long as you don't let them get to you, well, you can develop quite a potential, theoretically. That's what I'm looking for now, is to fundamentally prove that this potential can charge a capacitor. And that will be absolutely proof that there is not only a virtual charge, but that there's power in that field. And that virtual field contains energy that can be reacted against. If there's power, then you can make a force against it. We know that. So the fundamental experiment should prove that. I wish I could get somebody to work with me on it, but no one wants to seem to engage on it.
Hey, what do you expect to see with your experiment? Are you going to test it with the laser interferometer? Is that
Absolutely? I do expect to see something else. What I'm actually looking for is to see a counter torque against space itself. So this device, here's the plan. It spins up to X RPM, and I have some kind of encoder on there that keeps it at exactly that RPM. There's a motor that spins it up. Its internal battery pack and internal power supply are all contained within a box that's isolated from the environment, enclosed. It doesn't matter if there's air in the box or not. Regardless, it's electrically and air circulation-wise isolated from the environment. So I spin this thing up. I hang it from a thread so that it's facing basically downwards like this, and hang it from a thread at its center point to balance. And once everything is at a fixed RPM, I then, at that point, add the charge to the electrodes. And what I expect to see, if the theory is correct that I'm working off of, which is that it should produce a Lorentz force against itself because of the radiated fields not being in the correct position and the plates now reacting against each other at a slight, tiny angle. You know, that's all that it takes for electrons flowing through a copper wire is a slow velocity. So we only need a slight angle to cause this thing to drag. And what should happen is the whole box hanging from the thread should start to rotate against itself, against the direction of rotation from this device once the electric charge is added.
So do you have a flux meter? A magnetic flux meter?
I do have ways to measure a flux meter, but the problem is that if the impedance isn't infinite, they'll simply discharge the field. And the charge, sort of bend around them. Just like, if you go up every couple hundred feet, or so if you go up every 300 feet, you get like 100 volts, or I forget what the number is. It doesn't really matter in this case. The point is, if you stick an antenna out of the ground that's conductive, or a rod or a flagpole or something, and it just sits there and it's constantly there, the charge field will bend around it and ignore it, and it'll be compressed. So
well, I'm more wondering if you measure, you have your disc spinning, you've created your different segments where you have your metallization, and then you have a little gap in there, right? And then if you could measure with your flux meter the flux signal, get it close up to the surface of the disc.
Well, I can measure the potential. I can like if I stick my scope probe, even with no nothing attached to it, just stick the scope probe close to this plate at low RPM with low voltage, you can see the voltage signal swinging up and down.
Okay, and then when you see it, does it have edges, edge effects, kind of like sharp pulses where the edge of the metallization is, and then it stays up and then goes down? You follow what I'm saying? Is it
only if I bring it really close to the surface of the plate? Yeah, I mean, the farther you bring it away, the more sinusoidal it becomes. The closer you bring it, the more square it becomes.
Right. So when you do that, you can see in the signal, you can see the voltage potential will go. It'll have a ringing basically in front of it when it starts over the metallized place part.
Well, there's really no ringing. It's a very direct waveform. You don't really have any inductance in this place because there's no charge moving. The charges themselves are staying fixed in location on the disc. They're not moving around.
You're just measuring the voltage difference
right.
between the charge in the probe,
so
essentially.
The only thing that's really changing is the gradient divergence at the edge of the other capacitor plate, which in this case is your scope probe. So the closer that you get to the plate, the less edge divergence that you get, and the more it acts like a perfect parallel plate capacitor, and the more square wave that cutoff point is when you change or invert polarity. So it just makes sense based on the conventional parallel plate capacitor dynamics.
My point is, you can see that time delay between it when it goes, because you have that space in between or a little gap where.
Yeah. If I take one scope probe and I place it really close to the wheel, and I take another scope probe and I place it like 2 feet from the wheel, there's definitely a phase difference between those two.
Right.
And that phase difference is the reason why I'm expecting a counter torque against the device itself against space.
Oh, I see. Okay, thank you, Jeremy.
Yeah, no problem. Anyone else? That's what I wanted to talk about.
Yeah, well, I'm a little bit confused on capacitors. Like I said, I'm no scientist, but the capacitors store the charge on their plates, on the plus and minus. If they're I guess if they're a capacitor that has a polarized capacitor.
This is a big misunderstanding on capacitors, and if you'd like, I can clarify real quick. I've done a huge amount of preliminary capacitor experiments and demonstrated those on video and to a number of people to show where capacitors store their charge, how they store their charge, and the variations in the way capacitor materials will respond to external inputs based on the type of materials used. Okay, so there are different types of dielectrics, and they do very different things in terms of how the capacitor stores charge. Example one, I have this stuff. Now this is the same exact stuff we've seen that big disc made out of. Rough side one, smooth side other. In this case, it's not spinning. This is, again, a polypropylene plastic. So what happens is I will take a metal disc like this. I'll place it on one side and ground it. I will take another metal disc, place it on the other side. Between those two discs, I will apply about 50,000 volts, and I will then remove the discs, and this material I then set on top of a plastic cup and set to the side and proceed to explain how when charges enter the plates, they don't simply displace or polarize the dielectric. Electrons actually leap off one of the plates and they enter the surface of the dielectric, and that pushes the electrons out of the other side, leaving the charges trapped in the dielectric, which is why, even though technically when this plate is here, the charges migrate from the dielectric back into the plate, the fact that if I only remove one plate, the other plate's still there, those charges want to stay attracted to where their counterbalance charges are. So they actually leap back off the plate by the mechanical motion that I add of removing the plate. That's what gives them the energy to leap off the plate and to stick and burrow into the dielectric, which is why they stay there. Now, you can also use ions to deposit them into the dielectric. However, if I were to have these plates positioned some distance away from the same exact material and they never made physical contact, even in the air, as long as I never reached ionization potential and these were smooth surfaces with round edges, no charges would ever actually enter this dielectric. And if I removed the dielectric, the capacitance would change, but the charge wouldn't stay on the dielectric itself. It would actually re-enter the circuit and cause a current to flow back out of the capacitor by removing the dielectric, because there was no physical contact and no ions were ever able to exchange charges. So if that helps clarify where the charge is stored in the high voltage capacitor, I hope it helps.
So in one case you have free electrons, in the other case you don't? What'd you say?
Right. In one case, you actually have charges enter your dielectric physically, and the dielectric thus becomes the storing medium of the charge. In the other case, you have the dielectric that fills the space and changes the refractive index of the physical volume between the two plates, but no charges actually leave the plates and enter the dielectric. The dielectric simply polarizes that space and acts as a much intense refractive index material, just like a lens would for light. And it effectively makes the two plates act as if they were close to each other while still dielectrically insulating them, keeping charges from flowing from between them.
So in the case where it's in contact, that's where the electrons are free to flow. Right.
So in the case of ceramic capacitors, for example, the charges actually enter the ceramic material. If you were to, rub the plates off after you charge them, the charge would still be in that capacitor. And I did that experiment. I took a regular ceramic radio capacitor, high voltage, 18 kV cap, and I removed the plates by just using some acid to rub them off. And then I just simply used a tiny little piece of wire to sort of move around and, charge the plates up. And then I took a piece of wire and brought it around the two sides, and arcs formed across the surface, zapped in sort of like the, what do they call that? That zero pinch machine that, you see lightning discharges across the surface, the Z-pinch machine.
Ladder?
Yeah, the Z-pinch machine. It looked like that, basically. Sparks just ran from the entire surface over to the discharge point. get out of the dielectric because they were actually being stored in the ceramic itself. So that just proved where they were being kept.
So now, in the case where you have the dielectric and there's a gap, and they say an air gap between the two plates, okay?
Yeah.
If you remove the dielectric, there's still a dielectric. It's just that you've changed the dielectric.
Right.
So aren't you still putting because there's no charge that's going to build up on the metal in either case. It's not free electrons on the metal that are causing the charge to build up. That's my point. It's in the space between, you're charging up the air gap essentially too.
Well, no, it's not quite like that. You have a physical quantitative migration of electrons that move from one plate to the other. You could actually, if you could microscopically zoom in and force them all through the exact same single path, you could count how many actually flow from one plate to the other. There's a quantity of electrons that actually move in that circuit and are displaced. Now, they don't necessarily need to, the electrons from one plate don't actually make it all the way down the wire and all the way over to the other plate. They just simply move out of one plate and they push on all the electrons in the wire, and then some electrons at the very end of that wire then exit that point and they move into the other plate. So they call it a displacement current instead of, saying that the charges physically move, unlike where when you have a Wimshurst machine, the charges are physically separated because they are the same charges. There's no conductive circuit between the individual pads. So when you mechanically move them, that's the second type of capacitor where there is no physical contact and the charges are trapped on the actual metallic conductors themselves, if that gives you an idea.
Okay, thanks. That's cool.
Sorry. Hope it wasn't too complicated. I'm gonna grab something to drink. Y'all take a discuss whatever you want.
What's that?
I said I'm gonna go grab something to drink. I'll be right back.
So let's see. Anyone else got something to talk about?
Well, I think I could come up with something here. When I was younger, we talked about capacitors. I talked about some capacitors to these electronics dudes, and they said that they don't know where the charge is inside the capacitors, or it's like when you generate electricity with a generator, where are all those electrons coming from? Are they generated from the ether? Are the ether generators? I'm confused about that. But I just need to read up on it and study it more. But I've seen it's hard to get the real science when you go through the internet and search this stuff. Like some of these guys are saying one thing, and then you can get the exact opposite of what they're saying from some other expert.
Where the electrical energy was stored in a capacitor. His conclusion conflicts with how physics describes capacitors today. This video will describe that conflict and show you how to prove that Benjamin Franklin was right. This is the basic outline that we are going to follow. Now, why does it matter that we understand how a capacitor works? First,
doesn't apply to vacuum capacitors, just to mention that.
First of all, a capacitor is a very fundamental component in our electronics today. If we were to
might be useful to look at how they use electrical charges to basically force water flows so that you can do reverse osmosis while repelling other materials that don't go through the charge. Kind of like you have an empty hose and you turn it on, it takes quite a while before you have any flow of water at the other end. But if you have a full hose, the second you turn it on, that water pressure immediately shows up on the other end because it's pushing that water that's already in the hose out. So.
I do remember some basic videos on the Leyden jar and how they were able to store a charge inside this glass jar or capture electricity in it. You've heard about the Leyden jar?
Me?
Anyone? I guess
Yeah,
that's Franklin.
That's actually what Franklin used in his experiments. It was a Leyden jar, and that's why I was asking Remi about where is the charge stored, because a lot of people think it's in the metal plates because that's what the free electron theory is, but actually you can take, like Jeremiah described, you can take that piece of dielectric and set it over here and do a bunch of stuff and then plug it all back in, and it's like a battery. It just stores the charge. So and I feel that's how the so-called vacuum energy works too, is it's a type of dielectric. It has a real high dielectric constant, so you can't, and in some cases it's negative, and that affects the properties that we observe. So, if it's negative, then that's kind of like imaginary, mathematically.
You might look into Celeron's backing and research from the Princeton University research they did on the PAIR project, where they were basically using the concept of basically the mind affecting the virtual particles that normally wink back out of existence all around us. But if you were to concentrate on a specific given area, you could create more potential for them to remain and then become a part of the matter and energy that's in the surrounding environment to tip a scale, which is what their think off light is based off of, where they use REGs, random event generators, where basically your mind is attempting to concentrate on that random stream of events to tip them one way or the other. So Celeron.com, people that worked on the original PAIR research project are still basically over there. I don't know if all of them are there. I know some took their research from the Princeton Engineering and Anomaly Research Group and started applying it to epileptic seizures. And they had a lot of success at basically building devices that could detect a seizure from someone using, it hooked up to a computer to gather that data and sift through it. It was able to let someone know after it had tuned up to that person up to 8 hours ahead of time exactly when they were going to have a seizure within 5 minutes, which is much more accurate than a dog can do with whatever they're doing with their ability to sense and recognize an oncoming seizure for someone.
Wow. Wow. Quantum biology.
Right.
So that on that subject of the capacitors and the Leyden jars, I put a link to a YouTube video in the chat, and I just wanted to mention it. It's about 21 minutes, and it talks all about how basically why Ben Franklin's model is better than Maxwell's.
I have a copy of that program. It's kind of abandoned too, where their software basically enables you to use your CPU as that random event generator device to switch it on and off. And it's more of a training tool, but I think if someone wanted to tear it apart, they could probably re-engineer it to where the computer could then be used to activate external effect, since it is affecting an external effect of an image on a screen. So it's called Shape Changer. It's not very big because it was made back whenever I think Windows 3.1 was basically just going out. So you need an older operating system from what I saw, though. I tried everything in the world, and anything past from Windows 7 on, I wasn't able to basically get it to work. So it requires something like Windows 2000 or
What was it? How about XP?
That's what I'm saying. I think XP and 2000 are the end of the limit of what you can get that program to run properly on. So, but I've used it successfully with other people and had fantastic results testing our abilities and seeing what the difference is between those who basically have been using it for a while versus those who come in fresh trying to use it. So
I think you can use. I think you can use those operating systems in virtual environments. There was a place, or at least I thought there was a place you could go and work in a virtual 3.1 or
yeah, you should be able to run them in like
XP.
a sandbox. So I'll have to look into that. So anyway, like I said, though, since it's abandonware, if anybody wants a copy of it so they can toy around with it, just let me know. It can be sent through email with no problem. So
cool. Yeah, I'm working on a few ideas with my rotating liquid stuff. But since I'm so busy now moving from Roswell back to Albuquerque, I won't be able to have anything to show anybody for a little while. I'm trying to get an idea virtually or a mind experiment on how this thing would work. You know, I've done a lot of fails because I haven't had physics training. So I was pushing magnets around with electromagnets and, you know, sending them through glass tubes in a rotating disc. And I thought, yeah, I can change the weight of this disc from one side to the other on every half cycle. And then I thought, yeah, that works. And then I started looking at it and I think, well, for every action, there's an equal and opposite reaction. So every time I turn this electromagnet on to send the neodymium magnet, you know, to the up towards the middle of the disc, I realized, yeah, I was changing the center of mass on that disc, but the thing would change to make it wobble just like it was a static unbalance. I couldn't, you couldn't make it rotate every half cycle without it wobbling. And then, you know, Ron was telling me, well, and if you put this, you put a component in the liquid spinning, it self-balances. There's just thousands of little tests that I need to do to convince myself. I'm not theoretical enough to say, oh yeah, well, I should have known that when I move that magnet around with an electromagnet, it's going to move the center of mass to compensate for the change in center of geometry, and it'll just wobble again like a static unbalance. So I just wanted what I call a dynamic unbalance. So I thought if you could get a dynamic unbalance where it's just unbalanced, you know, I don't know how you're going to do that without getting, you know, by getting around Newton's third law. That's the whole thing about acceleration with me, because when it's going around in a circle, it's in constant acceleration. And I'm still trying to put those ideas together with equivalence principle, because, you know, Newton in a linear elevator in space, you accelerate that elevator, it's an acceleration. It's a result of what gravity is. He says it's curved time space. Well, okay, so you're in that elevator accelerating linearly, and it feels like you're standing on the Earth at 9.8 meters per second squared. Well, if you're going around in a circle, you're also being accelerated in an angular system, and you're in constant acceleration. It's centrifugal.
I can hopefully answer something about that if you'd like.
Yes, I would love to hear it, because it'll save me a lot of time.
Okay. So dealing with the gravitational part, the mass attraction to another mass. If you have one mass and it's sitting in free space, and you have another mass that's also sitting in free space at some distance away, and you accelerate mass A towards mass B, as in you apply a force only to mass A, mass B does not have a force applied to it, and this only works in a universe that also has lots of other masses in it that are points of reference that can create their own fields and consequently sort of balance out the gradient, so it's fairly even all around us, like the universe that we have now. So this doesn't work in a universe where only those two masses exist, because they create an entire gravitational field gradient wherein they are all of the space because they're the only things that exist. So anyways, in this case, we accelerate mass A towards mass B, and we accelerate mass A in a straight line. So from mass B's perspective, mass A was sitting in one spot, and is sitting there constantly, so that the amount of gravitational force attraction it has is the amount of gravitational force of the mass that mass A has at the distance that mass A is located to mass B. However, when let's say we have mass B moving at a constant velocity towards mass A, let's forget the acceleration for now, it's just moving at a constant velocity. Mass B's field, because it propagates out at the speed of light, is effectively building up in front of mass B, and mass B's field is effectively being stretched out behind mass B. So if we accelerate mass A, mass A's field is being compressed in front of mass A and being stretched behind mass A. So mass A's field, if we suddenly stop it here, the field of mass A moving along at the velocity of light in the direction of mass B is going to keep on moving out of the place where mass A stopped towards mass B, and when it hits it, mass B will experience all of the gravitational attraction of a mass that had the field of a mass that was existing in that amount of space for that amount of time, which will be much greater than that mass if it was static. See, that's an interesting phenomena, that you can actually make a mass appear to be much, much heavier along a certain axis, but only along that axis, only in that direction of travel. Now, onto your question of angular acceleration.
So go ahead.
Circle, it doesn't do the same thing, because the path of the force of the angular acceleration is constantly changing. So it doesn't build up in a line, and consequently you can't react against it in the same way. It's not such an unbalanced force. But there are ways to use it, because velocity takes part in all of this.
Interesting. Now, to get back on your first thing, mass A and mass B, mutual mass acceleration. When you're saying this gravity field that it's pushing in front of mass 1 that's headed towards mass 2, for instance, you're saying that this gravity field is ahead of mass 1.
I'm saying that the gravity field is going to be wherever the mass is, and it's going to leave it at the speed of light. So if you were to move the mass at the speed of light for 1 second, then it would have all the mass of that entire thing that, let's see, how would you calculate that out? I'm sure there's some calculations for this to figure out what the actual mass energy would be if you moved it at some velocity c for X amount of time in a given direction. I know there's equations for this. I'm not going to try to do them in my head right now.
That's okay. Yeah. So, but what I'm kind of getting at, I guess, from what I understand, and it might be a relative thing. It's like if you're in the frame reference of mass 1, and you see you're sitting still, and it looks like mass 2 is coming towards you. Or if you're on mass 2, you're sitting still, and it looks like mass 1 is moving towards you. That's relativity, isn't it?
Yeah, but there is a difference. A lot of people wonder about the twin paradox and this idea of who accelerated, and it's confusing, because you're like, well, if it appears the same from both persons' perspective, how does one tell who moved? Okay, let's say that you. Sorry, give me just a sec. Give me just a second.
Sure.
sorry. Okay, so let's say that you're sitting inside of a cylinder with a floor and walls and a ceiling, and you can't see outside. So in case one, you are going to be rotated. You're not rotating yet, but you're going to be rotated. In case two, the universe around you is going to be rotated and you are going to remain still. Can you tell the difference between the two cases?
I don't see how, but if you got
Very
an answer for that,
in case
very
two,
simple.
you are sitting still, you're sitting you're standing on the floor in the cylinder that's closed, and the universe rotates around you. You will stay exactly where you're standing and not feel any force. However, if we rotate you and not the universe, you'll be flung towards the wall. There is a way to tell, because there's an absolute frame of reference based on which has more energy and how long it's existed. And
yeah, it took a lot of energy to rotate the universe. Yeah.
Right. So the thing is, it's causality, because the most recent event, the most recent radiation of energy, as in a change in the physical location of all charged particles, was your event where we rotated you. And because it was the most recent thing, you experienced the difference in the change because it happened at your event. And now it has to propagate out of the speed of light for the rest of the universe to realize that you rotated. But the rest of the universe has already been sitting there. It's already been existing. So, you know, it's not gonna have the same effect if you don't move.
So like I'm moving right now here, and I'm sending out a wave. It's affecting everybody in the universe at the speed of light when it reaches them. But
Yeah, every
it's square, so it's going to be a real small force.
Every piece of mass that moves creates a little wave that travels out at the speed of light, which is also a variable based on the refractive index of space, into the ends of the universe forever. And that effectively creates the space between objects. That's where you're getting your physical space from. That's why there's so much more energy in space than there is in matter, and why space is so much larger, as in there's more space than there is matter. Matter takes up a tiny, tiny, tiny little amount of the actual physical volume of what we call the known universe. And the reason for that is because the longer electric energy, magnetic fields, the longer these things are radiated out, the greater the space becomes between them, because these fields never die off. They just permanently keep on traveling. And because they continue to persist, but the particles that produce them never die off, the ratio between how much physical energy the two contain continues to get larger and larger and larger.
So out there on the fringes of physics, the last speaker we had, I watched him. I wasn't able to be on the whole thing, but I watched the recordings talking about trying to find dark matter, trying to find evidence of it in those drums of liquid underneath the earth, you know. So we don't know what the dark matter is,
or if it exists.
Or if it exists, right? I mean, it's all a mathematical thing to make the balance of the equations, right? And the dark energy too. I assume dark energy is not connected to dark matter. Those two things.
Well, they're both dark.
You can't see them, but there's a lot of energy in that dark energy. Oh,
so,
well, like
Jeremiah, I had one question about your description of one mass going towards the other, and how that you're basically saying so basically space-time in between the two masses, they approach each other, is denser. And
well,
and thinking about it at the subatomic scale or the atomic scale, what happens to the protons and electrons? Isn't it like become egg-shaped, where the pointy part of the egg is where the proton is in the field, and then the electron comes out in like a parabolic kind of orbit?
The answer to that question is it entirely depends how you accelerate your mass.
Okay. So
if you push it
constant acceleration,
pull it from the front, you're going to refract it. If you accelerate it uniformly from the sides, you're going to have a drag in the center mass. If you somehow can grab onto all of the mass simultaneously, magically, with your device that can couple to every piece of mass all at once, then well, you'll have a perfect acceleration field. But in either case, what you're going to end up with is, based on its velocity compared to the speed of light, you're going to get that compression for however long it was spending going at that speed. And that's a field effectively that once it builds up, you know, you're in your own field, but if you suddenly stop and you leave your own field, as in, you know, you're no longer moving that velocity, you suddenly decelerate down, that field doesn't just go away, it continues to move. So if someone had, say, came out of warp drive and they stopped very, very close to a planet, the gravitational wave produced by their sudden stopping, that momentum from the mass that they had built up traveling that velocity at the speed of light, say, for example, or faster, is going to suddenly come rippling back out, and it's going to slam into whatever's in front of it in almost a beam-like configuration. And so if they exceeded the speed of light, there would actually be a gravity suction beam that would pull on anything that was in front of it. And if they had just gone at exactly the speed of light, all of that mass energy would effectively just be a huge force beam that would slam into whatever it hit, sort of like Pockledon's force beam.
But that wouldn't that assume that gravitation and electromagnetism are connected somehow?
Well, they're connected in many ways by means of the fact that they both have to propagate through the vacuum. And in doing so, they both have to follow a couple of rules, meaning that they propagate without a variable refractive index that's different, or for any other reason, through, you know, the pure vacuum with nothing in it. They both propagate at velocity c, right? They both die off by divergence by the inverse square of their distance. They both follow effectively a lot of the same rules. So you can use the same types of understanding to map both systems. And yes, they do produce the same types of unbalanced phenomena. If you move an electric charge, for example, along a straight path, the same exact thing happens to the electric field of the electric charge as happens to the mass field of the mass. You get a buildup of the electric field, and it appears as if you have a very, very large amount of charge, which is why we measure fast-moving charges not in velocity, but in electron volts, meaning that this one electron, which normally has 1 electron volt of charge, now, because of its velocity, has the same amount of energy as 100 electrons, 100,000 electrons, 10 million electrons, because it's moving really fast. So the actual electric charge field that it has is as strong as 10 million electrons in that same point. That's effectively what that electron volt number means when we talk about particle accelerators, is, you know, that electron has gained relativistic mass and a consequent relativistic electric field, which now makes it way more and makes it have a much greater charge. So all that needs to be considered.
But the example of tunneling shows that you can actually go superluminal. It's not really going superluminal, but isn't the vacuum or empty space just another type of barrier, like in a tunneling?
Well, yeah, then there's the theoretical idea that the charges themselves may somehow be in a geometry that can modify the refractive index because of the gradient that's produced by their motion. So say they may be in some kind of strange phase or strange state where they actually can go superluminal without technically themselves moving superluminal.
Right. So an example I was thinking of is I heard about this observation where they had a star that was falling into a black hole, and it popped out the other side.
What?
Yeah.
What?
It popped out the other side. It didn't get absorbed. It just tunneled right through.
Oh, right. So what happened to it? It didn't like fling it away, did it?
No, it just popped out the other side of the event horizon. It's like a jet and a black hole. When the jet's coming out on this side, the other side, there's a jet coming out of the opposite spin, just like an electron at orbit around a proton. That's what happens in protons. The electrons tunnel through the proton. It happens all the time.
So you're saying that in this case, instead of this object sort of disappearing into the event horizon, taking some long period of time and then popping back out, it was pretty much in one side, out the other instantly.
Yep. They observed it. Well, they can't say instant, but yeah, that's what it looked like.
But at the resolution limitations of whatever astrophysicists have right now, we observe what we believe to be this thing that you're describing to me. So very interesting. very interesting.
Yeah, I thought
indeed.
it was pretty cool too to see a tunneling example at the cosmic scale. See,
And Michael, can you hear me? There was a group observation of the Sagittarius A black hole, which is the supposed black hole in the center of the galaxy. And there's this G2 object, and it was a group. It proves that there's no black hole in the center of our galaxy, because it just goes, it swings through. And I was just talking
where it's an event horizon, you just can't see it.
No,
there was a distortion though, so there's like a heavy gravitational field. That's what really confused them, is that it didn't just wander through like empty space, but it didn't get sucked up like a black hole either.
Okay,
now they're supposing that might be dark matter that's creating the gravitational pull at the core.
No, it's the plasma toroid jet model. So like, let's go back to Robert Forward's paper, and like you have a bunch of charges moving around. He has like a poloidal as well as a toroidal, but just apply that to the stars in the galaxy, right? They all have an electromagnetic moment, and they're all whizzing around the center of the galaxy, the barycenters. So they generate a fake gravitational moment, or a virtual black hole, and then it's, the laws of electromagnetism are applicable at the galactic scale. We're just not doing it. That's like the whole, we're detection of a drag force in G2's orbit, measuring the accretion flow, something. Here, let me get the full archive. Measuring the density of the accretion flow onto Sagittarius A at 1,000 Schwarzschild radii. And it's this huge group paper. Was published in December 4th, 2018. Tuesday, yeah. So that paper, that is like empirical evidence that there really isn't a black hole at Sagittarius A. It's more of the dynamic, the addition of all of the stars' moments circling around the galaxy create this thing
So it'd be like basically taking the planet, separating it apart evenly, but it's still equally like distant. All the particles are, so you end up with a lot of black volume in between. Still has the same gravitational field at the very core of where that planet was.
No, it's the stars itself, like Sol. Like our sun is a nuclear fusion reactor with this huge electromagnetic field, right? You can see it in Jupiter as well. But they're all of the stars whirling around. It's like dust. I don't know if you've ever played with an XY table on a router, and you have a vacuum tube on it, and it's cutting out wood. You have to run ground through it, because all the particles zipping through the tube in a vacuum creates static on the outside of your dust collector system. So there is dust. There's this, the stellar water that gets blown out of stars. So there's, it's that Sam guy a couple of weeks ago was having at that the dark matter physicist from New York, the plasma toroid jet model, or plasma cosmology, and Anthony Perret. He worked up at Los Alamos, and his physics on plasma cosmology were declassified a couple of years ago. So it's there may be black holes, but I mean, I've studied through the mathematics, and it's, Schwarzschild came up with the solution, a field equation, and it had a 1 over infinity. So like infinite smallness, and they just called it a singularity, and we've been stuck with it ever since. So there may be black holes, but there's plasma cosmology. There's, it's the electromagnetic moment of stars. I mean, one of the things that clicked after seeing optical cloaking, neutron degeneracy, right? Like the neutron stars. There's no more external magnetic field on a neutron star, so light can't interact with it. Like it's, I guess, getting absorbed or whatnot. And so some of these characteristics of black holes are ascribed to degenerate matter, and we're still in this mess, academic mess of like, ooh, a singularity, and it's synonymous with death. and it's, oh, I'm going to die one day. So the mind clicks onto it, or the average person's mind thinks it's terribly fascinating. But it's a mathematical concept. The crowd has been running wild with it since World War I, and we're slowly finding out that there's better, you start applying electromechanical dynamics, this plasma cosmology.
Well, when I first heard about black holes, I figured it was proof the whole universe sucks.
Well, you got to remember, black holes have no hair. So anyway, it's a dirty joke from like the 60s.
You have to understand that the universe both sucks and blows simultaneously at the same time, though.
Yeah, I call it
sucking and blowing.
I call it the frat boy theory.
Continual expansion.
So yeah, it's really kind of cool that all this stuff. It's all the walls are getting torn down is what's going on. It's more and more information comes out. It's like at one point, did they say that all physics had been discovered?
Oh yeah, that guy.
Remember? So it's like now it's like we don't know nothing.
The consensus is becoming the wise consensus of we don't know nothing, instead of it just being the isolated few free thinkers that seem to be on the fringes of physics. I do like what's happening.
Well, even the military seems to be admitting we don't know nothing either.
I'm glad to know that we've had our part in helping that along at APEC and making this event happen. So
yeah, I'm with you.
This is a lot of fun.
Yeah. Now, what I'm hoping is that and that's kind of the reason why I keep bringing up these like seem kind of esoteric, like non-violence and intergenerational trauma and stuff, is because those are the folks that I think are dealing with a lot of. I mean, it's not just the stigma that they have to overcome, but just think of all this internalized trauma that they've had to do because of the job they have, just where they're at. And so why would anyone want to stick their neck out and say anything where they're going to get criticized when they've probably been dealing with it? They've been internalizing it for so long. And that's why I think we got to open it up, making it so people feel comfortable talking about it.
That's why I like to hide behind my, I'm an artist, not a scientist. Because if I try to be like academia, then, they all jump on you. The first mistake you make, like I said the other day that light was traveling at 300,000 meters per second. I said to this lady on one of these APEC conferences, nobody said anything. Well, I was off by like 3 zeros. It's just 300,000 kilometers.
Close enough.
And then I told her that the Voyager was going 1/3 the speed of light, because I googled it real quick and it said an ion engine could make it travel at 90,000 meters per second or something like that. So anyway, I just thought I'd clear that up. And, nobody trolled me on it or anything. I only got one troll on my website. And he said, no intelligence found here on this troll comment. No intelligence found on gravityalchemist.com.
Well, criticism is an expression of an unmet need. That's all. Don't get criticism. It's people say stuff to you that, especially people you're close with, that they'll get angry or something. They'll say something totally the opposite of what it's not. Somebody's trying to express something. They have a feeling. It's about feelings and needs, and people don't know how to express their feelings in our culture.
Mm-hmm. Oh, and like academia, you got to be careful, because as soon as they catch you on a mistake, they're gonna do like Eric Laithwaite and say, he didn't know what he was talking about. the guy that invented all of the, I love Eric Lathwaite. I love the spirit. I was like a kid listening to him. And I guess the Royal Academy or whoever it is over there in England, after he started doing those things about gyroscopes, they were all getting shaky and kind of took him off the air.
Shadow ban.
Yeah. He got banned. He got somehow, you get the really smart ones, either they're jealous or they just catch on something and then get you out of there because you either, he could have went on and really done something fantastic, which he had already done with magnetism and the maglev. It was incredible.
I wonder if this is like a remnant of like the attempt to stifle scientific investigation and research by everyday people that's been going on for quite a while. Basically, like they pulled the golden age of chemistry experiments or something like that, or a little golden book of chemistry experiments, because it was too dangerous. And this guy that died in like 2016 because basically when he was a teenager, he built a nuclear reactor in his garage, so which he was being pushed at the time to get a radioactive badge, because back then they were still pushing to improve the knowledge and whatnot, and the construction methods and whatnot to get nuclear on U.S. soil as an energy source and whatnot. So they were even pushing the youth to basically get involved in it. Now since then they've been just been pulling the rug out from underneath everything. Everything keeps getting more and more nerfed until eventually the only thing you have in science labs now are books. There are no
Well,
test
it's kind of like what the Waz was talking about. We used to. It just seems like when I was younger, everything was open source. If something didn't work or broke on my oscilloscope, I'd go look at the manual. I mean, in some ways, it's better today because if something breaks, I can go on YouTube and say, how do I change the klystron in my microwave? And there'll be a video there to show me how to do it. Okay.
That only applies though to areas where the company that made the part isn't putting a chokehold on the company that makes the individual components for it, so they can't sell you that part too, which is what the right to repair movement he was talking about was all about.
Right. So like I have a wall furnace, for example, and I can't buy the thermocouple. I have to buy a whole new wall furnace because you can't go buy the thermocouple at Home Depot, right?
Right. And part of their excuse is, oh, well, we want to be safe. We want to keep you safe. What's your plan if they make a mistake? It's like, it's not my plan to solve anyone's problems. They have to make their own choices. I'm not taking their rights and their choice away from them. That's the whole point. You don't need a plan,
Well, I mean, computers, I would get it. My son, for example, he's like 30 now, but I remember when he was like 10, he built or 12, he built his first computer, and he bought all the stuff online, and then he watched some videos online, and he knows how to build computers. Now, I learned how to build computers back when there were like 286s. Right? So it's like, but because I did that and I knew how to do it, there wasn't a barrier to him learning how to do it himself. But if you eliminate that, ability to fix it yourself, you're basically stopping innovation.
Right. Yeah. That's what they're pushing. The people that are opposed to right to repair, like Apple and whatnot, they're saying, oh, well, if you let somebody else repair your phone that, is not Apple certified, they might leak your data, or they might install TikTok, or they might do this, they might do that. And it's like, Well, then what about the guy that worked for Apple that released that woman's nudes on a phone that he didn't even know who she was. He just was supposed to repair her phone. Then he grabbed her data and just spread it all over the internet. You're not any safer with Apple than you would be if they're. In fact, you're safer, I think, with a third party because they can't afford the millions of dollars worth of lawsuit that Apple can.
Right.
You know what I mean?
Yeah.
Well, there's
much more
another
careful.
there's another side to this that I thought was really interesting, the Moore's law concept, Moore's law, and I hear Michio Kaku talk about this a lot. That things are getting less and less. They cost less and less. That pretty soon the paint on your wall will be like computer chips. Everything will be. They make them out of dirt. And it'll get to the point where they don't cost anything, and you have all this technology and all this binary information, all the powerful computer, and it could be in the paint on the wall.
Well, I'd rather leave it off the paint on the wall, William. I think enough. We have enough monitoring going on. I think we need to have days where we just leave our electronic devices alone, because I think we become too dependent on them.
Well, yeah, that's good. At some point, when you go to bed, you should make sure all the little red lights are off in the bedroom. Everything's off. It's dark. You let your mind relax.
The red light's less damaging than if you had blue LEDs or something in there too, though. So
exactly, no lights at all. No lights at all. Well, I guess there's a whole science of that too.
I actually can't sleep without sound because I'll roll around and grind my teeth and whatnot, and that actually, like a white noise, gets me to basically focus on that, I guess, while I'm asleep, so that I hardly move at all. I don't grind my teeth or anything.
So you said in the chat, Thomas, that your power went out?
Yeah, my lights just all clicked off. The only thing I have hooked up the battery backup right now is the computer and the monitors. So, which I'm on a headset, so
So you have a
thunderstorm.
Oh wow! So that knocked out your grid, huh?
Yeah, well, it caused it to glitch. Everything had to it was basically just breakers or something. It wasn't like transformers exploding or something.
Oh, but you have
seen
battery
that before.
backup.
Yeah, just a UPS. I've got a UPS on this, and then in the other room there's a UPS hooked up to the router and gateway and whatnot. So it didn't affect all of the lines either for our DSL either. So.
Huh, that's interesting.
Just the AC
just
power.
the power lines.
Just the AC, as always. The thing that keeps your food from going bad.
Yeah, well, I have battery backup too, so.
We need to get on that energy source so that we can basically have independent power sources in every place.
Yeah, well, I have solar, and I just installed new batteries, and then I had these old batteries, and then I bought this thing here. Let's see, it's
is that an inverter?
It's a 12 volt, 8 amp, 24 volt, 4 amp pulse repair battery charger. And what it does is
so you can keep using your batteries by desulfonating them.
It desulfonates them, and what it does is it makes it rejuvenates the leads, and it makes it form into these little domains. So by using a pulse. And
right. You know why they're using a pulse to do that, though, right? As opposed to just constantly hitting it with a high voltage.
Oh, it would probably break it down if you did that.
Heat. It's the heat.
Yeah, it's a heat thing.
It allows the heat to dissipate before you hit it with the next pulse. Because they do this, they do exactly what you're talking about to make the batteries in big vats, but they're not enclosed in a container that the heat can't escape. And they just constantly hit that lead with that material in order to activate it to turn it into the material that you can then stuff into your batteries
Well, it restored them.
charge.
So it's the point, and they're like 250 amp hour batteries, 12 volt. They're huge.
They're lead acid though, like glass.
They're all
mat or
lead
something?
acid. So now instead of when I install those back in, instead of 4.8 kV battery backup, I'm going to have a 9.6 kV.
Oh, nice.
4.8 kV gives me a day and a half of power, so I'll have 3 days of power.
Right.
I live in Pacific Gas and Electric territory, where they'll black me out if the wind blows too hard, or if it gets too hot, or if there's a fire over the mountain, or I mean, at the drop of the hat.
It's all down to whether they've updated or not since basically initial install and how much wear and tear it's taken, and they tend to let that stuff run way past its lifespan.
Oh, I know. Well, the
real.
problem with PG&Es, they're not maintaining the lines, and so what happens is they get arc flash to the trees and stuff, and that starts a fire. It's like PG&E's been sued so many times that they had to go bankrupt like 3 times now, and then they stick all the ratepayers with the bill.
And like they restructured not and to avoid.
Yeah, they
the heavy
restructure,
payout.
and then they take on a huge debt load to pay back all the insurance companies.
Right.
And the lawyers. So, and now my big pet peeve is they have this thing where if I could go flip the switch now and just like disconnect from the utility altogether. Well, it turns out they're going to charge me a fee, a departing load fee.
that box, that's about 1,400 watts worth of just the solar cells. So I'm not working on something to use at the house. I'm working on something to take on the road. Like it's going to be packed up in the pickup and pull it out on site and whatnot. I don't know if anybody needs anything like this, but like if you need a permanent canvas like structure, an awning on like say a skyscraper or something like that, just look up the companies that make awnings for your local buildings, because they throw the old ones away and they still have years and years of life left in them. Just have to clean them up and whatnot. I picked up one. It's probably it's close to like a kind of circular shape, like a lily pad. That's about 35 to 40 feet, depending on which direction you're measuring it. And the thing weighs about 150 pounds, just for the tarp.
So my solar panels, I got them in 2002, and they're still. So, but I gotta check out, folks. My better half just came and indicated my time's up. But I had fun.
Well, Michael, thank you for joining us.
Sorry if I pushed the boundaries a little bit there.
Oh, it's okay. Yeah, a couple of people were like, "This doesn't fit." I'm like, I understand where he's coming from.
No, I understand too. I just, I'm just being me.
No, I get it. I think we're doing good. So our next one, I think, is going to be July 31st. I have to skip to 3 weeks because I have to go out of town for my wife's thing. So July 31st, and then after that, we're probably going to do live from Tesla Tech, which should be totally off topic, but probably a lot of fun. So.
Oh yeah, that's going to be epic. Live stream from Tesla Tech. By the way, the 31st, I wanted to do a special APEC focus kind of conference on theories of everything for the 31st. So I wanted to invite David Chester back, and I've also I'm hoping to get Ken Griggs of the Phoenix Theory to come on and give a presentation, and also have a discussion between him and David Chester on deep physics. So that should be super interesting. I'm also trying to reach out. I've been kind of in loose communication with Eric Weinstein, and I'm trying to get him to come on to talk about geometric unity, but I don't know how likely that is to happen unless I can get him super interested. But yeah, that's what I'm trying to do, is to do a focus APEC on theories of everything and deeper, physics kind of stuff.
You know, I'm going to make notes on that right now. Theories of everything. And do you want to reach out to them, Jeremy?
Yeah, I just sent David an email. I've already got Ken, I think, confirmed. I've also reached out to Eric, and I'm going to try to reach out to a couple other people.
Okay. Yeah, and then Remi had another fellow, Daniel Sheehan. Different. I think this is different than the Michaels guy that he was reading earlier. Same name, Daniel Sheehan, University of San Diego, or San Diego.edu. On
Is that the lawyer guy research from Disclosure Project?
I don't think so. I think it's the same name but a different person. This one is going to talk about second law research and retrocausality. So he was going to talk about basically things that violate the second law of thermodynamics. I think he's on August 14th, I believe. That's where. And then Stephen Lutz, we were hoping to have him for countering inertial effects with type 2 superconductive flux pinning. And he might be on the 31st. And Remi recommended both of those gentlemen. So. Oh, and then Jason Sakaris, also from last session. And he is tentative. I don't know what date yet. So. But yeah, here, I'll share I'll put this in the chat. That's our schedule. Yeah, so anybody with that link, you guys can view that spreadsheet. That's kind of what I've been working on lately. So we have a bunch of tentatives. I mean, we have tons of tentatives. We'll see where things go. But yeah, if Ken and David Chester want to come on, that's awesome. And then Jeremy, have you thought about doing something more on UAPs? I mean, you did one heck of an overview a couple of weeks ago.
Yeah, well, I think all these topics are loosely related, and we should be a recurring theme for discussion at these conferences, because we have engineers and physicists together to talk on a scientific level about these things. I think we should do another. And that would be great if we can get Eric Weinstein to join us for a discussion on that, because he's posting all over Twitter saying that he's looking for scientific groups to discuss this topic with, or that are diving into this. And I'm like, well, we got the group, man. Like, so
I'll put him down too. Eric, do you think you could reach out to him and see? Maybe he'll show up.
I'm trying. I've been in touch with his brother Brett, but I'm trying to reach out, because he'd be a great asset in this, and with the stuff that he's been posting on Twitter. It's great. So
yeah, good deal, man. Good deal. Well, good conference session. I think it was exciting. We had some.
Yeah, I'm going to go ahead and end the live stream here on YouTube. Thank you, everyone who is watching this live, and for everyone that tuned in.
Deal. Thanks again, guys. I'm going to shut things down too.
Record.